I don't know. We're going to be up there. So Senator Markey and then somebody else. And it was bigger. And Rachel Raps is
Good morning, everyone. Thank you for being here. Just a note that we'll be starting in around 3 minutes. Thank you. Good morning, everyone, and welcome, not just from myself, but the whole team here at Green AI. Whether you're joining us in person or online, we appreciate your attendance and excited to be sharing with you our second summit and the first of the year. To introduce myself, my name is Leah, and I'm a student here at the college studying economics and environmental science and public policy, and I have the pleasure of being your moderator today. Before we get started, I'd like to take a moment to go over a few important housekeeping rules. We would appreciate it if everyone could keep their devices on silent to minimize disruptions, and please refrain from using flash photography during the event. The building management would also like us to remind you that eating is prohibited in the venue. And finally, please take notice of the emergency exits behind me, to my left and to my right. I would now like to ask you to please take a moment to scan the QR codes on the screen behind me to stay connected with us and what we'll be doing in the upcoming months at the Institute. To give a brief overview of the agenda for the day, after the opening remarks, the first day will feature 4 exciting panels on AI, data center energy usage and environmental impact, energy and innovation, next generation computing hardware, and lastly, green AI and data center policy and investment. These discussions will be interjected by keynote speeches, a presentation of launching initiatives involving a series of case studies featuring real-world applications of sustainable AI usage, a series of lightning talks on emerging innovations in green AI, as well as the launching ceremony for the Journal of AI Sustainability and the establishment of the Green AI Advisory Board. We will then conclude the event with a networking event where you'll have the opportunity to connect with us here at the Institute as well as the speakers. Also, please take note that our staff can be identified by the blue lanyards and the speakers by the red ribbons on their name badges. For more details, please refer to your program handouts. I would also now like to take a moment to acknowledge our organizers, the Green AI Institute and the Harvard Undergraduate AI and Sustainability Group, as well as our co-sponsor, Boston University's Center for Information and Systems Engineering. I would also like to extend our sincere gratitude to our sponsors who have made this event possible today. Our Harvard partners at Harvard University Office for Sustainability, the Salata Institute for Climate and Sustainability at Harvard, the Harvard Center for International Development, and the Harvard Provost Fund for Student Collaboration, the Harvard Undergraduate Association, and the Weatherhead Center for International Affairs, as well as our Harvard student group partners, the Harvard Climate Leaders Program, the Harvard Extension School Sustainability Student Club, and the Harvard Graduate Student of Education Coding and Co-working Club, as well as our partners at MIT China Innovation and Entrepreneurship Forum, Asian Americans in the Energy and the Environment and Commerce, as well as Climate Cardinals, and finally, the Citizens Climate Lobby at Harvard. Would also like to acknowledge the supporting journal, The Environmental Science and Ecotechnology. And before we begin our opening remarks, I have the pleasure of introducing our summit co-hosts. Professor Ayseh Koskan, the Professor of Electrical and Computer Engineering, as well as the Director for the Center for Information and System Engineering at Boston University, as well as Elise Morgan, the Dean ad interim at the College of Engineering at Boston University. So moving on to our opening remarks, this will be the official opening of the second Green AI Summit and will set the tone for the 2 days of engaging discussion, innovative solutions, and actionable strategies at the intersection of artificial intelligence and sustainability. Bringing together renowned leaders from politics, academia, and industry to highlight the transformative potential of AI in addressing the most pressing environmental issues of our time. And with that being said, I now have the pleasure of introducing Senator Edward Markey, the United States Senator from Massachusetts, who will be joining us via video to give the formal opening introduction to the event. Please join me in welcoming Senator Markey.
Hello, and thank you to the Green AI Institute and Harvard University for holding today's Spring Summit. The climate crisis is a 5-alarm fire. 2024 was our planet's hottest year ever on record. As we face politically motivated attacks on climate programs, it is more critical than ever that we fight for a just and livable future for everyone. We have tools at our disposal, and artificial intelligence can be a part of this solution. AI can help improve weather and climate forecasts. It can improve predictions of power supply and demand. And in a time of worsening severe weather, it can help monitor and respond to natural hazards. However, there is also a Dickensian quality to AI. AI could be the best of technologies, and it could be the worst of technologies. For all of its promise, it comes with real cost to our climate, our environment, and to our communities. Training and deploying AI models consumes substantial power, massive amounts of electricity, which is delaying coal plant closures and leading to the build-out of new natural gas infrastructure. Cooling data centers requires huge volumes of water, often in regions already facing droughts, and the computer chips that are needed to run models require mining raw materials that bring negative impacts to communities and add to a growing e-waste program. It is now getting worse and worse with e-waste. So to meet this moment, we need responsible, long-term planning to address AI's impact on our environment without sacrificing climate, environmental, and energy justice. And that is why I have introduced my Artificial Intelligence Environmental Impacts Act to study the full range of impacts due to AI. The good part of it, the positive, and the negative, the destructive. We must ensure that the AI era does not come at the expense of our clean air and clean land and clean water. We must work to ensure that we get the best of AI, but that we put controls around the worst of AI, especially as it impacts our environment. Thank you all for everything that you are doing to work on this issue.
Thank you, Senator Markey. I now have the pleasure of introducing Secretary Tomas Lamanauskas, the Deputy Secretary General for the International Telecommunication Union, who will also be joining us online. Please join me in welcoming Secretary Lamanauskas.
Thank you. Thank you very much for this introduction, and thank you for this opportunity to address this opening session of Second Green AI Summit. And indeed, it's a bit of a challenge, but also opportunity to follow Senator Markey on this, because of course he mentioned already some of the key challenges that AI faces, or AI development faces, and I'll hope to provide additional color in this as well. And I'll be speaking, of course, from the perspective of ITU, the International Telecommunication Union, which is the United Nations Agency for Digital Technologies, and we'll speak about our also perspective of how we can together make AI more green, but also how green AI can drive sustainable development globally. As Senator already mentioned, 2024 was the warmest year on record, and it was really the first calendar year in which the annual global average temperature exceeded 1.5 degrees Celsius above pre-industrial levels. Wildfires, droughts, and floods are getting more frequent and more intense as climate change becomes our everyday reality. The next UN climate conference, COP30, just over 6 months away in Belém, Brazil, comes at the epicenter of that accelerating climate crisis. As we seek solutions, AI offers a double-edged sword. It does consume a lot of energy and adds to the greenhouse gas emissions. Yet it can also do so much to reduce them. But first, a few words about the opportunities, broad opportunities that AI unlocks. Earlier this week, IMF reported that economic gains from artificial intelligence are expected to boost global output around 0.5% a year between 2025 and 2030. Yes, it does come with risks, including misinformation, disinformation, biases. And yes, these gains are not shared equally across the world. However, in these economic challenging times, such a boost is sorely needed. AI is far more than a business opportunity. In countries around the world, AI is enhancing agriculture. It is helping optimize energy grids, transport, and supply chains. It is bolstering humanitarian aid and boosting resilience against natural hazards and climate-related disasters. It is driving rapid breakthroughs in healthcare and neurology. For example, last year at our AI for Good Global Summit, we had a feature of brain-machine interface, or BMEIs. In one demo, a Portuguese MS patient, Luis, answered real-time questions from an emotional audience. It really gave us a perspective of what AI can do for good. That annual summit, powered by ITU with over 40 UN partners, has become the global showcase for responsible AI, as well as a key venue for global dialogue on AI governance. The next one happens between 8th and 11th of July here in Geneva, where I'm now, and I invite us to join you, and I invite you to join us either in Geneva online, indeed, and hopefully see you there as well. However, also coming back to AI benefits and opportunities, I want to emphasize that, of course, we need to maximize the benefits, but also looking how to minimize the risks that are occurring due to AI. Well-designed standards can uphold people's fundamental rights and ensure AI benefits everyone. To date, ITU has published 120 standards on AI, with 130 more under development. ITU's World Engagement Organization Assembly, WSA24, in New Delhi last October, featured the first episode of the new International AI Standards Summit, convened together with ISO, International Standardization Organization, and IEC, International Electrotechnical Commission. The next one will follow in Seoul, Republic of Korea, on 2nd and 3rd of December this year. This process helps us align our work with global goals, boost our combined impact, and build a better future for all. Key consideration for development of artificial intelligence is definitely its climate and environmental implications. Already last year, leading AI firms acknowledged that their energy use had nearly doubled, and their emissions were up about 50% compared to 5 years before. A new report from the International Energy Agency shows global investment in data centers reaching $500 billion last year, nearly double the level in 2022. Data centers currently account for about 1.5% of global electricity consumption. The IEA reckons that total electricity demand will more than double, and by some estimates could even triple in the next 5 years. Fortunately, renewable energy sources will cover about half that growth. And just as importantly, existing AI applications could reduce the world's overall energy-related emissions by some 5% by 2035, according to the IEA's analysis. That's because AI can optimize manufacturing and transport, maximize energy efficiency, and cut emissions across so many sectors. A winning solution in one of our AI and machine learning challenges integrated AI neural networks to cut energy consumption by 5G base stations up to 20%. AI optimizes energy storage and distribution in real time. This is key for variable sources of renewable energy. AI compute centers are good clients to absorb peak energy from the wind and sun, a surplus that could otherwise overload grids. Put simply, green AI needs renewables, and efficient renewables just as surely need AI. That is, if the energy and tech sectors work together. Still, we must tackle the impact of AI itself. We need tech giants to keep their promise and cut their own emissions to net zero. Tech companies are already major drivers of green growth. Our latest Green Digital Company study, which we conducted with the World Benchmarking Alliance, shows that the tech sector accounted for around 3/5 of renewable energy purchases globally. Yet for now, the energy demand continues outpacing investments in renewable power. And to significantly reduce their footprint, companies need to address emissions across their entire value chain, from component suppliers all the way to consumer device use. As Senator also mentioned, electronic waste is another big issue. Out of 62 billion kilograms of e-waste generated globally in 2022, only 22.3% was properly recycled, according to our global e-waste monitor. E-waste contains valuable materials that can make tech recycling profitable and reduce pressure on limited resources. The value of the metals contained in the e-waste generated in 2022 is estimated at $91 billion, while the value of recovered metals is estimated at only $28 billion. This is part of the business case for green AI. To complete the picture, however, it is important to note some other crucial ways in which AI helps us to fight the climate crisis. For example, satellite imagery enhanced with AI models greatly improves weather forecasting and ability to monitor our planet's climate. Natural disaster early warning systems reduce mortality 8-fold and give a 10-fold return on investment. This is why ITU is proud to co-lead the UN Secretary General's initiative to ensure early warnings through all by 2027. AI can support this by enabling more timely and more accurate warnings and more precise and efficient ways for them to reach all affected. The ITU Council, in a resolution last June, reiterated the need to align rapid global digital development with environmental goals. More specifically, it urges to ensure tech helps achieve the aims of the UN Framework Convention on Climate Change. Our key initiative in this regard, Green Digital Action, began 2 years ago ahead of COP28. It is based on collaboration among governments, the tech industry, civil society, the key international institutions to align tech with a green future. Together we aim to cut tech-related emissions, drive green standards, foster circular economies, enhance disaster alerts, and leverage tech for climate action in every possible way. Our relatively new pillar on green computing is focusing on such aspects like environmental management of cloud services, guidelines for energy efficient sustainable AI systems, production lifecycle management, usage and reporting on physical components, efficient operation of data storage facilities, developing energy efficient sustainable software, and the sustainability of communication infrastructure. We had a notable win at the last UN Climate Change Conference, COP29, in Baku, Azerbaijan. The COP29 Declaration on Green Digital Action, which was put forward by the Azerbaijan COP29 presidency in close collaboration with us, has attracted endorsements from nearly 80 countries and 2,000 companies, organizations, and other non-state entities from around the world. The COP presidency put it forward on 16th of November last year, also known as Digitalization Day, which is the first Digitalization Day at the UN climate talks as part of an official climate action agenda. This declaration on green digital action calls us all to find and deploy digital climate solutions, cut GHG emissions to net zero, build resilient digital infrastructure, and more. It is a very important commitment and a key step to a greener digital future. Dear friends and colleagues, we're also determined to ensure that everyone benefits from digital technologies, including the 1/3 of humanity which is still offline today. Our Digital Infrastructure Investment Initiative, co-led by ITU with 7 development finance institutions, aims to close an investment gap estimated on $1.6 trillion. Massive digital investments, if done right, can also be green investments. They can boost efficiency, enhance resilience, and help build social and economic as well as environmental prosperity. The 4th International Conference on Financing for Development, coming up in Sevilla, Spain, between June 30th and July 3rd, is going to be a milestone in this regard. Game-changing digital infrastructure investments, like we aim to unlock there, can drive green digital progress for the benefit of all. So, dear colleagues, on the road from Baku to Belém, we're joining forces with GITEX as well, the world's biggest tech and startup show, to hold a special Green Digital Action Summit as part of a GITEX Europe in Berlin on 23rd of May. It will provide a further opportunity to build upon the COP29 Green Digital Action Declaration and build a momentum to make digital a key part of a climate agenda as we get ready for COP30. We must ensure that digital, including AI, is at the heart of the climate agenda, just as climate action must be at the heart of digital progress. We must together ensure that AI is not another threat to our planet, but a powerful tool to meet the challenges of today. And I thank you very much and have a great event. Thank you.
Thank you, Secretary Lamanauskas. I now have the pleasure of introducing Vice Provost James Stock, the Vice Provost for Climate and Sustainability and Director of the Slaughter Institute for Climate and Sustainability, as well as the Harold Hitchings Burback Professor of Political Economy at Harvard University. Please join me in welcoming Vice Provost Stock.
Thank you. It's great. It is, let's see, should I be holding this thing?
Yeah, okay. Thanks. It's really great to be here, and I'm delighted to see this turnout. And I'm especially delighted to see all of the enthusiasm and efforts that went into doing this. This is just great. I love to see the momentum and the excitement. My name's Jim Stock. I'm Vice Provost for Climate Sustainability, Director of the Slaughter Institute. I'm an economist. That will be obvious in my remarks. And I'm really an enthusiast of all of these sorts of activities. Let me say just one word about the Slaughter Institute. We're here on campus. We're 2.5 years old. I think many of you know of us. And we sit technically or bureaucratically in the center of the university, report up to the president and the provost. So our job is to lift up and to promote and to support and to energize work in climate and sustainability across our academic spheres. And that includes faculty supporting faculty research, it includes students lifting up students in multiple ways, such as in this event, which we are delighted to help to support, and in external engagement and profile and so forth. We really like to think of ourselves as the hub for all of these exciting activities here at the university. There are incredible enthusiasm and energy around climate sustainability across the university, and to the extent that we can help provide a higher profile and support that and create a hub for that, that's really exciting. So let me say just a couple of words on the substance here. So I'm going to start on the Green AI Summit. It's terrific we're doing this, and those were both very good sets of opening remarks. I'm going to talk mainly on the green part of Green AI, and then I'm going to come back to the AI piece of that. So as we think about the challenges facing society broadly, global society in terms of how in the energy sphere, I think it's useful to think of four priorities and four goals that we're trying to achieve. The first of those goals is to drive economic growth. So there's large swaths of the world where people are still living in what is often referred to as energy poverty, where there's extreme inequality, where really small things like abilities to charge a cell phone or ability to have some power for irrigation can make an enormous difference in terms of welfare. So there's vast swaths of society globally that have inadequate energy. And even here at home, of course, we are in developed worlds. Energy is an important driver of all of our economic growth, even with increasing efficiency. We see, for example, as was discussed, how important energy availability or power availability is for AI, which is a brand new important driver of economic growth. A second, so if the first criterion then is driving economic growth, the second criterion is affordability. And of course, that's related to it. The only way you can have abundant energy that's going to drive economic growth is if you can afford that energy. So making sure that energy is affordable, people are really having access to it is a key driver. And indeed, we've seen multiple times that this is not just important in developing economies, but is really a driver of concerns in developed economies. So I think it's certainly safe to say that much of the re-examination of green commitments in Germany and in Europe has been related to energy costs and the possibility that, you know, as they move increasingly towards more wind and solar, that's and batteries on the grid, that's going to be driving up and has been a source of high energy costs. It's certainly not the only source of high energy costs in Europe because of high natural gas costs, because of the invasion of Ukraine. Here, domestically in the United States, high energy costs are also really an important driver of political opinion and of expectations of inflation. So, and then expectations of inflation are related to senses of overall welfare. So it's really clear that affordability is a critical feature, even in developed economies and certainly in developing economies. A third characteristic that's incredibly important, and I'm sure you'll hear more about this today, is reliability. So it's one thing to have it available in theory and cheap in practice, but if it's not available or if you have blackouts, those can be extremely costly. So there's really this technical side of energy system design where reliability is really ensured. So that's an incredibly important third criterion. And then the fourth criterion, I haven't actually mentioned anything green yet. I've also, everything so far has just been talking about energy systems. But the fourth thing is that we have to bear in mind that we need to do this while decarbonizing. So we need to make sure that we really need to try to get all four of those goals, growth and affordability and reliability, and do that while we're decarbonizing. And so that's really the big challenge that we have. I think what we've seen in there are some good remarks. I had some statistics to share, but now the warmest year on record statistic has been shared twice for last year. My little tidbit on that is that actually January was plus 1.75 degrees among pre-industrial January. So that's a big number. Here's another little statistic, an interesting one that was just released by NOAA without a lot of press earlier this week, which is that last year, overall global CO2 concentrations increased by 3.7 or 3.8 parts per million, which is the largest increase ever. The previous record was 3 parts per million. So this is really a big, big jump in terms of the increase. So it's not like, we've turned a corner and we're going the right way on emissions and so forth. Well, we're like accelerating in the wrong direction. So that's a pretty significant, pretty important thing to keep in mind. So we've blown past 1.5 degrees. We're going to blow past 2 degrees, maybe 3 degrees is a plausible thing. And that brings us into a world that we haven't really experienced before. So for a long time, where did this 2 degrees come from? It's kind of that's an interesting question. I don't know if anybody knows the answer to that. It appears that it basically comes from the historical record over the time that humans evolved. And over the time that humans evolved, we had fluctuations in this 2 degree-ish range. And so we kind of know, we can get it done. We can get it done. We might have a little more ice or whatever. We haven't done the 3 degree thing. So we just don't know. We don't know what that's going to be doing to ecosystems. We don't know what that's going to be doing to human civilization. It's going to have really big disparate effects. You say 3 degrees, but actually it's more in certain parts of the globe, like in the Arctic, and it's more over land than over sea. So these are really big changes that we haven't experienced before. We just don't know. And if you take a precautionary principle perspective, maybe that's the strongest reason to think that we've really got to do the green part of green AI. So then where does this bring me back? We're in a political moment right now where there is not a lot of policy support for the green part of green AI. It's actually a difficult moment from that perspective. So, and I think part of that is related to part of that is related to this affordability question and concerns about cost. So where does that bring us back? If we bring back to the point of this conference and what are the opportunities and what are the potentials, I think it comes back to the challenge of trying to figure out a way that we can do all 4 of those things. We can do the growth, we can do the affordability, we can do the reliability, and we can do the green. How can we do all 4 of those at the same time? So instead of thinking about those as a trade-off, some cases they are a trade-off, are the places that we can double down and they're not a trade-off. We can actually do them all at once. And I think there are options. That's not going to happen everywhere, but there are places that it can. It can happen in the case of electric vehicles. Electric vehicles are getting cheaper and cheaper and cheaper. And if we solve some of the problems of charging and so forth, that's a win-win for the climate, and it's going to be a win-win for affordability, and it's going to be a win-win for, the reliability. Well, it's going to be a win-win if we can get those chargers out there and the chargers working. That's an AI problem, by the way. It's partly a people problem, partly a politics problem, but it's partly an AI problem. So let's get the chargers working. And another place that it can be a win-win is in the grid. So if we can really use AI to solve some of the problems with grid congestion, think about smart ways to shorten the interconnection queue, that's going to allow us to bring more solar online and have smart ways to do that. And I say Leji sitting over here, and he's going to talk much more intelligently than I'm able to about some of those opportunities. Those are places, really big places where there's a lot of potential money to be made. I mean, EVs, like cars, it's a really big market. Power, that's a really big market. There's a lot of opportunities for entrepreneurs and for engineers and for policy people and for businesses to go out there and really make hay and achieve all of these 4 different objectives. So this is really an exciting opportunity to double down and focus on some of the places where we can do all of these things at once. I think just to give one more thing, that we've had 2 of the speakers talk about the double-edged sword. AI can be used to improve reliability of EV charging stations. It can be used to improve interconnection queues on the grid. It can be used to come up with better imaging for finding fossil fuel deposits. It can be used for faster, better ways to do fracking so that you can guide so it's a question of how we use it. It's a question of how we use it. And I hope that everybody here is excited about using it in a really constructive way to hit these 4 goals all at the same time. So thank you so much, and I look forward to a great conference.
Thank you, Vice Provost Stock. I now have the pleasure of introducing David Havlicek, the Associate Director of the Harvard Office for Sustainability, as well as Sarah Craig, the Senior Director of IT Operations here at Harvard University. Please join me in welcoming the pair.
Great. So I'm David Havlicek. I work in the Office for Sustainability. So as Vice Provost Stock works at the Salata Institute, works on research and teaching, learning, engagement with students. Our office works more on how the campus is run and the decision-making about how we're running our campus and how we can be moving sustainability forward as we do that work. And Sarah and I are here representing the Sustainable IT Committee here at Harvard, which is a group of staff across the university, and Sarah will get into that a bit. But I just want to kind of frame and contextualize what our sustainable IT work looks like in the bigger Harvard sustainability strategy, again, with how we operate our campus. So Harvard has long recognized climate change as a defining challenge of our time. We met our first climate goal, which was set in 2008 and achieved in 2016 to reduce our absolute greenhouse gas emissions, again, on our campus for scope 1 and 2 emissions by 30%. And then building on that, meeting that first goal, a faculty-led presidential committee set new goals for Harvard in 2018 to be fossil fuel free by 2050 and fossil fuel neutral by 2026. We've also, since 2014, had a university-wide sustainability action plan. So trying to do more than just this climate work. And so in the work we do, we're really trying to pilot and prove new solutions and systems here at Harvard to accelerate that happening more broadly. So in addition to our climate goals for scope 1 and 2 emissions, we also have a focus on tracking and reducing our scope 3 emissions. So these are emissions from our value chain. And we have specific targets for embodied carbon in capital projects and buildings and food, but we're also really focused on understanding some other categories like IT products and services. And as you've heard, IT and AI can play a dual role in this work as both a key enabler of sustainability, as you heard some examples, especially from Vice Provost Stock just now, but also as an area with its own environmental impact. So IT as part of a solution can look like smart building systems and automation, lots of examples of that on Harvard's campus, but also AI and IT as part of the problem, causing all these emissions and things like that. So at Harvard, we really strive to walk the talk. We work closely with faculty, researchers, and students to ground our operational decisions in the latest science and best practices. And this partnership between knowledge and practice comes to life through Harvard's Living Lab model, where the campus becomes a testing ground for sustainability innovation, piloting things, learning things from that, and then sharing that out with the rest of the world and accelerating this work. This model of experimentation and implementation is central to how we embed sustainability across Harvard's operations, in how we power and how we build and how we operate and how we lead. And a powerful example of this is the evolving work of our Sustainable IT Committee, again, that Sarah and I co-chair, which today serves as a catalyst and coordination hub for driving change across Harvard's decentralized IT ecosystem. So now I'm going to turn it over to Sarah from Harvard IT to share how that committee is accelerating this work.
Thanks, David. I'm Sarah Craig. I'm the Senior Director of IT Operations at Harvard IT. And I'm excited to talk to you about what we can do on the local level here to make improvements in this area. The Sustainable IT Committee has been active for nearly 2 decades on campus with the goal of helping us develop resources, policies, and best practices to really move the needle on sustainable IT across Harvard. The committee is comprised of representatives from across the schools and units, and it reports up to Harvard's CIO Council, which is led by Clara Jelenkova. And I just wanted to highlight some of the key accomplishments that we've worked on over the past. We've helped to secure Harvard's involvement in the Massachusetts Green High Performance Computing Center, MGHPCC, as it's more well known for. It's a shared high performance computing facility. It's located in Holyoke, Massachusetts, and several of the universities in this area, including Harvard, BU, MIT, Northeastern, UMass, and Yale are all using this facility. And as you can imagine, this enables significant computing energy efficiencies and also opportunities for us to collaborate with our peers. We also, as part of the Sustainable IT Committee, published sustainable IT standards back in 2017 that we've continued to iterate on. And those are really focused on developing sustainable IT best practices, reducing waste, and focusing in on how we can better consume energy. Lastly, we supported the launch of managed print services here on campus. And that's, for those who are at Harvard, is known as the Crimson Print. So that initiative started with a sustainable IT group that piloted it locally. And that helps to reduce energy consumption and e-waste, which has been a topic mentioned several times already. And in this past year, we've really ramped up the work that we're doing in this area, and we're focused now on 3 main priorities. We are developing a university-wide e-waste best practice and resource guide to help folks know what vendors to use and the processes for how to securely and ethically dispose of electronic waste. We're also standardizing our approach for how we engage IT vendors in this space, which is a significant way to make progress. And lastly, we're defining and collecting data on IT-related greenhouse gas emissions so that we can begin to measure and really strategically reduce them. And in 2024, the university demonstrated our commitment to helping to advance sustainable IT practices by creating a brand new role. It's a dedicated business analyst and sustainable IT lead. This role is it's now held by Jack Sawyer. Some folks know him. He's in the back here. And he is helping to ensure continued momentum in this space, driving the goals of the Sustainable IT Committee, but really building systems and structures across the university that are helping us keep on target for our goals. And I think this reflects Harvard's belief that sustainable IT, it's not just an opportunity for us, it's our responsibility for now and in the future. Thank you so much.
Thank you, Sarah, and thank you, David. I now have the pleasure of introducing Jerry Wang, the founder and president of the Green AI Institute, and who will be launching our white paper on global data centers, citing policy and practice. Please welcome Jerry.
Next slide, please. Good morning, everybody. I'm Jerry. I'm the president of Harvard Undergraduate AI and Sustainability Group. And now we're expanding this to a bigger group called Green AI Institute. Before I deliver my speech today, I just want to say a big thank you for all the supporters of this event. First, we'd like to extend our gratitude to Slada Institute, OFS, HUIT, the Weatherhead Center, CID, and HUA. And we're very grateful for our co-host on the other side of the Charles River from Boston University. Yeah, on the other side of the on the other side of the Charles River, Boston University, especially for Professor Aisha Koskun for her support from the Boston University Center for Information and System Engineering. And today, we have a great opportunity to hear our previous 5 speakers talking about their amazing understanding of this topic. And today, I also want to first deliver my gratitude to all the speakers that is flying from California, flying from China, flying from, a lot of places all around the world. So today, I'll spend the next 15 minutes to talk about how we, the younger generation, are doing actions and how we can make some changes from our end, and how we can leverage our energy and our time to collaborate with our speakers and everybody here. So with a vision, I believe many of you guys have heard from our previous speeches, we're in the critical conjunction between the advancement of AI technology, but meanwhile, we are having a bigger issue with the surging energy usage and the climate change goals. For us, our mission is to unite people from academia, industry, and policymakers to develop greener and more equitable AI. For our history, we're very lucky to go to the COP28, where I met a lot of like-minded people in this field. And with the support from the CSSL program at the Harvard OFS and being incubated at Harvard Innovation Labs, we're able to convene a bigger group. And last year, I also want to deliver thanks to our first Green AI Summit participants, where we have convened in Science Center, and then we kicked this off last October. We have launched many journals, white papers, which I'll give a detailed introduction, and how we have come today. And before that, I also want to express our gratitude to a lot of people in the Green AI communities. For almost every Tuesday in Leverett House, we're hosting seminars and hosting people from all across the world, including Professor Le Xie, who will be giving a talk later today, Professor Wang from Singapore, and Goda, who is from UK. For us, we plan to carry this out through a collection of activities. First, we'd like to carry out more intellectual properties, more white papers that can make it more accessible to people who are not familiar with this topic, to get to know the environmental impact of the AI, which we launched last October, and the white paper on global data center siting policies, which we will present today. We also want to convene people with the summit, where people can talk from different backgrounds. And we also have an open access journal, AI and Sustainability, where different companies are uploading their digital sustainability practices. And also, we extend our welcome to the younger generations. And it's not just the college students. We also make it available for high school and younger students to do this competition for them to see how they can implement digital sustainability in their own platform. So last year, we're very lucky to have the first one, where many of them are showing up today as well. And thanks for continuous support. We have over 1,000 views on YouTube and 14,000 people who saw our website during those few days. For us, we launched this white paper last year. I just want to do a quick introduction for our newcomers today. Last October, we have summarized the policies in different areas, including the United States, EU, and China, to see what different layers of policies have been impacting the different companies' practices with Green AI. It is not just the mere energy efficiency standards. It also accounts with renewable energy usage, carbon emission reduction, water usage, waste management, e-waste, EIA, information assessment, and transparency. We have worked with many international organizations, including the ones we have invited, to carry out a more standardization work. One, when it comes to scope 1, 2, 3 with carbon and water with data centers, and we also leverage the LCA methodologies to carry out that for the AI models. All of these are online with a barcode, so please feel free to scan it, and there's more information. And later today at 4 p.m., our team will give a detailed introduction of the information we have here. And for us, for people who are new to this topic, the data center has multiple implications on the environment. There's scope 1, the direct emission, scope 2, indirect carbon emissions and water footprint, and scope 3, which is the things on the supply chain and the value chain. We have summarized all this information in our white papers, and we also have a few copies today in person. So if you see anybody with the blue badges, we are the staff and organizers of this event, and you can also welcome to take a look at those physical copies. We've also carried out lifecycle assessment of many AI models, but in Frank, all this methodology can't happen without actual data. So we will later announce today that we will also hope to form more industry partnership to work with companies across the world to build this together. And today, we're also launching our second global data center siting policy and practices. As our keynote speakers has mentioned beforehand, there has been $1 trillion level investment over the past few years and in the foreseeable future into this industry. And for us, there are so many factors to be considered. And that's why today, we will not go through the details, but I'd like to connect our white paper with our agenda today. Today and tomorrow. So today we'll be here in Harvard and tomorrow at BU. We have formed over 7 panels, including people from industry companies like Oracle, IBM, and Meta. And we also have people from other sides of the Pacific Ocean, including Tencent and Alibaba. Meanwhile, we also connected, policymakers, as you have seen beforehand. And also we have people joining us from the EU. Thirdly, we have so many faculty members from different disciplines: economics, computer science, electrical engineering. For us, we're exploring different layers when it comes to the data center's impact. It is not just a technical problem when it comes to site selection and construction process. It is also multidisciplinary with so many implications on the economic and government incentives. And right now, we have seen a shift into this much more energy-intensive, AI-centric, and renewable-powered hyperscalers. For us, we have looked into many of the debates here into this book, including the ones we have from last summit, renewable versus nuclear. And we've also dived into the geopolitics here. So all of them are in the barcode, and please feel free to scan us. And meanwhile, we've also looked into many interesting states. Apart from the traditional host for data centers in Virginia and Texas, there has also been a shift in many policies in new areas, such as Ohio, California, and Arizona. And to make sure we can make this a continuous project, we'd also want to partner with many, many other organizations. You can see many posters here today in the room and outside that we are officially launching our environmental science and ecotechnology special issues with Green AI, with our managing guest editor, Professor Gopa from BU, and Shaolei Ren from UC Riverside, Shren Goda from Nottingham, and many other members to join. And you can also find a physical copy of this, of our previous ESE journal at our entrance table. You can also talk to people with a blue badge. Meanwhile, we noticed that this is not just an academic project. Things happen in academia, but right now, the translation to business, translation to policy makings are getting more and more challenging, given the fast-moving nature of AI and green. So we also launched this open access journal with AI and sustainability, which later today we'll be going through more in details at 4 o'clock. So eventually, I want to call for actions, because yesterday when I was chatting with my colleagues, we were just talking that in the AI, you have the mix of expert network. So many people, so many agents in the AI models have different kind of functions with their background. And I was chatting with my colleague from Green AI. We were like, what if we convene people in this room to make it a super GPT with this mix of experts? What would that be? What kind of powerful things can we do? So today, we'd love to welcome all of you guys to join us as members and many other capacities. We have a lot of interesting opportunities to have existing relationship with companies. Many companies, they're exploring new topics. And here we do have over 50 PhD, master's, college students with different kinds of backgrounds in their pocket. And meanwhile, with volunteers, we also have so many people here today. We have over 30 volunteers today joining us from Lexington, from BU, from Tufts. And we have a lot of opportunities, as I mentioned, to host weekly meetings. And honestly, every Tuesday, 7 p.m. at Lever House, we have meetings every week to plan for the conference, plan for the white papers, and many other initiatives. And since our first summit last year, we have so many new chapters set up. Previously, we've got Stanford, Virginia Tech, and recently, we got people inquiring us from university in Korea, from university in Zimbabwe, And we have seen this growing trend where people from all over the world, they are not just using AI, they're becoming more aware of the environmental impact. And many people with different backgrounds, we're working on that together. And also to our industry people here today who is coming from companies or research institutions, we'd also love to forge more partnerships. And with many data centers and many AI companies, I know you guys have many talents in your pocket, but the questions we're facing right now seems to be far more than the people we have. So we'd love to form this relationship to help our industry partners for us to utilize those non-confidential data to do more analysis. Some of them can go to publications, some of them can go to our case bank, and some of them can be presented in our Green AI Summit. So eventually, I want to say that over the course of the past 2 years, we're very lucky to have the leverage to be here at Harvard, to enjoying this amazing pool of resources from our fellows, our faculty members, our students. And we're also very lucky that this is not just a consensus of us 20 people and 30 people. This has extended to a bigger group. And today, we have people here in person in Cambridge, but we're also very lucky to have the whole YouTube streaming, and people from all over the world are asking us on LinkedIn about the real-time questions. So as a summary, we utilize white paper as a platform to formulate our opinions and to educate the public. We use the summit to convene the people's mind. We use the journal to make it an open access platform. We make the challenge to even stimulate younger people. And we offer opportunities to our members, our sponsors, to set up more chapters and to form more industry partners. So in the end, we are a mission-oriented organization to build greener and more equitable AI for sustainable development through efforts connecting the industry, academia, and policymakers. We have our Green AI Index to quantify, Green AI Institute to go across different campuses, Green AI chapters to do things locally. And we use Green AI Summit to bring us together, and all of us are forming this Green AI community. So yeah, without further ado, I just want to say again, a big thank you to everybody who has supported us in this conference. And as I said, we'd love to stay in touch with you. We'd love to build this mix of expert analogy. We'd love to leverage your impact for the upcoming 2 days and for the future. Thank you very much.
Thank you, Jerry. We'll now like to proceed with a short break, so please feel free to make your way out to the foyer or remain in your seats. And please make sure to make your way back here for a prompt start at 10:20 for our first panel of the day. Thank you. But I also noticed it was great. Like I opened it up, all good. That's separate. Oh, it worked out smoothly, right? It was. Okay. Well, I do mention that in understand that, but I'm saying that. With it, well, I guess it's like, sorry. But that's, I think, a secondary considering so you know, this is really dates they have with But it's very cool, you know, like all things driven by, you know, motivation and awesome people. So a lot of those suggestions stuff. I said, like that suggestion. And it would be also, you know, have some of this like very real stuff that you guys are doing. Yes, such. Yeah. Next to brain, like, how about we do this course? I don't know what that's about them, but you no, it's me. Can I share? Okay. That's right. Hello, everyone. If you could please make your way back to your seats, we'll be starting the panel in around 2 minutes. Thank you.
So let's get started. Welcome to the Green AI Summit. My name is Le Xie. I'm a professor in electrical engineering at Harvard John Paulson School of Engineering and Applied Sciences. I came here last August. When I came here, I was told by my dean in a joking way that I'm the first power system hire that Harvard has ever made in her 380 years of history. So don't screw it up. So no pressure. So, but I'm very, very honored and pleased to moderate this session today, focusing on data center AI energy usage and environmental impact. We have a star lineup of panelists. We'll invite them all together to come to the podium. KJ Joshi from Hitachi, Carol Jing Wu from Meta, Noman Bishar from MIT, and Jiaqi who will be joining from Zoom. So please have a seat. Now, what's the best way we can, no particular order, just have a seat. Yeah. 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 So we have about 15 minutes. So the plan is that we're going to kind of have a bit of a conversation within the panelists, and then we'll open up for some Q&A with the audience. I think as the Vice Provost Stock mentioned in his opening remarks, when it comes to green AI, we're really juggling with some multiple objective functions, and some of them are not necessarily very well aligned with each other, which is we want to keep the growth, we want to have the energy that is very affordable, we want to also have the grid that's very reliable, and in the meantime, we want to keep the growth of the AI. To me, that's a daunting task, but it's also a once in a generation opportunity. And we have a lot of very bright students and researchers out here. So maybe we'll first sort of start by just asking each one of you a very quick question, which is, what are among all the sort of news coverage about this huge growing energy demand and so on across data centers, what are some of the sort of perhaps energy/environmental impact that has sort of a relatively less covered and characterized? And if you may share with us some of these insights, we'll start from maybe KJ.
Thank you very much for having me. First of all, quick introduction about myself. I'm KJ Joshi, Chief Business Officer at Hitachi. Hitachi is actually the second or third largest company, depending on the market cap in Japan. They are very large operators of data centers, nuclear power, rails, and very diversified conglomerate, about 60 billion in revenue. So I'm pleasure to be here. I spent the last 23 years in the data center industry, so I'm happy to talk a little bit about more broadly the transition that the data center industry is going through. And just to answer this question, that what are we really grappling with? It's two things, and I know it's been talked about a lot, but water usage, that's the first area where we are seeing significant impact. Some of the data centers take up to about 500,000 gallons of water a day if they're using water as a cooling technology. So when you're building these massive data centers, you're talking about significant water usage. I think the other area that's not been talked about a lot is the rare earth minerals that go into making these AI chips. And I mean, all the discussions around Greenland, I won't get into the political debate here, or Ukraine. It's actually about rare earth minerals. To be honest, that really drives a lot of the motives behind all the saber rattling, and I'll leave it at that. But I think it is really important to understand that having control of these rare earth minerals will be a huge differentiator. But at the same time, when you're digging up all this and mining them, and there's an environmental impact there. So I'll leave it at that. But thank you.
Yeah, let me introduce myself first. My name is Carol. I'm currently a director at Fundamental AI Research Group at Meta Platforms. I'm a computer architect at training. And so with that background, I guess I've been looking at energy efficiency optimization for quite a while. To Larry's questions on what do I see as the most important and new directions that we must pay attention to for AI sustainability is, I think, efficiency optimization we should continue to do, especially for the use phase of AI data centers, for example. But the less explored aspect of computing sustainability implication is embodied carbon. And this is basically all the greenhouse gas emissions that's produced during the manufacturing phase of hardware in general. And these can be AI hardware or all the peripherals that we put into data centers itself. And I hope to sort of put this on your radar. And I'm happy to elaborate more on this particular aspect.
Hi, I'm Noman. I am the Computing and Climate Impact Fellow at MIT Climate and Sustainability Consortium. I'm a computer systems person with background in electrical engineering. So my work focuses on how can we change how we design and operate data centers and computer systems to make them more sustainable. And I think there are a few things that are not at the forefront in this debate about sustainability of AI or green AI. First one is that that there is a difference between energy and power. So energy is the total consumption, but power is the instantaneous rate, and they pose very, very different problems. So data centers, especially AI data centers, are a lot more power intensive, and they have a lot more power fluctuations, which are impacting the reliability of the grid. Also, the fluctuations are impacting even like there has been some recent research on that they are impacting the lifetime of household appliances for homes that are near the data centers. Also, integrating more data centers and new power increases the electricity cost for the ratepayers in the neighboring communities. So there are these issues that are not at the forefront, but probably they should be considered as important as the problems of energy consumption, carbon footprint, and water use.
Let's also move on to the Zoom participant, Jiaqi, who is heading the data center of Tencent. And that's a huge operation. So Jiaqi, can you tell us a little about some of the key challenges you see that has perhaps not so covered yet?
Okay. Can you hear me well? Okay. All right. So before that, just one quick fun fact. My wife is actually currently studying Harvard THN graduate school. So I'm also part of the alumni network. And also, I want to introduce just a little bit about Tencent, just in case you folks don't know. So Tencent, we're one of the largest social media, gaming, cloud, and probably the future AI company in the world. And we have roughly about 100 billion US dollar revenue last year. Globally, we have more than about 100 data centers in the world, and we have about more than probably 2 gigawatts of IT capacity in plan. So I manage the data center operation team, including the planning, construction, energy, and ESG side. In 2022, we released our carbon neutrality goal that we will be net carbon zero by end of 2030. So that's a pretty aggressive carbon emission goal, especially in China. So this is basically the brief overview of where I came from. To your question, I think we mentioned a little bit before, but water is definitely one key aspects that we are missing. In some of the key places in China, for those data centers, water is a big consumption. Water is a big consideration because sometimes we don't have enough water for the cooling side. And also land is also a big consideration because in China, data center construction is regulated by a government. So the government provided us a couple hotspots that they will allow us to build data centers in those areas. They don't allow us to choose freely because that will be more efficient. So in that case, land is also a very important consideration for that. The third one is also the embodied energy. I think one of the panelists has mentioned. We also need to consider that because of the Scope 3 commitment. We need to understand what's embedded energy, including steel, cement, all those kind of building materials. I think that's pretty much the missing areas.
Excellent. Thank you. I think we have identified some common issues, which is great. Maybe let's sort of zoom in a little bit to each of these aspects. KJ, you mentioned about this issue of water as well as Jiaqi. So let's sort of perhaps zooming a little bit into this issue of specifically water, but also more broadly speaking, infrastructure access. And Hitachi is very well sort of suited in sort of an energy infrastructure and solution provider perspective. What you know, when you see this growing demand for building more data center and you see this gap of, oh, I don't have access to water or power, what are the things that you guys are doing to accelerate that barrier from the technology perspective? And then perhaps you can also relate to the market and business perspective.
Yeah, so thank you for the question. I think it's a really good question. And it's not just Hitachi. All across the industry, there's a lot of innovation, one going around waterless cooling. So when you're looking at liquid cooling is actually not using water. It's waterless cooling. It's a new technology. It uses certain types of chemicals which act as coolants. But you still need to dissipate that heat somewhere. What you're doing is you're basically transferring that heat from point A to point B. And once that coolant actually absorbs the heat, you need to dissipate it somewhere. You definitely don't want to dissipate it in the air, given all the considerations around how hot the climate is getting. So we are looking at finding ways to redistribute that heat for either heating homes or heating swimming pools, and really how we use that heat that the data centers are generating. So that's an area where we are putting in significant amount of research. Second, I mentioned waterless cooling technology. Specifically, there are 3 areas, and I'm going to touch on that in the afternoon, where I'm going to talk about direct-to-chip cooling, and then immersion cooling. And the third area is what we call a coolant distribution and based cooling, where we are taking the heat away from the servers to, into a different area. So those are areas where we are making significant investments. We are also looking at how we can also, so heating and cooling is definitely one area, but on the electrical side, there's a pretty significant transition from moving from AC to DC, because there's a lot less loss when you actually use DC power. And again, I'm an electrical engineer by training. I wasn't smart enough to go to Harvard. I went across to the other small university at MIT. So, but it's a little geek talk, but AC versus DC. DC is actually a lot more efficient, and you will start to see a pretty big trend that moves a lot of the data center equipment on DC platform. And that's the other area that you're going to start to see significant investment. So any of those electrical engineers, learn, how to make DC equipment.
That's music in my ear. I love talking about this DC and AC stuff. But that's great. So you identify, this is a, I was able to relate some of my personal experience. I went over to tour one of the biggest crypto mining facility in the world down in Texas. That's my prior life to here. And I'm just amazed by this, oil immersed cooling. I mean, that's just incredible. So actually definitely see a lot of opportunities over there. And also I was talking to one of the MIT professors on Monday evening. He's a big shot, and he said, "Oh, my next startup will be on air conditioning." So that kind of relates to, I guess, your comments on this aspect. And following that, maybe let's move on a little bit more into the inside view of data center. Maybe to Carol, these electrical engineers try to do everything more efficient from the electrical circuit point of view. As a computer system person, how are you kind of driving the innovation and research within Meta to just make the computing itself more efficient, and perhaps not only more efficient, but more kind of dancing together with the grid?
Yeah. So this is what I would like to share here, and this is our green AI journey within Meta. I would say around 2020-ish, there was a lot of conversations externally about what is the carbon impact of AI. And a lot of studies were just looking at open source models or based on paper publications. A couple of us were very curious about what exactly is the energy consumption coming from for AI model training in a more industrial setting. And so that's how we got started, is before guesstimating, let's just instrument our training workflow from the very beginning, all the way from data curation, model training to inference serving. And let's take a look at where energy is being spent let's take a look at if we were going to characterize carbon impact of AI, what is the biggest bottleneck that we must focus on? Subsequently, we share our findings in the Sustainable AI paper that we published in MLSIS 2022, where what we found is that actually, if you look at some of our production models, the amount of carbon emissions from training and inference, they are equally important. So if you are really looking at places to reducing carbon impact of AI, we must focus on making both training and inference to be more efficient. What's even more interesting is this aspect of embodied carbon. As a computer system designer, I think often we look at optimizing the use phase of computer systems. But what we often do not think about is all the additional energy consumptions or carbon emissions that get produced during the manufacturing phase for these hardware. And so in our Chasing Carbon paper, we basically did a data-driven analysis to just talk about how much carbon emission or greenhouse gas emission is coming from manufacturing side of computer systems. And that sort of is our hope to guide the communities about what to focus our optimization efforts on. Ever since then, I guess with collaboration with Harvard and Arizona State, we started looking at how to quantify embodied carbon, how to build the very first architectural carbon modeling tool such that we can have a data-driven way for assessing manufacturing emissions for all the hardwares that we put into Meta's data center. We talk about a lot of our findings in Meta's sustainability report. So that's like the first phase, is to be able to model. Then there's a second phase, is once we have the tool, we have the quantification results, how do we optimize manufacturing emissions? How do we think about the trade-off between embodied carbon and operational carbon? I would say this is more in a research phase. And so we have active collaboration with folks at Harvard to just look at how to even think about this design space in general, and how should we think about reducing embodied carbon for computer system design. I believe there is a panel discussion in the afternoon that will just focus on this particular topic.
Excellent. This is fascinating. I'm going to sort of trace the train of thought also next to Jiaqi. So I guess Tencent is operating perhaps similar or even a little bit more data center than Meta. I don't know. You guys can compete. But you're sort of thinking from a more broader global perspective, I guess, or different geographical areas. Meta's data center is probably more focused in the North America, where Tencent's data center are probably more located in Asia. Can you sort of comment on hearing some of the comments here from the North America? What are the sort of research or technical challenges and barriers that Tencent is thinking about internally as far as the data center is concerned, especially from the computing side?
All right. So actually, I think don't want to compare the size. Definitely, we have a different geographical focus compared to Meta. I think so in China, we have a little bit different grid system compared to US. In China, the grid here is a little bit more resilient, I would say. I used to work in AWS, so I can see the differences. So that's one thing. Another thing is renewable power, the cost of renewable power. I think that's a little bit different. So in China, we have very, very strong industry for renewable energy production, including wind and solar. You know, if you don't look at the tariff, if you just look at the cost here for renewable power for wind and solar, it's very, very cheap compared to coal. So right now, I think our advantage is we start using more and more renewable energy power data center with lower cost. I think definitely that is one of the main difference. So another thing I'm concerning is the scale. The scale is also a concern. So right now we're building very large AI clusters in China. As we can see in the news, like Meta XAI, they built like 100,000 GPU H100, and they are probably building another 200,000 GPU card. So right now we are building a very massive scale data centers as well for AI training. But that's one concern. So one concern is, are we going to continue building larger and larger data centers in the future? Or let's say we have models like DeepSeek or some other models that can use more, like less energy intensive way to build our training model. So that is definitely one concern for building massive data centers here in China. Another thing is inferencing. So right now, after we have very large training model, we need to build a lot of inferencing clusters. Those are probably a little smaller clusters with higher latency requirement. So how are we going to build that inferencing clusters in the very populated place with also massive scale? That's another big consideration we're having right now.
Yeah, I'm happy to address that because that's a topic that's really near and dear to us as Hitachi as a company. And we are making significant investments in what we are calling small format data centers, and especially focused on inferencing. As power is becoming very hard to find, what we are building is a 1 megawatt. Now, again, a megawatt is a lot, but in terms of data centers, actually not. And we are designing a modular system which supports 1 megawatt data centers that could be put in a parking lot. And you could essentially run your inferencing workloads in any part of the world, especially those that are either latency sensitive or they have some sort of sovereignty or privacy angle for which you cannot transfer the data over to a cloud or any other sovereign workloads. So we are very focused on developing what we are calling edge data centers, so which are small format, 3 distinct modular systems. So it's not a container data center because container data centers is like it's on a 40-foot container. But this is really 3 modules: the IT module, the cooling module, and the electrical module with generators, and all 3 distinct systems in less than 10,000 square foot format. So that's one of the areas I'm happy to talk about at some point. So thank you.
Yeah, excellent. This is a very interesting perspective on the architecture of data centers. I think a very, very prevailing discussion right now is, are we going to go for a few, hyperscaler, or are we in this sort of a smaller sized, but much more dispersed data center? And there's implications on the resiliency as well. I'm a power system engineer, so when I think about this distributed solution, I always feel like that's a little bit more, resilient when something fails. And that's something I think Norman touched upon in his remarks, which is it's not only about energy, but also about power. And Norman, you have been doing a lot of innovative work on sort of advancing machine learning views and machine learning approaches to addressing this power bottleneck. Can you kind of talk a little bit about what you're working on, especially from utilizing AI machine learning as part of the solution of relieving the bottleneck?
Yes, definitely. So one thing about, so if you look like at more historically, there has always been this push and pull between like centralized versus distributed. Initially, like power systems and small power plants were there. Then we went towards like economies of scale, big power plants and so on. But moving energy is much more costly and inefficient than moving data. So probably the next frontier is going to be like more distributed solutions for data centers. And at that scale, you have to consider how they integrate with the grid. And I think more recently, there has been a lot of like work in electrical engineering and power systems on microgrids and virtual power plants and so on. That is where maybe you have these distributed set of like smaller micro data centers, which are strategically placed within a grid. And then you control them in an aggregate manner at the like at a higher like virtual level. And also, I think one key frontier is going to be on that you don't simply optimize systems individually. So you are not trying to optimize data centers and power grid separately. And then also like the buildings and transportation, as our society is becoming more and more electrified, there are these interdependencies between different sectors, which can pose problems, but as well as like potential solutions to optimizing the system of systems where you get more benefits than like siloed optimization in individual fields. So that is where I think the next like set of research is going to be, specifically when it comes to like these micro data centers that are distributed within the grid.
Great. So we spent some time talking about the technology front on energy and environmental issues. I want to kind of also spend some time talking about the other part, which is also important. That is the business and the regulatory part. Maybe I'll just, if you can each reflect upon what are some, I mean, I guess in principle, we all agree that green is a good thing, right? But you also have, business or bottom lines and so on, and stakeholders. How do you see the barrier of moving this forward, that really trying to harness the growth of AI together with this green, mostly from the business and sort of a regulatory perspective? You can start with.
Yeah, I mean, I think certainly today everybody's more shareholder driven than stakeholder driven. I've made this statement in the past, where when everybody looks at a 700, 800% growth in NVIDIA stock and all the data center companies related stock, including ours, again, not to be, I think truly speaking, a lot of focus has been on the green Benjamins than the real green, initiatives. And I think we do need to be very responsible today. Movements like NIMBY, I don't know if you're familiar with NIMBY, especially is not in my backyard, it stands for. A lot of people in Virginia are basically totally against having data centers in their backyards. Nobody wants to get up in the morning and smell diesel generators, right? So I think the backlash is coming, especially not just from a pure environmental point of view, but also the impact it has on societies, on people. And I think we need to be very proactive. The industry, we need to be proactive from participation in these kind of initiatives. This is why I'm here, because we as a business need to do more, and not just in terms of making better products and better services that are greener, but also making people aware of what we are trying to do, and on the same side, understanding concerns and issues that the society is facing, so that we are being more receptive to it, right? So I think certainly this is an effort that's on our side as a company, that we are making a lot of conscious effort in understanding what are the societal issues, because we don't want somebody to be saying, hey, I don't want a data center in my backyard. That's just not something, because we need that. It's an essential service. It's like a utility, but nobody wants a nuclear reactor in their backyard, right? Same thing. So I think just thinking through those issues and being proactive about it, and then working with the local governments, working with the educational institutions and organizations such as Green AI is very, very important for us.
Yeah, maybe there is the aspect of business, and there is the aspect of societal responsibility. Perhaps I can give some examples about how to align sustainability with business motivations. And the particular application use case that I'll share to your earlier points, Lei, about interaction between grid and data center is that if you look at renewable energy generation in the world, there is actually a pretty significant portion of renewables that is curtailed. It is underutilized, and the grid is congested, not ready to sort of deliver the power to where the usage is needed. And I felt like that is a potential win-win situation for power consumers. If we can predict where these curtailed renewable energies is going to happen, then it will help the management of power consumptions and power generations to unlock that additional utilization. And so obviously it's a very complex resource management problems. And this is where I felt like AI can play a pretty significant role, is to just predict emission factors of power grid and use that signal to decide how to shift either compute or transmit energy to where the usage is most needed. And this is like a win-win situation for sustainability as well as cost or business use case, right? In addition to that, but this is not something that we can do easily today, because first, it's a hard prediction problem, and also we may not have all the grid capabilities or data center system capabilities to do that matching as flexibly and as easily that we would like. So that's one. Second thing that I would like to highlight is going back to embodied carbon. So if you think about where most of the IT hardware is being manufactured today, a lot of that is happening in Asia. And we also know that depending on where the manufacturing is happening, renewable may not be, readily available. So what Meta is doing today is to work with our suppliers to help them identify renewable energy sources and help them to adopt greener practices such that the embodied carbon that Meta will be adopted by procuring these IT hardware into our data centers is going to be as low as possible. So these are like some of the examples of things that Meta is doing that is on business incentive side of things, but also on the sustainability responsibility side of things.
Excellent. So, and university has a role to play there too.
Certainly.
We will be the convening place where the grid operators and companies like yours can meet and discuss.
Yep.
Sorry. So I think one thing that I would like to highlight is about there is some like limitation in understanding of how actually grid works, in a sense that people think of it as a big pool where everyone is just putting energy and anyone can take it, but it's not like that. Even if you have renewable energy power plant on the same grid, it doesn't mean that it is directly connected to your data center. And while there has been a lot of push for renewable energy by tech companies, and that has incentivized more renewable energy, but increasingly adding more renewable energy is going to be hard. And even if there is extra energy available somewhere, it doesn't mean it would transmit to your data center easily. So and grid would need to manage and match supply and demand at all the locations within the grid, which becomes very, very hard as more renewable energy is integrated into the grid. So these are the challenges where I think how we operate our infrastructure, not only data centers, but even our residential buildings and other, let's say, transportation must change. Because currently data centers are built with this reliability abstraction that they have unlimited power supply. And moving forward, they would need to respond to these demands from the grid. Right now, there is no kind of demand response or incentive structure that can make them do that, because the downtime for a data center can cost like 1 minute downtime can cost like 10,000 to hundreds and thousands of dollars, because there is massive infrastructure cost for GPUs and so on. So in this case, there is no monetary incentive, so there needs to be some kind of regulatory or like policy initiatives that figure out what is the right set of like these interfaces between electric grid and data centers. And they will adopt based on the grid and the type of data centers, because not all the data centers are same and not all the grids are same. So I think there is significant, while I think there is technological innovations are there, we need to work with policy folks and make them understand the requirement and constraints of grids as well as data centers and figure out the right policy solutions moving forward.
Excellent.
Maybe I can jump in a little bit on this. So several years ago, when I gave a talk on sustainable AI, audience asked the questions, what is the role of policymakers and all that? And at the time, my response was, well, do we have the tools available to help us quantify, to instrument the workflow, to help us understand what we're talking about, energy consumptions, carbon characteristics, and all that? And I think accounting methodology plays a significant role here. To my knowledge, I think the GHG protocol committees is having a lot of conversations about what is the right methodology for accounting for scope 2, scope 3 emissions. And I think that needs to settle such that everybody, the important power consumers on the grid, will have a standardized accounting methodology that we can all use to understand what is the environmental impact of, in this particular case, data centers.
Right. Very well put. Yeah. And Jachi?
Yeah, I totally agree. Other speakers, one is incentive, and one is, we need some better models and data to help us drive very smart decisions. I just want to add one thing. Is that all is about cost and price. I'm very optimistic about the future, and I'm very optimistic about technology. So I do think actually when we spend more time and more effort into technology like renewable energy technology, we will definitely get a lower cost solution to power next generation AI data centers. Let me give you guys an example. Yesterday, I went to Ulaanbaatar. That's a city in Mongolia, in China. It's in the northern part of China. So it's there are a lot of data centers there. Those are one of the designated spot by government for building data centers, and they have massive wind power plant there in Ulaanbaatar in the city. I remember 4 years ago when I first came back to China. So the cost for the solar farm is about 6,000 yuan per kW. That is probably equal to $1,000 per kW for the total cost, including all the turbines and installation and everything. So $1,000 per kW in 2020. But right now, yesterday I was asking what's the price, and they told me it's already below 3,000 yuan per kW, which is equal to about $500 per kW. So that's half of the cost in just 4 years. So one interesting aspect is that so the renewable energy cost is decreasing so quickly, so that it became very competitive compared to just the traditional coal power plant. So it's very interesting that we used to have like the electricity price in the city powered by coal is very high, and with more and more wind farms and solar farms with lower emissions, so the electricity price start decreasing. And now the grid and the municipal government, they are encouraging data centers to build more solar and wind farms themselves to power the data centers directly. So that's kind of the lower cost and also the sustainable solution for the future. I think that's a very interesting example how we can find a sweet spot between the sustainability and also the business part of the decision making process.
Excellent. So there's optimism in the technology overall. Let's also open up for some Q&A with the audience. I know you guys have a lot of questions, so we start from there. Yeah. Is there a mic? Go ahead, give the mic. The panelists can. If you can just briefly introduce yourself.
I'm Nate. I'm an AI for Good researcher. Thank you for the whole panel. It's been very informative. My question is, so a common criticism that I've seen for the data center industry is that the hyperscalers have been maybe in some respects a little overzealous in the speed of their deployment and also the need, frankly, to build all these data centers in the first place. I've been kind of keeping tabs on the news articles. And for example, Microsoft tapped the brakes on their $1 billion Ohio data center plan. Amazon is pausing data center lease commitments as well. So I guess my overall question is, like, for the industry of data centers, like, do you see the backlash from communities and these problems that we've been discussing today kind of scaling in magnitude and the need to solve these problems and like just canceling like more projects in the future, just overall like industry trends? I'm really curious.
Hyperscalers, who wants to address that?
I'm not sure how much I can share on this particular aspect, but I can see how all of these is going to be driven by demand. So if we have efficiency breakthrough, for example, that's going to reduce demand, for example, and that is the reasonable thing to do. So while it is hard to predict the future, I think it's important that we take a look at the data and that the data to help us make informed decisions, right?
Yeah, so I'll certainly, I can answer to that. A couple of factors are driving it. Number one is actually availability of capital equipment. If you look at the wait time for a substation right now, it's about 5 years. If you look at UPS, it's 4 years. And nobody wants to start a project, have the land building done, but it's sitting empty because you don't have the capital equipment. So there is still a very big shortage of actual capital equipment availability. That's number one. I think the second factor that is driving is clearly availability of power. There's just not enough power there's no point in announcing a project and building something if there's no actual power available. So power availability is now actually 4 or 5 years. The grids are basically not committing to anything in the short term. Every deal that's being discussed is with a utility. Many of them are looking at having what is called a behind the meter solution, which is actually having your own power in your own backyard and a solution like a SMR, small modular reactor. Now getting an approval from EPA for an SMR is a 5, maybe 7-year endeavor. So there's a lot of external factors that when people announce these mega projects, you need to make sure that you're not sitting on a 500-acre parcel of land without all the capital equipment, the power, and any of the related supply. Like even GPUs are a big constraint. You cannot get GPUs. So don't read just the headline. Just see what's driving. What's behind that is basically a supply of everything else.
Let's have a very quick answer, and then we go to the next question.
Just one thing, not a hyperscaler person, but one thing I hope is that some of it is because people are realizing that a lot of these announcements and investment were based on the hype around AI, not the realized benefits. AI has a lot of potential, but the actual applications where it can make a meaningful change remain limited. So if companies are realizing that there is not a lot of business value in actual applications, maybe they are tracking back some investment. I hope that is the case, because that would mean all the AI capabilities that is there is being used for meaningful applications and not just like having just generative AI available.
Next question.
Great, thanks. So I'm Dr. Kimberly Samaha, an electrical engineer. I've been in the power business for 35 years. So all that you guys are saying is music to my ears. I guess the question that I've found over and over again, you've highlighted it, all of you, is that we still do technical, economic, policy. And how can you envision that we can get this thing to be more of a socio-techno-economic analysis? Because I really do feel like, just even this announcement that these things are going, because is it the backyard? Is it the technology? Is it the CapEx, the OpEx? What are some of your ideas in terms of how we can bring this thing together in a more integrated way?
Well, maybe I can say that we need to rethink about education. That's something we are actively working on, by the way. We have more things to announce later.
I think education and then collaboration between industry, academia. I think improving knowledge sharing, transparency and all that plays a pretty significant role here.
Back. He has been raising his hand. Yeah.
Hi, my name is Alex. I'm an MBA in quantitative economics student at BU. You were talking about the challenge of having enough renewable energy for data centers and one of the main issues with that is the energy generation is not happening where it's needed and nobody wants a nuclear power plant in their backyard. What innovations are you seeing to get that energy from where it's being generated to where it's being needed?
One, actually, people are moving closer to where the power generation is happening. So data centers used to be in tier one metros and, Boston, New York, Silicon Valley. They are moving to tier two, tier three locations. That's one big shift in the mindset. Go closer to where the power is getting generated or where you have sustainable sources. I think the second thing that I'm starting to see is that the small format, where people are not looking to do a gigawatt data center because it's very hard to find a gigawatt of power, but you can find 20 megawatts of power. So I think really thinking about the form factor is going to be a big driver also going forward.
In the interest of time, we have two last questions. Aisha, in the middle.
Thanks. Aisha Joshkun from Boston University. I wanted to ask, what are the biggest challenges towards going towards these more distributed network of smaller micro data centers? There are some companies around this idea, even containerized data centers, etc. But still, when we look at where the power is coming from, it's still mostly hyperscalers, right? So if you are going to move towards this, what are the couple of big things that we need to resolve? Thank you.
Dominate the conversation. Anybody else? So I think one is security. So certainly making sure that all these installations are secure. Second one is availability of, again, capital equipment. So finding small format. Most companies haven't made the right capital investments in designing and building these small format data centers. And third one is which we haven't talked about is networks. You still need to transfer data, and you need availability of fiber. And that is not actually the current infrastructure in fiber is actually very, very constrained. And it's a very expensive project. It costs about $1 million a mile to add new fiber. So it's very expensive. And one last thing, which I think we are trying to solve, is through satellites. So Amazon and Project Kuiper, or if you look at what Starlink is doing, is putting 6,000 satellites in space. That'll help.
Okay.
And if I may add one more thing to what KJ just mentioned is I think management and keeping all the compute as utilized as possible is much harder for distributed side of things.
That's an excellent research topic.
Yeah.
Last question.
All right. All right. Thank you for the opportunity. I'm a undergraduate research student in Rensselaer AI and Reasoning Lab. And I have a question about there are a few upcoming future ways of computations. For example, IBM's Quantum and also a company called Lamanauskas. They use Photon to compute. And Huawei also registered a new patent on three-value logic gate circuit. In terms of data centers, do you believe the future of computation will attribute to the data centers? And do you believe that future of computations will be a good bargain comes with ability rising and maybe there could be more energy cost?
You can ask Jachi online to say a few words, and Norman.
Actually, I don't know too much about quantum computing, but I do think that may be one promising technology in the future.
I would just add that based on my understanding, quantum is going to be focused on the problems that we cannot solve today and not general purpose computing. So probably the general purpose computing and GPUs and all of that is going to be there while quantum solves the problem that we cannot computationally solve today.
Thank you. So I think we certainly have covered a very wide ground, ranging from technology to business, or maybe we should call it social techno aspects. And a lot of food for thought. This is just only the beginning of the event. So I look forward to more discussions throughout the day. Let's give a big hand of applause to all the panelists.
Before we move to a quick break, I would like to invite all the speakers for the next 2 days to make their way to the front so our photographer can capture a group photo. Thank you.
Yeah, honestly,
Hello, if could everyone please kindly make their way back to their seats and we'll start the keynote speak in approximately 2 minutes. Welcome back, everyone. If you could please make your way back to your seats. We'll be getting straight back into the event by inviting Roger Zhaoyang Wang, who'll be delivering a keynote speak. Zhaoyang Wang is the General Manager of Alibaba Cloud's Global Data Center. Please join me in welcoming Roger Zhaoyang Wang. Thank you.
Good morning, everyone. Thanks for having me today. It's great to connect with all of you online at this Green AI Summit. Really inspiring to see so many people working towards a greener future. I'm Roger Wang from Alibaba Cloud, and I will be talking about AI plus sustainability, how they promote each other in AI era. So we will share our best practice and insights. As the backbone of our digital world, cloud computing infrastructure like data centers powers everything from AI to cloud computing, but they also come with energy and environmental challenges. Today, my topic on AI plus sustainability will have 4 parts. Let's dive in. No. Alibaba Cloud is the earliest high-tech company in China to open source its large AI models. We actively develop advanced AI technologies and have achieved open source across all sizes, modality, and applications. Over the past years, Alibaba Cloud has made over 200 generative AI models open source, and this includes all sizes and types. The model parameters range from 500 million to 110 billion. As to the model types, we have text generation models, visual understanding and generation models, speech understanding and generation models, as well as text to image and video models. Our goal is to provide green and affordable AI service for all our customers. As of now, more than 100,000 derivative models based on the Qwen family of models have been developed on Hugging Face, making it one of the most prominent models family worldwide. In addition to embracing the open source AI technologies, Alibaba Cloud also offers a full-stack cloud service covering IaaS, PaaS, and MaaS, which is model as a service. And as the largest cloud service provider in China and the leading one in the Asia-Pacific region, we cross 87 availability zones and across 29 regions globally. Alibaba made 3 carbon pledges in 2021. First one is decarbonize Alibaba, including Scope 1 and 2. Also greening the value chains, enabling low-carbon circular digital ecosystem. And Alibaba Cloud also will reach carbon neutrality and 100% clean energy use by 2030. Infrastructure represented by data centers is a crucial hub that transforms energy into computing power in AI era, and therefore is also a key part of sustainability. We have to think about, firstly, how can we make AI cloud a service of sustainable? What we call sustainable AI in this part 2. Secondly, how can AI algorithm, tools, and the products accelerate carbon neutrality? We will talk about this in part 3. To achieve sustainable AI, we propose the Green AI Infra Stack 5 greens. For green energy in our data centers in fiscal year 2024, we have a PUE of 1.200. Our clean energy mix is 56%. We are recognized as leaders in renewable energy consumption by BNEF, Greenpeace, and China Electricity Council. In 2024, we signed a 700 megawatt renewable energy PPA, integrating source, grid, load, and storage. It shows our commitment to sustainability and renewable energy. We developed the key components, including power distribution unit, cooling and control system for data centers, open source the latest Cube DC5 architecture, continuous optimized operation to achieve higher energy efficiency. We help customers reduce carbon, by 3 steps: carbon footprint, carbon bill, and carbon intelligent recommendation. Our work on sustainable AI is recognized by UNIDO, IEEE, and others internationally. UNIDO is United Nations Industrial Development Organization. In this part 3, we talk about AI for sustainability, namely how can AI algorithm, tools, and products accelerate carbon neutrality. Data center is suitable for AI applications since it's highly digitized with diverse energy conversion process. In Alibaba Cloud, we propose artist framework to improve data center lifecycle operation. AI help data center efficiency in site selection, electricity trading, operation, and job scheduling. We achieve more than 10% energy consumption reduction per computing power and more than 15% operation cost per computing power. AI adoption in data centers can be summarized as the organic combination of DC-verse, digital employee, and robots. DC-verse transform physical data centers into digital world while maintaining real-time data sync up with the physical world. It's not only simulate physical data centers, but also achieve autonomous operation with AI algorithm. Digital employees, much like human employees, can directly handle work orders, significantly improving work efficiency. And the robots are responsible for tasks such as site inspection and rack installation, and all this kind of work. Ultimately, DC-verse, digital employees, and robots will interact and collaborate seamlessly with one another. Here comes two real cases. The first one is about AI for power grid resilience and reliability. Alibaba Damo Academy built an AI-based global medium-range weather forecast model. By leveraging the global regional joint learning framework, it can provide accurate hourly prediction at 1 kilometer spatial resolution. The weather forecasting model significantly improved the forecast accuracy of downstream tasks in the electrical power industry, especially when extreme weather happens. Damo Academy further developed an interpretable renewable energy forecasting model based on the global weather forecasting model. It actively mitigated the uncertainty posed by the intermittent renewable energy, ensures the reliability of power grid, improves the consumption of renewable energy, and further alleviate the pressure of climate change. Another case is about AI for energy-intensive industry decarbonization. Our AI-powered digital control system, so-called Industry Brain, from Alibaba Cloud Group, provides energy-intensive industry such as cement manufacturing, steel making, and solid waste management automobiles with solutions that improve energy efficiency and conserve resources. In fiscal year 2024, it enabled our customers to reduce 304,000 tons of emissions. Last part is our prospects. These are our 3 focus areas at present: technological innovation, standard development, and ecosystem build-up. Technological innovation includes the full stack of AI technology from model, platform to infrastructure. We target at higher model and energy efficiency that could be driven by cutting-edge energy techniques. Standard development will primarily focus on establishing metrics for AI energy efficiency and accounting for energy consumption. The key indicator will be the energy consumption per token. The ecosystem includes not only customers and partners, but also include governments, organizations, universities, and research labs. By fostering ecosystem development, AI technology is being integrated into more industries, enhancing their sustainability. The Alibaba NTU Global E-Sustainability Corporate Lab, we call it Angel, officially launched in September 2024, represents a key collaboration between Alibaba Group and the Nanyang Technological University, supported by the Singapore Real 2025 Fund. Angel creates and deploys impactful green digital technologies for global sustainability. Angel is quite a good platform where we combine our focus with business. For instance, we conduct AI full-stack energy consumption modeling with NTU in green cloud service and green AI projects to reduce carbon emission per computing power. We aim to set up standards for efficient modeling and infrastructure. We collaborate with academic institutions and industry alliance to establish platforms for research, application, and incubation. Therefore, we call on all industry to embrace AI and actively consider how it can boost efficiency. Let's welcome a sustainable future with AI. Thank you all.
Thank you, Mr. Wang. I would now like to transition us to the initiatives launching on scaling green AI in infrastructure, policy, and research in action. These case studies will spotlight and showcase real-world examples of sustainable AI practice. First of all, I would like to introduce Jeremy Renshaw from the Electric Power Research Institute to give an introduction of EPRI's Open AI Consortium. Please join me in welcoming Jeremy.
All right, thank you. I'm happy to be here today. All right, these have been great talks so far, and I want to especially thank Jerry, Jay-Z, and the rest of the Green AI team for the wonderful leadership that they're expressing here. Just really fantastic summit that you put together. I know how hard these can be to do, so I really appreciate all that you've done to pull us all together today. So what I'll be talking a little bit about today is an initiative that EPRI, the Electric Power Research Institute, has put together with a number of organizations around the world that we're calling the Open Power AI Consortium. So without further ado, I have just a short video to introduce it for us. If it plays.
Announcing the Open Power AI Consortium.
In case you were wondering, that music was AI generated, the voices were AI generated. One of them was a deepfake of our CEO. But the 1970s style graphics, those were human generated. So still have a ways to go. We couldn't quite get the AI video generation to work for us for that, but maybe next time. So what are we looking to do with this consortium? So really it's looking at how can we provide higher performing, smaller models. So you think of that from a sustainability perspective of how can we get better answers to responses that we have to large language models, foundational models, other AI models, using less energy both to train and use them. So what we're doing and how we're going about this is really looking at three main areas, three main groups that we're trying to target. One is, of course, electric utilities, the ones that are providing the power. Second is a lot of this group today. Academia, national labs, other key organizations that are involved in this space. And of course, the third one, technology partners. This could be your hyperscalers, it could be your AI developers, or others that are involved in training, testing, and validating AI models. And what are we looking to do with this consortium? So what we're looking to do is really around three main work streams. The first is a focus on open source data, models, libraries, and other tools to be able to help the industry, in this case, the power industry, to be more effective and more efficient with their AI aspirations. The second area is developing an AI sandbox, or really collection of sandboxes, so that the organizations that are wanting to use these models can test them out in a virtual environment with simulated conditions, with unseen data, to be able to verify that they will work in a real world environment. And what I mean by that is, if you look at standard AI models, if you get, say, a marketing model that is 99% effective, that is amazing. If you keep the power on 99% of the time, that is an abysmal failure, because that means about 15 minutes every day, your power's off. And people don't like when their power goes off for a second. Imagine, 15 minutes a day, or in some cases, it could be worse than that. So we have a very different standard of reliability in the power sector than many others. And then, of course, the third work stream is looking at implementing these models into the real world and bringing those lessons learned back to the developers to create a virtuous cycle and a feedback loop, so that as we continue developing, training, and testing these models, that we will understand how and where they will be effective and how effective they are. And finally, de-risking that deployment. So instead of 50 utilities, each working on 50 different use cases, why can't we have 50 utilities, each working on one, doing it really well, and then sharing those lessons around the world? And one of the things that we do really well within the power industry is global collaboration, sharing those lessons learned to be able to help others around the world. And EPRI is in a unique place as a global nonprofit organization. We have a public benefit mission to help the global industry have safe, affordable, reliable, and environmentally responsible energy. So what are we doing? We're looking at how can we take the existing open source models, your llamas, your Qwens that you've heard about earlier today, and build on top of those with energy sector specific data to create domain specific models. So you can look at these as smaller, higher performant models that, instead of training on the world's global knowledge of data, the history of the world, how to make fire, how to tie a knot, how to bake a cake, how can we tune these so that they only have the knowledge that we need to interact with them for energy specific data? How to operate a substation, how to set your relays, how to optimize your power flow in a grid, how to perform asset management with boilers, turbines, feed water systems, and so forth. And then augmenting that with vast tomes of energy specific data, whether it's EPRI data, ASME, IEEE, CGRE, other global industry organizations that have energy specific data. And then the last piece, and the most important piece, why you see kind of a step change there, is using a company's specific data that they have behind the paywall or behind the firewall that is not open to the public, to be able to further train, test, and tune those models. And where we're going with this, and what I mean is, about 95% of the world's data is private data. I mean, there's vast amounts of data that's publicly available on the internet, but most of the data, and the most valuable data, is not open to the public. So what we're looking at doing is bringing the global industry together to open source more of that data, or anonymize data to be able to share, or generate synthetic data that can be shared that is not giving away key aspects of the power system operations. So really bringing that global network together to collaborate, to share data, and improve the global well-being of all humanity. So pretty big goals that we have here. We announced this last month at NVIDIA's GTC conference. Since then, you can see we've signed up about 40 organizations. We're in talks with about 30 or 40 more. So we're growing quickly and happy to be here. But for Jerry's information and the rest of his team, this is the first time we're talking with an academic audience. So thank you for this invite, and we are happy to be here. You'll notice that our key partner is an industry university. That one is a little bit vacant. So we have lots of utilities, but we need you. So if you're interested in getting involved, there's no cost. We just ask for a commitment that you come with the intent and the desire to make a difference and make an impact in the world. And then we want to bring you in to collaborate with us in the global consortium that we're putting together. So with that, if you are interested in getting involved, it's very easy. Send an email to openpowerai@epri.com. Talk with me after this talk. I do have to leave at lunch, so catch me fast. And tell us that you're interested in getting involved. We will make it easy for you to get involved. And like I said, we want to make a global difference. Now, I did promise Jerry to also talk a little bit about data centers. So we have a parallel effort, not free, not open to everyone, on data center flexibility. So I've heard a lot about that. I liked the reference to the nuclear NIMBY, you know, not in my backyard. I've got a new acronym for you that you might want to use. It's BANANA. Build absolutely nothing anywhere near anyone. That's my new favorite acronym. So yeah, feel free to use that, spread it around. I want to make that one go viral. But let's actually build some things near some people so that we can get a global footprint of helping to develop these AI tools and models and using the data centers instead of just as a sink, as a grid resource. So we've heard about flexible data center operations. I think that's going to be a key ingredient in helping us to be successful, not only for AI, but with other initiatives. We heard quantum computing will come up. I think all of these areas around data centers will be very important going forward. So if you're interested, reach out. We'd be happy to pull you into either the Open Power AI Consortium or our data center flexibility initiative. And with that, I will close.
Thank you, Mr. Renshaw. I now have the pleasure of welcoming back to the podium Professor Shirley, the Gordon McKay Professor of Electrical Engineering at Harvard John A. Paulson School of Engineering and Applied Sciences, to give an introduction of the Power in AI Initiative, or PAI, at the Harvard School of Engineering and Applied Sciences. Please join me in welcoming Professor Shirley.
Thank you. And thank you, Jeremy, for this very interesting initiative at EPRI. We're going to talk about something we are doing here at Harvard. So as you know, I've been here for about 8 months and been really engaging with these wonderful ecosystems. Jeremy talked about 2 initiatives. One is called Open AI, Open Power AI, and the other one is called DC Flex. If you think about it, it sort of very much synergized the mission here, which is trying to bring the computing and the AI aspect a lot closer to the power systems aspect. Here, we sort of, we do not think about this as 2 separate initiatives. We sort of bring them together. And believe me, I spent a lot of time just thinking about the acronym of PI. So, but what is our core mission? At the university, I think our core mission is education and research. And in particular, I believe at Harvard, we would like to create a cohort of talents that are deeply immersed in this world-class liberal arts environment, but are engineer leaders who are very well versed in both the power aspect as well as the AI aspect. And I think most of you would agree with me that if you go around the world nowadays, you don't find many talents who are very well versed in both aspects. So this is what we want to do. And I'm actually going to just, I don't have the fancy videos, but we have some research papers. I'm actually going to give you some of the snippet of some of the research frontiers that we're actually pushing, and just to give you a sense of what we're doing, and then hopefully get your excitement of working together. I see this really as very synergistic to what Jeremy has talked about from the industry perspective. And, you know, me as a person, but actually there's a broader agenda at Harvard Seas or Harvard in general, is that we really are honing in on climate and sustainability, as Professor Jim Stock mentioned this morning. I'm actually one of the few new hires at the School of Engineering, and then at the university level, we have this broader agenda. And if you haven't, how many of you have not been to this building? This is the new engineering building at Harvard. If you have never been to the building, if you have some time on campus, I do encourage you to spend 30 minutes just touring it. It's next, across the river, absolutely wonderful facility, and they touted it as the healthiest building in Boston. I don't know what that means, but it is the healthiest building in Boston. So our lab, our research group are over there. the motivation of doing this research and education initiative is really that we're seeing a lot of computational driven power surge, both in the form of AI data center and also in the form of things like blockchain or cryptocurrency type of computation. But both sides, while energy efficiency is getting more and more improved, the amount of computation is exponentially growing at a much faster rate. And we have this sort of a insatiable demand for computing. So the real question is, what is the interaction between the power systems and AI or computing? And the way we would like to think about it is that it is really a two-way street, not a one-way street. In other words, the improvement of AI is going to be tremendously advancing the way we do short-term as well as longer-term decision-making in the power sector. And in the meantime, the power sector is positioning itself to accelerate the deployment of computing and AI. And that's sort of where this is coming about, right? And just to kind of give you a sense, we have some folks coming from the data center world. You probably can appreciate that. But doing a state-of-the-art large language model training, what is the implication on the power grid? So the implication of the power grid is that there's a lot of fluctuations, as you can see here. But how do we best characterize that at a large scale? And the short answer is that we don't know yet. So we are working towards that. And then also, if you aggregate them together at a sort of a megawatt or hundreds of megawatt level, what is their response to some of the wholesale level energy market signals, such as the one you see here at the bottom? The short answer is that they seem to be somewhat flexible, but not entirely flexible, right? So the question is really, how do you characterize the flexibility and how do you harness the flexibility? And many researchers here are actually pushing the boundary as we speak, right? And then the other side is that, do we have enough of a grid infrastructure for this demand of computing? Is it just because we don't running short of supply of energy? I would beg to answer that it probably is not because we are short of supply of energy, but more so because of the short of the grid infrastructure, right? And this is actually something very new that Texas has just approved this highest voltage level in the US or North America, 765 kilovolt transmission backbone that's going to supplement the grid in Texas. And this is just one example of this kind of a build out. So on the both ends, there's a lot of a need for educating as well as research to bringing these two communities closer to each other. And these are some example we did. I'll just give you a snippet of some of the research we did. This is in the context of a large data center, but this is more of a crypto data center. So the question was, how much of flexibility are they already offering to the grid at a wholesale level? So we look at this. We were able to get some of this data firsthand, and at least to my surprise, that if you look at their correlation coefficient between this data computing loads and system-wide net demand, meaning the total demand minus the renewables, their correlation coefficient is very different from all the other kinds of demand, such as industrial, commercial, or residential demand. Because in all these other categories, when the grid is very stressed, you're also using the most amount of power in your household and in most of the industrial settings. But these data centers seem to be exhibiting sort of a negative correlation, which means that when the grid is stressed, they seem to be reducing quite a bit. Now, the question is, of course, for this broader context of computing devices, such as large language model training, is that also true or is it not so true? So what does it take to make it a lot more flexible, right? So a lot of research is going on behind the scene. I had the honor of going to the White House last February for this Office of Science and Technology Policy Roundtable about AI for energy, which some of the utility folks were also involved. And that also sort of inspired some of our research on thinking on the other side, which is what exactly is the capability as well as limitation of the foundational model of AI in today's power grid? Like what Jeremy said, data is a huge issue. But beyond data, just in terms of different kinds of use cases that actually power engineer cares about. What are some of the capabilities that this foundation model can offer and limitations that we are not there yet? So we sort of conducted a whole range of studies, probably first in the world last year, and published in this journal paper last June. And you can see there's a whole list of use cases that actually can relate to a lot of our power engineer friends here in the room. Let's give you a very quick snapshot of one example that we did last. So you have to chronologically think about this was done in the spring of 2024. Question was, if you look at all the historical wildfire situation in California and all the California transmission line map, could you ask the AI to tell them the preventive strategy for the upcoming wildfire? Unfortunately or fortunately, the answer was quite good because it was validated in this year's wildfire actually turned out to be what the AI predicted to be highlighting on. So we wish that we have pushed this a little stronger and faster into the real world. And that's exactly what we are doing now. And now we are sort of in the second phase, which is trying to understand this whole scaling issue. You know, one of the big success for large language model is sort of this scaling law and how that sort of pumping in more data means better performance. So roughly the idea is that. But then the question is, how much of a data do you have to pump in for the fine-tuning stage? And then to our surprise, and perhaps Jeremy, we can talk about that offline. If you're talking about a power grid, you actually don't need that much of a significant data at the fine-tuning stage to have a very, very surprisingly good performance for foundation models. So data readiness, scaling law, understanding the quality, and a lot of the guardrails on the privacy and safety side, which I think utility colleagues and power industry colleagues care a lot about. And you know, some of this also was presented to the policymakers, such as you know, system operator and chairs of the PUCs. So to sort of summarize, I think we are entering this very exciting era where this sort of interaction between AI and power sector is really, really very fruitful area, both for education and research purposes. We can think about AI, sort of the best way I can think about it is sort of co-pilot for time-sensitive decision roles, but not yet to be a sole pilot. And the challenge is sort of the safety and privacy guardrail. That's one thing I think our utility friends care a lot about. And then in terms of powerful AI, I think the big question out there is how do we harness the most amount of flexibility from these data centers? And then the challenge would be through this time scale alignment. When the grid is expanding on a 15 to 10 year time scale, and the data center are updating on a 6 months time scale, right? So with that, we kind of got together at the School of Engineering that my colleague, Professor Minglan Yu, who is an expert on computing systems, and I are working with a whole range of stakeholders to bring about this power and AI initiative to really look at both education as well as research aspects of this interaction between power and AI. And very pleased to announce that on the one day, May 20th, we are going to have the symposium. It's a lot more, research focused, and we're going to bring basically half power industry and half AI industry together. So we have companies like OpenAI, Meta, Google, Microsoft, and AWS. We're also going to have companies like Avisource, ISO New England, ERCOT, Avangrid, and Encore and Centerpoint and so on. So bringing these two communities together. And then we're going to have a short course because we felt like at this intersection, we may know a little about power, but we don't know much about foundation model, or we may know a lot about data center, but we have no idea how to do power system planning. And so we're going to actually teach people about this together. A very interesting experiment. We encourage you to participate. And with that, I thank you for your time.
Thank you, Professor. I now have the pleasure of introducing Paulo Carvalho, the Senior Fellow at the Mustafa Rahmani Center for Business and Government at the Harvard Kennedy School and former General Manager of IBM Public Cloud. Please join me in welcoming Mr. Cabal.
Hey, good morning, everybody. Congratulations, Jerry, and the team that organized the fantastic event. As a electrical engineer turned technology business executive, turned the policy wonk. Now I have a real appreciation for the intersectionality of these subjects, not only from a technical perspective, like we just heard, between power and AI, but also some of the social technical aspects of this. Back in October, I was here in the first edition of the summit, and I talked about the need of innovation and how some innovation was required for us to deliver to this promise of a future green AI. And I talked about innovation along a few dimensions. One was innovation in terms of new models that would be more energy efficient. I talked about innovation in terms of data center design and operations. And also I talked about innovation in terms of data center siting so that we could start locating these data centers closer to greener energy matrices. So I'm glad to see that all of these, 6 months after, are being reflected in the talks here. But there's another area of innovation that is required, which is policy innovation. So how are we using policy to make sure that we have the needed set of incentives guiding the R&D investments per the industry and government in the right direction. So that's the area where I have been working for the last few years, actually the last 2.5 years, since I left the business and joined here at Harvard. And I've been focused on AI policy for the United States. Why the focus on the United States? First, I think that through efficient usage of policy, we can maintain and extend our leadership in this space. And also we need to recognize that, a lot of what's happening in terms of AI is happening here in the US and as well as in China. So, and the fact that we have a vacuum, especially in terms of federal policy, creates an important space for us to have a debate in this area. So my team, it's basically, we had a small group, 2 research assistants joined me. They're master's students at the Kennedy School of Government. We also partnered with the Harvard undergrad machine intelligence community. And what we have done is we have done close to 50 in-depth interviews with C-level executives in the industry and also members of the US Congress and both the House and the Senate. And to try and understand what is going on from a legislative perspective, we've taken the 150 AI-related bills that have been issued during the last Congress, 2023 and 2024, of which, by the way, 0 have been enacted into law. We put this into a model. We did natural language processing so that we would understand from those thousands and thousands and thousands of pages, what patterns were emerging. So we learned a few things. I'll leave you with a reference for the paper with all the details. But first, there is a belief in going it alone from a U.S. perspective across both Republicans and Democrats, which is a little bit concerning since a lot of the issues that we're discussing here are global in nature. There is also a very intentional lack of AI regulation. This is not, sometimes we blame it on a dysfunctional Congress. I think it goes well beyond that. It's a very deliberate process of trying to maintain a laissez-faire approach to this. However, there are agreement in certain areas in Congress. There's agreement in terms of investing for maintaining or extending the U.S. AI leadership. Interestingly, there's agreement and understanding that we do have an energy problem, not only in terms of, and it's been discussed here today, not only in terms of not having enough energy to power the upcoming AI data center buildup, but an inefficient and obsolete energy grid that needs to be transformed. So, we should expect some legislation in this area. Now, there is still a significant lack of trust between industry and Congress, and it's something that needs to be addressed. Also, in talking to several within the industry, it became very clear that it's a oversimplification to talk about industry. What we have is a diverse set of point of views, from OpenAI development advocates to people more focused on public interest, people that advocate for national security, small firms and startups, big tech. So it's a very diverse set of investments. And across the board, there is a concern with the fragmentation of policy, not only internationally, but also in the United States, as the states are starting to move with legislation and regulation absent of a federal policy. And also there is resistance to creation of any new government structures or agencies to regulate the area. And finally, there is kind of a perception and a concern that we have a very early stage AI ecosystem, and as such, a resistance to try and regulate it before things mature in this space. So based on all of that, we created a proposal that tries to bring industry and government together, that also can deal with the fact that this technology is still evolving very quickly. So any policy proposals and regulation or legislation that is created needs to be incremental and adaptive over time. And with that, hopefully break a little logjam that we have today that is kind of blocking any policy, as we have seen with the 150 bills, of which 0 have been enacted. Earlier this month, my team and I went to DC. We presented this at the House, at the Senate, and met with industry associations, lobbying groups, and it was, it's a very, very good. And we also submitted this as an input for the RFI that was issued asking for an AI strategy for the country. We called it the dynamic governance model. It starts with the government defining what are the policy goals that you want to pursue. Many times we think about policy goals as something that would restrict action. You also can think about policy goals as something that will foment or incentivize investments in a given area. And then it has 3 steps. The first step is the creation of evaluation standards through public-private partnerships that would bring industry and government together. We talked a lot about standards earlier today, and other initiatives in this area. The second one is the creation of a market-driven set of solutions for audit and compliance. So this is either based on the standards, if we can get and evolve the standards to a point in which they can be automated. We can even have kind of a little bit of a cottage industry of ragtech entrepreneurs that will create technical solutions for automation of the standards, or it could be auditing done by third parties, like it's done today, for example, for financial standards. Another component that can be evaluated in this area is the creation of regulatory sandboxes, since we have a lot of unknown unknowns in this space. So it would be good for government and industry in a sandbox to understand this. And then finally, this will feed a system of accountabilities and liabilities. Today in the US, we can address this in 3 different ways. We can address it via antitrust. We all know that there's significant activity in this area. We can address it via liability or torts, which is kind of litigating in court. And by the way, there is even interest by the industry in the creation of standards so that you minimize your liability risk. Or in the process of understanding this, we can start to creating ex-ante regulation for specific areas in a way that wouldn't be, hurting the ability of the industry to innovate. And this kind of retrofits, again, the standards process, and we continue dynamically as the technology evolved. So that's the dynamic innovation model. As I mentioned, we just completed this, published a paper. You have a link here to the paper that we published at very end of February. We've taken this to DC. Hopefully, it will influence a little bit the government policy that it's about to be published, and you can keep track on what we're doing via this Substack. So thank you very much.
Thank you to our wonderful speakers and our attendees for joining us for the first half of our day. Before we move into our lunch break, I would like to give a quick preview of the latter half of the day. After lunch, will be followed by two panels, the first on a low-carbon AI and data center ecosystem, and the third on the next-generation computing hardware. Afterwards, we'll have a series of lightning talks on emerging innovation in green AI, as well as our final panel on green AI and data center policy and investment. This will be followed by our launching ceremony, as well as a networking session to end the day. For our lunch break, I would like to invite our invited speakers to please make their way to my left to where the lunch will be served. And for our attendees, the Gutman Center hosts their own cafe on the first floor upstairs. And if you're in need of assistance, you can spot our volunteers who will be wearing these blue lanyards. And I'd please like to invite everyone to make their way back here for a prompt start at 1 p.m. Thank you so much.
Thank you.
Oh, okay. All right, thank you. Yeah.
东海挣脱，翻过沙滩路探索，发现遗失的堕落。问我找什么？哦，白色反光中的我，追寻前梦的线索。爱上是不得的快乐，天下起。
Upbeat music, upbeat. What is this? Wait, what is? Wait, happiness? Wait, I'm not sure right now. Let's don't do that. Okay, let's do it. It's fine, it's fine. Let's just get back to the slide.
It's just 5 minutes.
Yeah, let's go back to the slide. Maybe, yeah. But is our screen also shared?
什么 screen？
刚刚是音乐在 share 上，
对，
但是画面没有 share。
没有。
那我们可以 share audio 先静音啊，我们放点小歌。
什么 audio 记忆很小。
哎，算了，不算了，就这样，就这样。
因为如果你这个 share，它也会 share。
I was report to me. I know. Oh, he's online. Nice to meet you. Well, I saw it. Yeah.
Yeah. Thank you. It's about a 2 hour. Thank you very much here. Thank you.
Thank you, everyone. We'll be jumping straight back into our event with our second panel of the day on a low-carbon AI and data center ecosystem. The rapid expansion of AI and data centers has led to rising energy consumption and environmental concerns. This session will explore solutions for reducing their carbon footprint. I have the pleasure of introducing our moderator, Andreas Klaub, the technical leader at Electric Power Research Institution, or EPRI, who will be introducing our panelists today. Thank you.
Good afternoon, good morning, good evening for those online. Just want to first say thank you to the Green AI team for putting on this summit. I found it profoundly interesting, and it's such a fascinating thing to be a part of this event. There's a lot of interest in the subject. We covered a lot of ground in the first morning. So we're going to talk a little bit about a panel today about low carbon AI and the intersection with the power system and some energy innovation concepts to get us through to the next chapter of this. As was mentioned, I'm a senior technical leader with EPRI or EPRI, or the Electric Power Research Institute. I have a power systems background. I've been involved in the industry for about 10 years. We have a couple panelists here. I'm going to give a quick introduction, and then I'm going to go to our panelists and walk through. They can introduce themselves. But a couple things that, from my observation on the power system, are pertinent, and that the intersection of big tech, for me, is relatively new, given my heavy power systems background. But I joined the industry in about 10 years ago. And one of the things I first noticed, there's three things. First is the flat or declining load growth on the bulk power system. At the time, this was about 2015, the overwhelming historical records were already almost 10 years old. And I was always told that we're never going to see these records again. And rapidly, I want to say around 2022, 2023 timeframe, you see a distinct hockey-shaped curve where the compound annual growth rate increases tremendously. And I know hockey is a tough subject for those Boston Bruins fans not in the postseason locally here, but that's the reality of what we're dealing with. And in some cases, talked a little bit about peak demand versus total energy use. And that's been a profound change in the last few years. And now, in the long term, I want to say about 10 years, you're seeing risks of peak demand, sometimes multiple times what those historical records were. So in a matter of just a few years, you've seen we're never going to see these peak records again, to now we're shattering those records in many areas of the country. And this is in the North American context, but you can apply it to globally. The second thing I want to talk about is the resource interconnection process. The resources that are meeting that demand now with those heightened demand are thinning reserve margins. So the resources that are coming in are vastly wind, solar, and storage resources. But those can't connect fast enough. So we're seeing those resource adequacy risks. And now we're seeing different initiatives with the uncertain climate in DC that we're looking to any sort of resources that we can. In some cases, we're keeping resources online. Other times, we're fast tracking more carbon intensive resources than perhaps what some would like. And the last thing I want to mention, at least on the grid power system, is the interaction of these large loads. We did see recently a lessons learned report out of NERC, which is the North American Electric Liability Corporation, with a 1,500 megawatt data center that suddenly dropped off the grid due to a grid disturbance. So that's a 1,500 megawatt load that dropped off in a matter of seconds, switched to perhaps a backup power supply, maybe diesel. But the implications there, not only for emissions, but also for the grid health in general, that's still to be more well understood. So enough talking for me. I think I've scared everybody enough. I'm going to turn it over to our distinguished panelists, setting the stage. So we're going to be looking at low carbon AI and the interaction with the green development. So our first panelist is Dr. Jun Zhao, with Manager of Power System Automation at Eversource Energy. We have Dr. Varun Sivaram, a Senior Fellow at Council on Foreign Relations. We have Peng Zhao, Assistant Professor at Harvard School of Public Health. And then online, we have Xiaolei Ren, Associate Professor of Electrical and Computer Engineering at the UC Riverside. So thank you all for being here. I guess in particular order, we'll just say, please introduce yourself and your familiarity with the challenge ahead of us.
Okay, yes, thank you. This is June, and the manager of the power system automation at the Eversource Energy, the local utility company. And we are a data team in the company in the engineering and operations side. We are trying to use data analytics, machine learning, AI to improve the efficiency for the asset inspection and the predictive maintenance. And prior to that, I was a professor for 7 years. And so very nice to have a talk here. Yeah, thank you.
Hi, everyone. First of all, Andreas, I don't want to hear any more self-pity from Boston sports fans here. I mean, you guys are the home of the Boston Celtics, unique capability of making everybody else feel bad about our hometown teams. I'm Varun Sivaram. It's great to see you all. I have two hats. I'm a senior fellow at the Council on Foreign Relations. They say there are decades where nothing happens in foreign policy, and there are weeks when decades happen. We're in one of those weeks right now. So if anyone wants to hear about DC, I'm happy to tell you. My other hat is I'm the CEO and founder of a company called Emerald AI. Emerald AI makes data centers flexible grid assets to make it possible, as Andreas was saying, to speed up those resource interconnection processes. Happy to talk more about that. Thanks.
Good afternoon, everyone. Thank you for a kind introduction, Andreas. My name is Peng Zhao. I'm a faculty member from Harvard Chan School of Public Health, from the Department of Environmental Health. So I'm not an AI expert, as you can tell by my department, but my lab's research primarily focus on the measuring and monitoring the different type of chemical pollutants persisting in the environment, and how they contribute to the chronic disease like cancers and some respiratory disease as well. And recently, we also become interested into covering the implication of in terms of the health and then environmental impact induced or caused by the technology infrastructure development, such as the AI and the data center deployment and development. So I just hope I can bring some different perspective of how we can make the AI development or data center development more sustainable or more eco-health friendly. Yeah.
Hi everyone. I'm Xiaolei. I'm sorry. I'm just in my hotel. So, in the last like more than 10 years, I've been primarily working on the intersection between power systems and data centers. I've been working on emergency demand response and demand side management for data centers, with a focus on sustainability, water consumption, including carbon water consumption, and more recently on the public health impact of the technology. And I'm happy to be here.
Thanks so much. And as you can see, we have a very diverse panel, pretty heavy power systems background, which is great. A little change of flavor here. So I always like to start with the easy questions first. Since we have such a diverse background here, I want to talk about what are the low-hanging fruit that we can achieve today. I talked about the immediate needs on the power demand, those pressures on the power system to accommodate these large loads, and there's a variety of reasons for that. So from your standpoint, what are the lowest hanging fruit that we can achieve, let's say in the next year or two, in the space to help solve this challenge? And then I'll talk a little bit about what that challenge is.
Okay, yeah, I can talk about this from energy company and also that from the application perspective. Like at the EverSource Energy, that we have, try to use the AI and machine learning to solve the problem for the asset inspection. And we developed them streamline, so take advantage of the computer vision so that it can get so quickly and accurately to detect by using camera and AI, detect like on our eyesight, on our infrastructure, what kind of the equipment over there and the defect over there, and build a streamline to give the user, to give the operation team quickly visualization about the system status. So I could see this is a kind of the low-hanging fruit. Why? Because the computer vision has been over there for, I think it's longer than the large language model and the other AI method. And that's also can be easily to apply for the energy industry, and also not only for the distribution, for the transmission, for the substation, for the whole system. Okay, yeah. So this is our application. Yeah.
Thanks so much.
Thank you.
I think we're just going in sequential order at this point. So Varun, from your side, don't want to lead.
Sure.
Yeah.
Let me hit two different categories of low-hanging fruit. The most obvious one is the low-hanging fruit that's enabled for the last 2 decades data centers to stay at a relatively flat amount of American power consumption. That's efficiency, right? Data centers today, and I'm sure you heard this in the morning, live at about 3-4% of American power consumption. And that's despite orders of magnitude of increase in the usage. Look, none of you guys were streaming Netflix videos 2 decades ago. And despite the rise of insane cloud computing, we still use about the same amount of power for data centers. Efficiency is also going to be a low-hanging fruit opportunity in the data center rise that corresponds to AI, right? The Blackwell NVIDIA GPU architecture is substantially more, in order of magnitude, more efficient than the Hopper architecture. A lot of the low-hanging fruit there is going to come from the system integration of these AI systems, let's call them. But there's a wall you're going to hit, right? Already in the fundamental underlying semiconductors, we've hit scaling laws. It's hard to go much smaller than a couple nanometers for gates. And so therefore, first of all, I don't expect efficiency is just going to solve the problem magically. I actually do believe we'll go from today, 4% of electricity consumption in the US is data centers, to 8 to 12% by 2030, just 5 years from now. So I do expect that to happen despite efficiency improvements. And second, precisely because we're going to hit these efficiency walls. So what else is there? I'm going to call this a low-hanging, a medium-hanging, and a high-hanging fruit. And it's load and demand side flexibility. And Xiaolei, I was glad to hear you talk about demand side management. So maybe you'll come in on this as well. But there's a gentleman sitting somewhere here in the audience. I think I see him there. Tyler Norris, researcher at Duke University, who's written extensively, and he's a speaker later on. He's written extensively about how there is substantial headroom in American power grids around the country to accommodate far more load just with existing power systems and existing power plants, about 100 gigawatts of such headroom if we can tap into that low-hanging fruit of load flexibility. I call it low, medium, and high because there are easy ways to do this. Today, there is latent flexibility already in the way that AI data centers operate. And the medium and high is going to be the truly graceful and sophisticated approaches to coax additional flexibility out of those data centers. Hope we get into that.
Yes, so I think I would like to say maybe from the design's perspective, especially using less toxic and more environmental friendly materials, as well as make sure the new GPU or data center design is more consider the environmental impact and not just the performance as we previously did. And because I was more like a proactive person. My career had been involved in chasing different type of environmental pollutants for decades. The industry development we had before was trying to solve the problem after we realized that. For example, right now some emerging contaminants called PFAS, like forever chemicals, which have some proof to cause different chronic disease. It's also a problem in the chip industry as occupational exposure. And these contaminants was not realized the potential environmental health implication when the industry invited them. Yeah, so I think that's a story we have been learned. And so I think if we can prevent any potential problem to lead to unsustainable outcome, then maybe we should consider when we design things. Yeah, so that's my perspective. Yeah.
Thank you. Xiaolei?
Sure. So I think to me, the low-hanging fruit is really leveraging the flexibility of the data center to help the grid survive the emergencies when the grid is nearing the capacity, or even when there's some potential outages. The data center can shut their load, can move their loads to different places, or I think this is the emergency demand response is really important because eventually the purpose of having the power grid, the primary priority is just to ensure the grid stability, ensuring the supply and demand are always matched. And having this flexibility from the data center side is really important. But at this point, with data center, many of the data center participating in emergency demand response, they turn up their backup generator, which is not really the ideal way. Some tech companies have tried to use like spatial load shifting to move the workloads away from those congested grids, congested network part to other places. But for many other data center like co-locations, they have unique challenges because the data center operator don't really have the direct control over the servers or the loads, and they can probably like turn up their AC temperature set point a little bit, but doesn't have a lot of flexibility. So they need to rely on backup generators. But in the future, I think if there's more coordination between the data center co-location provider and their own customers like tenants, then we can have more potential to help to leverage the flexibility of the data center to help the power system become more reliable. And also this is sort of flexibility is not only helping with the reliability, but also can help us better integrate the renewables into the system to lower the carbon footprint, lower the air pollution, and so on. So I think these are really simple things that can easily be tapped into.
So if you haven't noticed yet, I'm always an optimist, perpetual optimist. And I'm seeing some common themes, at least with the low-hanging fruit. We're talking about demand flexibility. We see that a lot of interest, at least on power system analysis side, to incorporate flexibility into some of our traditional assessments. So the two common themes that I want us to maybe hone in on as a panel are the demand flexibility aspect. And Varun, you mentioned 8 to 12%. Even me as an optimist gets scared about that because we're already towards the high end of some of the forecasts. So to increase that, I think that really puts the emphasis on demand flexibility. So the other thing is automation. So maybe we can use AI to increase the efficiency of these technologies and thereby reduce that demand. Just because as of right now, looking at the state of the power system, there is a little bit of a bottleneck, as was talked about in the morning, about the ability to build out resources. So how does the panel feel about utilizing AI to maybe solve some of these challenges in terms of demand flexibility, but automation? Are there use cases maybe that you're seeing? And you're not, I mean, you're at Eversource, so you're an actual utility. So maybe start with you about that.
You mean how to the automation?
That's correct.
Okay, yeah, that's I think since the start of the AI and the machine learning data analytics technology, just found a lot of the potentials for improve the efficiency and automate the workflow. And in the traditional engineering and the power company, and I mentioned that one side is by using the computer vision, and another side is about I think maybe many of the companies are facing this problem, that is knowledge management. Now you have a lot of the proprietary knowledge, you have the document, you have the data in different standards. And thinking about data, how many of the data you take advantage to make a decision? That only 5 to 10% of the data is being used to make the decision in enterprises. Another thing that what the percentage of the data you can use? Okay, only 5% of the data is structuralized. So that means many of the data that are in picture, in document, in video, and in voice, and so how you can convert all this kind of the data into a structured, and you can utilize them for your final decision. So I think that this is the two very huge potential. One is like to automate the inspection, and so you have the visualization about your infrastructure, your asset, so that you do the like a predictive maintenance and to improve the efficiency and reduce the downtime of your equipment. And on the other hand, that is for the knowledge management. This is very helpful for the knowledge transfer from the previous generation of the engineer or professional to the younger generation, and also for the company to maintain the knowledge within the company and for future innovation work. Yeah.
Thanks. Excellent answer. And I think this morning, Dr. Jeremy Renshaw at EPRI talked about the lack of data that's available in public space. A lot of it is private data. So I see an opportunity there in terms of, obviously you have to worry about security, and power system is very risk averse, but that's an excellent point. I do want to get to Xiaolei, because we were talking about demand response. So how can we utilize AI to utilize that powerful resource? Because as I mentioned earlier, the resource bottleneck on the bulk power system, that's an emerging challenge that's still being discussed widely around industry today.
Sure. So I think, the other panelist has already mentioned the usage of AI on the supply side. On the demand side, I think these data centers are already highly automated systems. So either these tech companies or those co-location data centers, they are much more highly automated than many other systems. So if you look at the number of employees in a large data center, they probably just have like 20 to 50 employees at most. And that's even fewer than a Home Depot store. So so that just shows they're already highly automated. And if you look at the research community, we've been publishing papers on data center demand response for I don't know how many years, more than 10 years at least. So I think the technology is there, but the problem is really to get them on board. So how can we incentivize data center to participate in this demand response more frequently, not just during those emergency hours, but also like more on a regular basis. So that's something I think many of the data centers are not in that type of mindset yet. And even though I think they do have the technical capability, but they just not either maybe not financially incentivized or some other reasons. Yeah, I think maybe we can use AI to help us design the market mechanism to get them on board.
Yeah. It's like you almost read my mind, Xiaolei. And you're in your hotel room. You're not even on site here. You led me to my next question, was talking about the policy frameworks. Now, this morning, there was a graphic about Winter Storm Heather, which was a winter storm event last year. And as we've seen on the power system, there have been very high-profile events with Winter Storm Uri and Winter Storm Elliott, and that's becoming increasing focus. And we saw the data center use that wasn't really aligned, or the draw on the demand wasn't really responding to what was actually happening on the grid at the time. So I want to talk a little bit about policy frameworks, since that's within the scope of this discussion. Varun, maybe you could comment on sort of more holistic policy level frameworks about the intersection of these traditionally divergent industries with data centers and the bulk power system.
Yeah, absolutely. To do that, let me just back up a moment. We're talking about trying to make a low carbon power system compatible with explosive growth of data centers, a growth trajectory that, Andreas, you said scares you, right? How do you do it? In my head, there's kind of 4 overall categories of strategies. Strategy number 1 is we build out more low carbon dispatchable or firm generation. So we're talking things that can ramp up and down, or things that provide baseload power, nuclear, next generation geothermal, right? In addition to, of course, the other clean resources we have and we love, like wind and solar and batteries, which are a dispatchable resource. The second category is expanding and strengthening the transmission and distribution grids. The larger your geographic area that you can basically average over, the easier it is to tolerate intermittency both on the demand and the supply side. So it's easier to match supply and demand at every second, like Xiaolei was saying. You got bigger grids. So grid enhancement. The third strategy is on-site resources. So on a particular data center, you might have batteries, a microgrid, a fuel cell. That's another way to make your data center a cleaner resource. And of course, the fourth one, which we've been just talking about, is load flexibility, and particularly computational load flexibility on the data centers themselves. And that, there's a reason that's the low-hanging fruit. That's the only one that didn't require CapEx investment. It's the lowest cost in the cost curve. Xiaolei mentioned that the academic community has been working on this. I do want to just make a shout out. Our chair, Professor Aisha Joshkun at Boston University, has a beautiful paper that says, look, it's not just that we want AI to be flexible. We might need to use AI to make AI flexible. And so that circularity is inherent in her Condor framework. I'm also very proud, by the way, Professor Joshkun is the chief scientist of Emerald AI. That framework uses a neural network, an AI, in order to modulate the AI training and inference. Well, so look, where do we go from here in terms of policy frameworks, which is your question, Andreas? Around the country, data centers are not going to have a choice because policy frameworks are under development, right? Senate Bill 6 in Texas, for example, there is a, Tyler and I were just having lunch, there's a FERC proceeding right now on the co-location order. I hope I got those words right. Tyler says maybe a little bit. Around the country, there are mandates or proceedings saying we need to make it possible for data centers to be good grid citizens. We need to transform them from being energy-intensive loads to grid allies. And you can either get paid for doing it, or you can get kicked off the grid if you don't. Or you might get very draconian restrictions, such as if Senate Bill 6 were to pass, the chance that a data center could simply get shut off if it weren't cooperating in a particular way or have the right equipment or the right software protocols to provide flexibility. My hope is that we go the route that enables both data centers to thrive and society to thrive, and not the draconian route that pits society against data centers. Because the worst outcome is you have a lot of data centers coming up in local communities, and the local communities say, my rates are going up, right? You don't want your grandmother's power price to go up because Amazon brought a data center next door. The way to align these incentives is for, again, those data centers to become good grid citizens. And that's possible, and Xiaolei mentioned some of the technologies. Around the country in Ohio, Indiana, for example, there are these cost allocation proceedings that say we're going to have to revamp the way that we have tariff structures, electricity rate structures, so that when data centers come to town, they have to cover the costs of the grid infrastructure upgrades that they cause, and they have to give some certainty for how long they're going to use this amount of power. again, the more flexible a data center, the more leeway there is to bring that data center in without a very restrictive and penalizing tariff structure. So I think we all roads lead back to Rome, or all roads lead back in this case to load flexibility. It's the only way to align the competitiveness of the United States on building out AI explosively and making sure your grandma's rates don't go up, making sure that there isn't a societal revolt against the entrance of AI data centers.
Thanks, Varun. Dr. Peng, the question on policy frameworks was elegant. Good grid citizens, I'm gonna keep that one for later. Could you comment on your side at least? I know you talked about maybe data centers isn't necessarily where your focus is, but we're talking about policy frameworks to reduce the carbon intensity of these systems on the power grid.
Yeah, for sure. Yeah, I think there are many perspectives, like the policymaker or the regulatory body can be involved in terms of data center or AI deployment. For example, right now, to my knowledge, I think for example, like the carbon footprint or the total emission of all these facilities are not mandatory to disclose, right, based on the current policy. So maybe we can consider about to encourage the industrial company to disclose all the data and make sure that the model they develop is efficient and not like just for increasing 1% of performance and then sacrifice a lot of carbon or produce a lot of pollution behind that. For example, like train really a lot of new foundation model, etc. So I think that's the one things that policymaker can be involved and encourage. And another perspective is I think there is some social disparities and environmental justice issue behind that because most of the energy generator facilities as well as the data center are built in the neighborhood that with lower social economic status. And we all know that all these facilities produce pollution like noise, air, and water pollution. So that will make the case worse because they're already in a kind of higher, the area have higher pollution compared with the area that have higher socioeconomic status neighborhood. Yeah, so I think these are the things that government or the policy can be engaged with and improve the sustainable issue that brought by the AI development. Yeah.
Thanks. That's certainly an important component, the environmental justice impact on these communities. And sad reality is that once this infrastructure is there, it's there for a long time. And what we're seeing, as I mentioned in the opening remarks, is that some of these facilities are staying on longer because of the need for reliability or you see reliability must-run agreements and other impacts that are keeping this infrastructure on longer and efficient in a way just to meet that demand because there's such an interest. So you see some of these climate objectives maybe taking sort of a back seat. So what I really want to focus now on that topic, though, is energy efficient infrastructure. So once you have that in place, how can we make them a little bit more efficient, given that they're there for decades or even longer? So Jun, maybe on your side, the EverSource, but infrastructure, you could comment on that if there's goals or objectives that EverSource is working through right now.
As for the energy efficiency, I think in many of the utility companies, they are having the energy efficiency department trying to use different strategies to improve the efficiency. Like at EverSource, we are talking about a different diversified energy supply for some localized solution. And another thing is for the outage management, that is to reduce the downtime of the electricity and then to improve the efficiency. Another thing is for different of the power flow study that on the optimal side and to improve the dispatch and using the technology skill side to enhance the efficiency. Yeah.
in a little bit too, and grid enhancing technologies too. Is Eversource currently looking into those as well?
Which technology? I'm sorry.
Grid enhancing technologies.
Oh, yeah, definitely. Yeah, like last year we got a DOE funding that is to take advantage of the DLR, dynamic load reading. Yeah, then in one of our transmission line, this is the special point of this project is that this line is connecting with our first offshore wind project in Rhode Island. And so like we want to study that how this DLR technology that can be used when like you have the high load demand and on the one hand, and on the other hand, that the wind generation, that wind that is fitting in, then how this is to be used to relieve the pressure of the grid. Yeah.
Thanks, Jim. That was well said. For other panelists, talking about energy efficient infrastructure. So any comments there? As I mentioned earlier, some of these assets are there for a really long time. And Peng mentioned the environmental justice impact. So maybe a comment on that one. I do want to get some questions from the audience, so this is your warning.
All right, I'll go fast. It's really important in my mind that we shift the paradigm away from just blanket energy efficiency, which of course is important, right? It's important to save the planet, that we try and be as fastidious about our energy use as possible. But, you know, I was just in Texas, and you try telling a Texan that they should do less of something. You know, the burritos are bigger, the cars are bigger. I want to shift the discourse away from blanket energy efficiency to utilizing the system most efficiently. Because actually, there's plenty of capacity, for example, on power systems to provide power, to provide delivery capacity. Think of the grid as like a highway. I don't know what the big highways are here in Boston, but Massachusetts Turnpike, is that a thing? Think of a highway and assume that it's only utilized really heavily, like there's totally thick congestion 1 hour every month. That's kind of how the grid works, right? The rest of the time, that road is very available, and the grid is the same way. So if we can better utilize the existing capacity of grids, we actually make it possible for everybody to make money. We help economically productive uses of data centers, that asset that's going to live for 20 years, we're going to sweat it more. We're going to get more value out of it because more companies are going to build their amazing ChatGPT models and use them. The utilities are going to make more money because you'll be able to sell many more kilowatt hours. And your grandmother will save money because there isn't additional infrastructure going in to service the economically productive uses of energy. More efficiently using electricity grids and electricity generating infrastructure rather than building new infrastructure is the best way for us to align our economic goals and our cost containment goals. That's what I want to talk about. System-wide efficiency, not asset-level efficiency.
Thanks. I do want to talk a little bit, one last question for the panel, and then we're going to open it up here. What's something that the public just isn't aware yet or just has plain wrong about the issue with low carbon AI with data centers? What is something that maybe they wouldn't know or haven't heard just yet?
Okay, from my experience of developing the application, the first is that, do you think that we are the AI ready? Okay, this is the continuation about
I don't want to answer that.
my talk about the data and that I decided that we first that garbage in, garbage out, right? Second, that we are not taking advantage of the data, and that only 10% of the data is being used for making the decision. How we can involve more and more data and also the data quality. This is for the second is like another question is the Gen AI or large language model the best? Okay, so this is when we trying to solve the practical problem and develop the application for our users. This is the first question we are thinking about, like we are going to use the large language model, or we just use some linear regression or curve fitting can solve the problem, or computer vision and NLP, natural language processing. this can solve the problem for one hand, and another hand, it can have a huge saving of the energy and without using the large amount of the parameters, the large language model.
Thanks. Question again, Shelley, I'll turn this to you. What is something maybe that the public or just general folks don't have an understanding with, or maybe it's a common misconception on their part with the issue you're talking about?
So yeah, I think the climate part has been fairly or relatively well recognized by the public, but some of the regional impacts like the water consumption and also the air pollution has not been well understood. For example, the Executive Order 14141, which is about advancing the U.S. leadership in AI infrastructure, mentioned the cancer risk when prioritizing the data center locations. So this is definitely suggesting a connection between the data center and the total potential risk of cancers. And also these air pollutants are actually traveling hundreds of miles. So many people think if I don't live next to a data center or power plant, I'm immune to these air pollutants. But actually, no, these air pollutants are really across the state lines or county lines. So the pollutant that we breathe in could be coming from those data centers many hundreds of miles away. I think this type of regional impacts is relatively less understood by the public.
That's a great answer. Peng, I'll give you the last word on just the common misunderstanding of the issue, and then I want to open up for audience questions.
Yeah, I just want to add on like a simple point is that I think right now the community was not really engaged when develop new centers or facilities because I already heard many news from the local residents that who have this facility near their neighborhood. There are some transparency issue behind, I think, maybe from profit or maybe the current policy is not restricted or something. But I think that's a issue that the broad public is not aware, but the local community have strong concerns. Yeah.
Thank you. Better answers than I wasn't even sure where that was going to go. So fantastic. Okay. We have some time for questions. I want to say maybe 4 or 5 minutes in the back.
Hi. Yeah, thanks very much for the panel. I have a question for Peng and Shaolei. With regards to these health impacts, be it noise, be it air, or other pollutants, what is the research on how to improve that, right? Like you've talked more about understanding the situation, but is there also research on how to improve the technology?
Shelley, I believe that was
okay.
to you.
Yeah, maybe I'll go first. So yeah, of course, understanding that's just the first step. The second step is we can modulate tap into our demand flexibility, either the IT load or maybe using some of the on-site resources like battery to modulate our load. Because when you use the resources or the power system, when you consume the power, will be greatly affecting the amount of emission you generate into the air. Yeah, because similar to the carbon intensity, which is varying over time, this air pollution impact is also changing over time. So when we use the resources, will be very important for the amount of health impact. And also where we choose the data center location, that's also important as well. Different places have different clean fuel mixes, different wind direction, weather patterns. Those will all play a role in the final health impact on the region.
Yeah, the time impact that hits home for me, because if you go to any sort of HISO or RTO website at random different times of the day, there's different fuel mixes based on the time of the day. So it could very well be less carbon intensive based on when these things are being run. Peng, I think you were asked a question as well.
Yeah, I think that's a very good question, but I want to point out that the greenhouse gas emission as well as air pollution or water pollution, they are not a unique problem for data center or AI development, because we have been used non-renewable energy for 100 years, right? So scientific field definitely have some scientists working on that part to mitigate or control the emission of pollution, like especially the peers from the environmental engineering field. So people and the academia have been working on that, but there are some unique perspective that I think the AI industry can work on. For example, is the the sustainable GPU design, as I mentioned earlier. So there are some other perspective I think the AI industry can work on to make a better sustainable future that lead from the AI development.
Thank you. I believe we have time for one more question. Gentleman from the right over you. White shirt.
Oh, you had a voice from earlier.
I mean, I can yell. Thank you to the panel. My question will be really quick. So earlier it was touted that, you know, we have small modular reactor technology, but we also have geothermal, which has been like a very interesting emerging like renewable energy like part for data centers specifically. I'm curious, like one of the reports I was reading, it was either out of DOE or another government agency, noted some issues with scalability when it comes to geothermal in the United States. I'm wondering like what are the panel's thoughts on scalability of geothermal and also feasibility moving forward in actually making it a viable alternative energy source for data center development in the United States?
Sure, I'm happy to jump in. Look, I actually am super bullish on advanced geothermal, both from the technical side and the political side. Look, there is only one, maybe two clean energy technologies that I've heard our Department of Energy Secretary Chris Wright laud. One of them is nuclear. The other one's geothermal. Geothermal has the advantage that the workforce for the next generation geothermal industry can come in large part from our existing oil and gas industry. And on the technical side, there are these companies like Fervo Energy that harness the drilling advances on the oil and gas side, such as fracking, to make next generation geothermal far more widespread and scalable than what we call first generation geothermal, which depended on finding that perfect reservoir of hydrothermal rock. Go to Yellowstone, you will find great geothermal energy, but what about the rest of the country? And it turns out that if you use fracking and you're able to do hydraulic fracturing, horizontal drilling, you're able to actually liberate heat within the Earth's surface much more effectively over a much broader swath of terrain. So geothermal makes sense in like half the United States if you use these next generation technologies. Now, you're right. It's going to take some time to scale it up, right? I don't expect to see AI data centers running off of next-gen geothermal at the gigawatt scale for another decade. But I do think that in the long run, that's kind of category one of the four strategies I gave is clean, firm, dispatchable resources. It's going to be a really important one. We just have to Andreas's point, harness the low-hanging fruit, harvest the low-hanging fruit in the near term before we get those longer-term strategies off the ground, or should I say out of the ground.
Or organizers, we have up make an executive decision. One more question in the front.
Thank you for the session. It was very informative. But then I have a question for you, Varun. As you mentioned that we should shift our focus from individual energy efficiency to system-based, what do you think are the main barriers that will come into for, making the grid more smarter?
This is a great question. I think we need intelligence at all levels. So as Xiaolei mentioned, we're going to need intelligence at the data center level. The data center has to be able to intelligently orchestrate the operations that it has to, for example, reduce its consumption or even increase it at intelligent times. But beyond that, it needs to know when to do it. So intelligence at the grid layer, the complement, needs to be there to operate the grid in a manner that says, look, I need to send dispatch signals to my assets. I think it's that confluence. So and that's at many levels of the grid. You're going to need it at the distribution level. You have these companies like Camu Energy that develop these DERMS platforms, distributed energy resource management systems, DERMS. You have companies and technologies at the transmission level. You have these kind of master grid planner technologies. All of them need to work together. So I think to your question, intelligence at every level of the grid is going to be important. And these days, we should be including the end user as one of those appendages of the grid. They have to have intelligence too. It's not good enough anymore to have what I'll call a dumb load, a load that says, I'm going to act just like you act when you walk into a room and turn on the light switch. You don't really know what's going on in the grid. It's no longer okay for loads to act that way. They also have to be intelligent at the grid edge.
I don't that. Yeah, this is talking about the system level integrated. I'm not an expert, but we have a team in Eversource and the member he is also here. They have some ongoing work that is for the integrated planning, that is to plan the electricity and the gas together, and also load, so that you get a more efficient way for the overall solution, for the network solution. Yeah.
Thanks very much. I think that's all the time we have for this panel. So let's please give a round for applause for our panelists. Thank you so much. Thank you all. Thank you. Photo.
Thank you to our wonderful panelists. We'll now proceed with a short break. Please make your way back here for a prompt start at 2:10. Thank you.
Thank you. Thank you. Oh, thank you very much.
Okay.
Advocate. And do you advocate for but now the second is that head of education. So you often like only yeah, I got it.
There will be someone to talk.
Okay. So what's your yeah, I guess yeah, they're 2010 to 2018. It's must always kind of on this side. It's just a game of organically as you post on
Alrighty, let's get started. So right now we are heading towards our third panel, and we'd love to invite our moderator, Professor Gage Hills from Harvard Seas, to start the whole conversation. Yeah.
All right. Thank you, Jerry. Also, do we have Olivier online?
Yes, I'm here. Yeah. Hello,
beautiful.
guys.
Let's get started. So my name is Gage. I'll be moderating this panel. I'm very excited for this panel because I am a circuit designer. So I identify with things like electrons and transistors. And I spend most of my time thinking about what future computing systems are going to look like. So my background is more on the sort of electrical computing system side. So designing things like the logic gates and the adders and multipliers and memories that we use inside our integrated circuits to do computing. And then you get hundreds of thousands of those or millions of those, you know, connected in racks of graphics processing units in data centers with a bunch of communication links between them. So I think this panel is going to be very exciting because we have a sort of range of expertise of people that are also thinking about what future computing systems are going to look like, both using what I would call these like electrical technologies, like sort of the transistors that we use in our logic gates today, but also some of the optical or photonic technologies for things like communicating data. Obviously, light is very fast, so it's great for communicating data inside data centers for these large-scale AI workloads. Maybe even doing computing in the optical domain, manipulating photons to actually perform computation instead of using our transistors and logic gates. And then even farther into the future, maybe, I think I'm justified in saying that, some of the quantum computing systems. So we have AJ Joshi, who's I think also has somewhat of a similar background to me in the energy efficient VLSI, also some photonic communication, computation, memory. We have Olivier, who I met this week, also had a very exciting conversation with, who's working at QEI, the Quantum Energy Institute, and also has some background in the high performance computing. So I think he'll have some great perspectives. And then Pedro, is it Lopez? Lopez is also here representing the far future of quantum. So I think this will be a very exciting panel. We'll go through probably about like a 5-minute introduction from each of us. I'll go first because I'm the moderator and I get to pick. So I'll give it a little bit of the sort of directions that my research group at Harvard is working on. Then I'll pass it over to AJ, and then Olivier, and then Pedro last. So me, so my research group at Harvard, we have about 8 PhD students working on these future of electronic computing systems. So you might have heard about things like Moore's law or like Dennard scaling, like slowing down, sort of referring to the fact that as we're making transistors smaller and smaller, they're no longer giving us like the same level of energy efficiency benefits, where we get these sort of diminishing returns. As we're making the transistors smaller, they're still getting better, but the rate at which they're getting better is slowing. So it doesn't mean that the electrical computing has like saturated. It just means we have to be smarter about how we integrate technologies moving forward, or like the ways that we're getting the performance benefits. It's not just by scaling the transistors smaller and smaller. And one of the key areas that you might have heard about some of these things is sort of related to these large-scale systems that we design today, like a large-scale system being like a data center or something that has literally like hundreds of thousands of interconnected chips. If you look at where a lot of the performance bottlenecks are in these systems, is actually not just in the computing, like once the data is inside the chip itself, but it's in all the communication between the chips and the memories. Because even like I said, light is really fast, but light is actually not that fast. I always end up saying this, and I don't know if it's the right thing to say, but light goes about, it's like a 30 centimeters in a nanosecond. So if you think about like how long it takes to get to the other side of a data center, which might be like 100 meters away, that's many nanoseconds. And when you think about nanosecond relative to like the clock frequencies or integrated circuits, our clock frequencies are on the order of like gigahertz, right? So gigahertz is 1 billion times a second. So that's like computations happening every nanosecond, right? So like even just to communicate data like at the speed of light is a very big performance bottleneck compared to the rate that we're computing stuff. So a lot of the innovations in these electrical systems is in these sort of like 3-dimensional integrated circuits, where you actually try to take like many chips and like stack them like directly on top of each other. So they're like as physically close to each other as possible. So if you've heard about things like the HBM, like high bandwidth memory, is like 12 DRAM chips, like memory chips that are literally stacked on top of each other. And then those would be packaged on like something called like an interposer, which is like a bigger chip that you put this stack of DRAM chips on the same bigger chip as like a graphics processing unit. So a lot of this stuff is not even really just making the transistors smaller and smaller, but is just getting them like physically closer together. And then also you want to have very tight integration with some of the like photonics for communication. So how does this relate to all this, like Green AI Summit? Well, of course, all these things have implications on the energy consumption of these integrated circuits. And, when you look at energy, right, that energy has to come from somewhere. Ideally, it comes from some kind of renewable source, right, like wind or solar or something like that, but it might come from some non-renewable source. And the other thing that we are working on a lot is that as these systems are becoming sort of more and more heterogeneous, right? There's like more and more pieces that we're connecting in these like three-dimensional circuits. These systems become sort of more complex to fabricate, to like physically manufacture. And that carbon footprint, there's a carbon footprint that's also associated with the physical manufacturing of the integrated circuits. And once you start getting like different types of materials for these like three-dimensional integrated circuits, you might need different types of semiconductors. You might need different types of materials for like lasers and like photodetectors for communicating stuff. You might need different materials if you're integrating some kind of quantum thing, and I don't know anything about quantum, so I'm excited to learn about that. But yeah, so these are some of the things that we're thinking about, like even just in this, you know, boring like electrical compute, right? There's still a lot of room for innovation there, both in just the energy efficiency and then also related to these like resources, like energy, carbon footprint. You know, what kind of waste are you producing when you're manufacturing stuff? Is that toxic? Is that getting dumped into the water? Are people drinking that and dying? So with that, I'll pass it over to AJ.
Hi, everyone. I am Ajay. I'm a professor at Boston University, and I also work as an architect at Lightmatter. You may have heard about this company, founded by folks at MIT, and I just help them on the architect side. I didn't have enough things to do in life, so I also started my own company in cybersecurity. If you're curious, happy to talk about that at some other point. But following up on what Gage said, so I started my journey as an electrical engineer, designing circuits, happy to use Cadence. Some of you have had experience with Cadence or complained about Cadence. And then over time started looking at photonic communication, primarily for chip-to-chip, on-chip communication. And we did some good work with the argument being that communication is a bottleneck. We need to get data from memory, then bring it to compute. So let's make that efficient. And we thought, okay, done, nothing more to be done here. The AI rise hadn't happened at that point. And I started working on other things. And then this small company at that time called Lightmatter reached out to me saying, hey, we are building photonic computing systems. I'm like, what are you talking about? I thought that particular field was pretty much done and dusted. Some of you may know that back in the 80s, there was a big push, 1980s, there was a big push towards building photonic systems, photonic computing systems. Unfortunately, the form factor was not practical. To perform simple addition operations, you required a big optical table with a whole bunch of lenses, mirrors, laser sources. Sounded nice, sounded a nice science experiment, but not at all practical. But over time, a lot of good work happened in the area of photonic integrated circuits. And over the past, in the past 10 years or so, there is a renewed interest in photonic computing. And so yeah, I started working at Lightmatter. We started exploring different architectures based on different devices. So one observation or one thing we all were aware of is that photonics can never replace electronics. At least I don't see that happening in the near future. Reason being that we all are too deeply embedded in CMOS. There are a whole bunch of investment in CMOS, and also there are some fundamental barriers to using photonics. But photonics is very good at certain things. For example, if you want to do gem operations, photonics is very good at doing that. And thankfully, with the rise of AI, where 90% of the operations are gem operations, we saw the opportunity and said, okay, let's at least replace those gem operations perform those gem operations using photonics. There are these nonlinear operations, I understand, they still need to be done in the electrical domain. So the opportunity here is not just photonic computing, it's electrophotonic computing, I would say. Still, electronics is not going away, it has a role to play. So that's one part, but the piece about moving data from memory to these accelerators, electrophotonic accelerators still holds. So there's that other piece that I had worked back in the days that came back into focus, saying that now you need to think at a larger scale. It's not just your individual chip, right? You need to think at a data center scale, because training your AI models typically happens at a data center scale, or even inference happens at a data center scale. And how are you going to ship all that data back and forth? So that's where these novel photonic networks came into the picture. In particular, my work with Lightmatter involved looking at wafer scale network switch. Some of you may have heard about the Passage line of products that they have. So we have one product that should be available this summer, another one available next year on more than 100 terabits per second bandwidth. And so you can easily house a whole bunch of GPUs on top of the interposer, get high bandwidth communication between the interposer, accelerate training. And so that was the second piece where it's like, oh, great, now we can do photonics. And then I started wondering, wait, we also have to store memory. Can photonics play a role there? And I was immediately shot down by the photonic device designer saying that you can't store data in the photonic domain, just not possible. And I said, yeah, that makes sense. But can I somehow manipulate stored data using photonics? And that's where the third line of research came into the picture, saying that if you think about phase change material, you can change the state of that phase change material using photonics. And that idea can then be leveraged to read data or write data into that phase change material-based arrays. So essentially, the idea of not storing data in photonics still holds, but you can still manipulate data in using photonics. So that way you don't have to convert to a different medium, say electrical medium, write the data, or electrical medium, read the data. You can still live in the photonics domain for the whole time. So all three pieces, communication, computation, and storage, all three can be done using photonics in some sense. And everything was working out nicely. And then I came across a paper written from David Brooks' group here in Harvard about ACT, saying that, hey, embodied carbon is the one that has a problem. All this work that everybody's doing on operational carbon is great, but that is not going to be enough. And so we said, wait, are we making a mistake here, right? We are maybe looking at the wrong problem. So we started looking at embodied carbon for photonics, and we worked with AIM Photonics on this. And interestingly, the process for manufacturing a photonics chip is much simpler than that for manufacturing a typical CMOS chip. Reason being that the number of layers that we need in the photonic integrated circuit are less. Materials are different. The size of these devices is much larger, so your yield is higher. So essentially, the embodied carbon for photonics chips is lower than that of an electronic chip. And so we realized that, wait, this is a nice win-win situation. We are reducing embodied carbon because the manufacturing process is simpler. And also we are reducing the operational carbon because photonic computing, photonic communication, photonic storage is more energy efficient. So a nice win-win situation, which is readily applicable to today's data centers. So it felt almost like a nice, a perfect storm brewing where AI was pretty much dominating. They needed high performance compute. They needed energy efficient computing while making sure that they don't use up all the energy resources. And so they are deploying photonic computing, photonic communication, and photonic storage to support these AI workloads worked out well. And that's where we are doing now. I have these projects both in my lab at BU, and also I work with Light Matter. And this is my personal opinion, not Light Matter or anything, but I do think that photonics will have a big role to play in AI data centers in near future. Primarily, most of it being from the sustainability angle, because I really believe we have an opportunity here. So that's my take on how we can make AI data centers greener.
All right, thanks. Very interesting. I also have some questions, but let's hear from Olivier. You can hear us, Olivier, right?
Yeah. Can you hear me?
All right, yeah, loud and clear. Go for it.
That's cool, yeah. So, by the way, the I of QEI stands for initiative, not institute. We're still just a community, not a kind of organization, a formal organization with a building and an institute, but whatever. So I'm a software engineer by training. I've been in this industry for about 40 years now. And I started getting interested in quantum computing about 7 years ago. And now I'm teaching quantum computing in various places, in universities and with customers and with many different organizations. And when I started getting interested in that field, I found that potentially quantum computing could bring a lot of advantage. Of course, this potential computing advantage, it provides a potential capability to do stuff that you can't do classically, typically doing chemical or material simulations that are not accessible to classical computing, even with the largest NVIDIAs of this world. And interestingly viewed from the bridge, quantum computing could potentially bring some energetic advantage compared to classical computing, at least when you look at the theory. I mean, when you look at the basics of quantum computing, it's reversible computing, more or less based on Bennett's work from 1973. It's using massive parallelism, even beyond what you could do with a GPU. But I mean, you can't say there is a definitive answer to this potential energetic advantage. It's still an open question. It's involving a lot of theoretical academic research and even down to engineering done by industry vendors. And the reason why it's still an open question is that to deliver the promises of quantum computing, you need to build so-called fault-tolerant systems. Maybe Pedro is going to talk about this from Korea. When building the systems, you need to increase significantly the number of physical qubits you use to create so-called corrected qubits. And it creates a significant overhead that you don't find usually in classical computing. So usually the overhead you have in telecoms is a couple bits, a couple additional bits. The overhead in storage is maybe you double the storage size with a RAID 5 in data centers and stuff like that. In the case of quantum computing, the overhead is a couple orders of magnitude. It's between 1 and 5, depending on the technology and depending on the type of qubit, atoms, ions, electron spins, or photons, and so on. So as a result, with a group of colleagues from the academic world, I should mention them. One is Alexia Ofev. She's based in Singapore. The other one is Robert Whitner. He's British, but based in Grenoble in France, so it's very international. And we've got people involved in all continents, Australia, Asia, South and North America, Europe. And we created this initiative as a community 3 years ago to look at this problem. So it was a kind of preemptive approach to make sure that both the academic world and in industry and space were looking at the energetics of the systems as early as possible in the design stage to avoid, putting us in the shoes of maybe some folks in the AI world today who are discovering that AI is consuming a lot of energy, particularly with LLMs. So we want to avoid getting in that situation. So that's why we created this. And so far, there were some paper published. We organize a workshop every year. The first one was 2 years ago in Singapore. The last one was in France last January. The next one is in Barcelona, Spain. It's a very sunny place if you like it, in April next year. And so we are starting also to work with industry vendors to make sure that we do 3 things. One is to provide some kind of methodology to assess the energetic cost of those systems. The second is to find a way to benchmark it. And the last one is to find methodologies to optimize the energetic cost. And it's a very complicated problem. Gage, it's connected to stuff you mentioned. Electricity is also involved. Photonics is also involved because you've got a lot of overhead coming from control electronics, from lasers, from a lot of devices, which are mostly classical, and where you need to optimize stuff. And then you have cryogenics also as well in most of the modalities. So we need to optimize very complicated systems. And it involves, a huge industry. Tens of vendors, hundreds of academic teams to make sure that we address that issue. So that's for an introduction. I will answer your questions later on.
Thanks. Yeah, very interesting. Yeah, Pedro, you want to also follow up on the quantum stuff?
So since we're on topic, right, I try to synthesize a little bit everything. So again, nice meeting everyone. My name is Pedro. I'm a quantum scientist and head of education at Quora Computing. So we are a startup. Well, by now, not so much of a startup. Missed Olivier visit last week or two. Sorry, Olivier.
Yeah, it was earlier this month. Yes.
That's right. Yeah. So this company is coming out of a couple of labs from Harvard and MIT. And so if you take this road here and you walk until the end, like a couple blocks, and then you take a right and you walk for another 30 minutes across the bridge, you'll find that there's a company there that right now at this moment is taking a bunch of laser lights, kind of coordinating that at a microscopic scale, and using those laser lights, kind of individual laser beams, to hold individual atoms in place. Individual atoms, it's like one atom. So if the transistor is small nowadays, the atom is smaller, right? And these are rubidium atoms. You hold them in standing like a space with laser light. So light is not like lightsaber, right? Like lightsaber is straight. Light actually has a waist, right? This waist is what some people call the focal point. Right? So the focal point, you can use that to hold things. Some biologists use it to hold cells and do even surgery inside a cell. We use it to hold atoms, and these atoms are flying in space, and we are shooting more laser on those atoms and doing calculations with those. And it's all very exciting. It's happening kind of quotidianly, every day. You know, you can access it to our machines on AWS, and we are building new machines. But despite the inspiration of that, these machines are actually quite clumsy, right? So the atom is small, but holding this atom in space is actually quite big, and should be about 1,000 times bigger than a transistor nowadays, or more, about 1,000 times. Also, the speed of this is very slow. So the speed of a quantum computer at a best scale. So just moving from these two sides, right? Like it's the size, clumsy as the hardware, the photonic hardware was expected to be, if not worse. Speed, best estimates is that quantum computers, fault tolerant, like Olivier was saying, would be about 1 billion times slower than classical computer, 1 billion, like 10 to the 9 times slower than a classical computer. So why do we care, right? What makes this topic aspirational is that the way of doing computing, the logic, the information manipulation is completely different. And that's what kind of justifies us building these machines, despite them being clumsier, slower, bigger, is because it's the one kind of a value proposition that I know in computing today that changes the game. The rules are different. You don't do calculation anymore using standard kind of irreversible circuits. The circuits are reversible. Everything changes. You have to deal with probability, with a bunch of stochasticity that happens in the small kind of quantum world. When we say quantum, we're talking about things that are small and isolated, right, and code. And the rules are completely different, and so different that there are certain problems, like the most famous one being this factoring problem that lies inside RSA, so the standard of cryptography that most technology uses. There are others, but it's definitely still widely adopted. Could be broken within a time scale, like any message of that. The estimates today range between a few hours, maybe 8 hours, to a few days, maybe like 5 days, right, for breaking those encryption methods. And this is something that with a classical computer, even being 1 billion times faster, would take you like the age of the universe or something. So from an aspirational perspective, it's very aspirational, right? Quantum computing, we don't know exactly how this is going to work. We don't know exactly what are going to be the actual applications. Definitely these things can do any calculation. Definitely they shouldn't be used to do any calculation because they are, as I said, clumsy, and for the wrong problem, they will only slow you down. They will not speed you up. So they're extremely purpose made. And finding out what are those purposes is kind of one of the holy grails of the field. Finding out how to build them, finding out how to use them. Both questions are kind of open and in development. Yet, the field has advanced tremendously from like the past 5 years that I've been involved, and from the past 15 years that I've been working as a physicist. The whole game has changed a lot. Questions like the issue of energy and sustainability in quantum have started to pop up. So if you can solve things in a way that is new, could that, at least in principle, save you in energy? So reversible circuits, they should be more energy saving, at least philosophically. They are supposed to be more efficient, but now you have all this gadget around it and all the classical computing that goes on top of doing your quantum computing. So we will be saving any energy at all, and estimates say that not really, but as Olivier said, there's no final definitive answer. That if you ask two different people in this field, you hear different answers. Definitely, that's the answer that I give right now, and tomorrow I might change my answer. So happy to have more conversations around these topics, and yeah.
Thanks. So I probably have a couple questions just to get the discussions started. But then I think we also want to hear from you guys. So maybe, I don't know, a couple questions and then the last 20 minutes or something for opening up to the audience. But I want to start by maybe touching on something that Olivier mentioned, sort of thinking about this holistic optimization of the entire system. right? You talked even about like the energy that it might take to cool a data center or some kind of quantum system, all the energy and circuitry that you might need for like redundancy in quantum systems. Olivier, we also talked over Zoom this week about the different sort of material platforms or different options for actually making physical qubits, which in my understanding has not been fully decided on in the community. So I guess my question is, how much of a role do you think that thinking about sustainability and like carbon footprint or toxicity or manufacturing will actually play in the development of these like future technologies? Like, is it something that would actually change how we decide to develop the technologies moving forward? Or are we going to end up in a similar situation as I sort of see our large scale computing systems today, where the sustainability was kind of like an afterthought, right? Like we set up all our fabs, these cost billions of dollars to set up. We start just churning out chips out of them. And then we say, oh, okay, well, this is the embodied carbon footprint of like making chips. So I guess that's my question, maybe to start with Olivia is one, should we do this? And two, like, do you think that this will actually happen, or practically will it end up just being like another afterthought after technology?
Yeah, I think it's a chicken and egg problem, because I mean, the fact that we created a QEI and other, academics and industry vendors are talking about this, it rings a bell. I mean, people are listening. We hear also the huge energy consumption coming from AI-based data centers. So, I mean, there's some kind of eco-responsibility that pops up in the minds of even entrepreneurs in that space. But what I would say, coming back to your remark on the great variety of technologies around, like the cold atoms, ions, and others, is it's really amazing. I mean, there's more differences between the different types of quantum computers than between two GPUs from, let's say, from one from Cerebras and one from NVIDIA or from GraphCore. There's a lot of differences. The controls are entirely different. And what I found out in my own work is that, I mean, current systems don't consume a lot. I mean, if you take a current QPU, like we call it, a quantum processing unit, from Quera or from IBM, from Google, from Weaver, Candela, and others, it consumes a couple tens of kilowatt. So it's about the power of an NVIDIA rack, not more. But that's what we have right now. But the systems we have right now are not more powerful most of the time than an NVIDIA rack. So that's why the comparison is useless. What's interesting is to look at what's going to be the weight, the cost, the power footprint of those systems when they scale up to do stuff that's not possible with classical systems. And when you look at the technology and when you look at the various options in each of the technology, what's amazing is the ratio between the low energy footprint systems and the high energy footprint system is about 2 orders of magnitude wide. It's from 1 to 100. And it's both CapEx and OpEx. CapEx for the cost of the machine, including the hardware that you have inside, and OpEx, which is mostly boiled down to the energetics and the power consumption. So it looks like if we advertise that, if we show that there's this discrepancy between let's say the good, the bad, and the ugly, it will, probably drive some innovation. It will push some vendors or some so-called enabling technology vendors to improve their systems. What I can also observe is the interconnect between the energetic footprint of those systems and their potential market. And it may be weird. And I even don't talk about the so-called Devon's effect that you may know, when the more you save energy, the more you consume, and blah, blah, blah. So just looking at the market scale. In the case, let's take the case of superconducting qubits from IBM, Google, Alice and Bob, Norquantic, QCI from Yale. Those systems, the energetic cost is mostly at the cryogenics and control electronics level. But the control electronics we use right now is very ugly. It's FPGA based, it's room temperature, it's not cooled. And we know that there are some technologies around, even just ASICs, which are way more efficient than FPGAs. But people don't use the ASICs. Why? Because we don't have a volume market. It's not justified from an economical standpoint. So if there was some economical justification, we could have a lower energy footprint. So you see there's an interconnection between the economics and the choices vendors are making. We have the same problem with software. I think a law that's very known in the HPC world, which is the software quality drives a lot of the energy high or down. And it's going to be the same for quantum computing. There's going to be a lot of progress and a lot of innovation to do in the software part, both at the algorithm level, so the design of your solution, and at the compiler and the middleware level. And so you're going to have to interconnect all these software stacks and the hardware stacks, including error correction, to make sure that you save as much energy as possible. And there's going to be a feedback loop between all the different scientists from these different stacks. That's why we need this holistic view, because everything is connected. I don't know if I answered well your question.
Can I jump in a little bit? So just to add a few more perspectives on this, I think that the question, like it was multifaceted. Like there's the sustainability, so there's the energy side, there was the toxicity side, there is like the materials consumption side. They're all different, I guess. And from most quantum technologies that I see, kind of toxicity of producing this is not really that complicated, that's dangerous. I feel like making batteries is much more complicated than that. And also the volume, the demand for that, like Olivier was saying, is not, I wouldn't say that it's big enough that you see factories dumping things in the water because you're making quantum computers anytime soon, right?
Eventually we want to.
Eventually, I don't know, right? Because so it remains an open question whether this technology will ever become a consumer technology, or if this is going to be like, what's the best comparison? Is the best comparison, is it like a GPU, an accelerator? Or is the best comparison is like exascale computing that everybody might have heard of, but probably no one really touched one, right? So the amount of people that need to use it is so reduced, and it all boils down to the question of what are these machines used for, right? So should I compare the carbon footprint or the energy consumption of a quantum computer with that of classical computer? Well, you don't use them for the same reasons. You don't use them for the same workflows. So perhaps they don't have to be compared. Rather, they have to be judged kind of individually against the benefits that they would bring to society, right? Because there will be a cost. It's not going to be a gain. It's going to be a cost. It is already a cost, right? Like you're dumping investments on doing this that you're already not dumping into other things. So the question is it worth it?
I don't know much about quantum computing, but
for the photonics side, right? Like,
so
there's all sorts of materials.
Yeah.
I know silicon photonics is nice to fabricate because we can use all our existing processes.
Right,
but
right.
there's, whether like these perovskite materials or different. I don't know if Light Matter is looking at some of these other photonics platforms.
Yeah. So in case of photonics, it's still a little bit of a niche market today. Photonics is used in a variety of areas, but not at the same scale as, say, we use microcontrollers or processors today. Assuming light matter processors accelerators become commonly used down the line, I don't necessarily see them jumping to a completely new technology. This is just my view, because if it's possible to build something using existing fabs, why set up a new fab, right? And so it just becomes a more pragmatic, cost-saving way of doing things. There are how you interface electronics and photonics does play a role on the cost of manufacturing photonics. If you do a monolithic integration where you're using the same process as, say, global foundries, then you have already paid the embodied carbon price. You're not going to pay something new. But if you're going to do 3D integration or 2.5D, where the photonics chip is built in a separate fab, then you really have an opportunity to build something ground up where you say, okay, this is going to be carbon aware, right? I'm going to make sure that the amount of greenhouse gases that I emit or the amount of energy that I emit in the air, if I can control that, I can reduce the cost of manufacturing these photonic chips. So thankfully, photonics has not hit that stage where it's the train has left the station, as they say. We still have a chance to still have a chance to set up the manufacturing process such that it is efficient. The quantum part, I'm happy to hear that there is not a big market yet. So this is a great opportunity for them to like really do a good job from scratch. And then that way, I don't know, hopefully in my lifetime, if we see quantum computers, they will be like super efficient, very sustainable. Everybody carries them in their pocket would be a great thing.
Thanks. Yeah, I want to, we have about 15 more minutes or something. So yeah, I want to hear some questions from the audience. Go for it. Oh, maybe we'll bring you a mic.
Hello, thank you for the interesting panel. So my question goes, as you were saying, years ago, some companies weren't able to develop further because there was no infrastructure yet or not the timing yet. And now, I don't know, 20 years later, it is. I wonder for the quantum and the photonics industry, what is happening now that it's not given the ability for those two industries to develop further, and maybe 20 years from now, it will be.
I could say from the photonics perspective. So back in the days, let's say back in the days, in the 80s, when everybody was excited about photonics, building a photonic computing system was possible, but the size of the photonic system was huge. So it wasn't very practical. Now, one could argue that didn't we go through the same experience back in the 50s and 60s when electronic systems were like you would occupy a whole room? True, that's what it was in the 80s. And now we are like we have a billion transistor chip, we could occupy like a very tiny space, right? Same thing I envision happening. Maybe I take that. I don't say exactly the same thing, but because the question about photonic device scaling is still out there. I don't think they will scale the same way as CMOS, but photonic devices will become better over time. We will have photonic systems. What changed now is the need, right? Back in that time, the amount of data crunching that was happening was not as much. Now we are crunching a lot more data. So we need more compute capacity, more bandwidth, more storage. And photonics, in my opinion, can help address all those questions. Still need to work with electronics. Electronics is not going anywhere. But that need has created this urgency that we need to explore alternate non-CMOS solutions in parallel. That's where photonics is playing a role.
So if I can just add from the quantum side, there is situation is very different if you ask Google and they're making the superconducting chips and they have to make every single kind of qubit exactly equal. And us that rubidium comes from nature and rubidium all looks alike. For us, what limits us, laser power. You need laser power and you need the laser power to be very stable, phase stable, amplitude stable, everything extremely stable. There's a lot of laser power out there if you're doing laser welding, but those are not necessarily the wavelengths that we need. So unfortunately, the answer is more power, not less power. But yeah, perhaps that's not the answer that we would like to hear. Olivier?
I didn't get the question very well. Was it about the timeline of the innovation in that space? So
I understand that the question is.
Yeah, it was about how fast it is.
What is preventing the technology?
What's preventing? Okay, and you're right, Pedro. It depends a lot on the technology. So if I come back on the solid state qubits, like the ones from Google and IBM, they have significant challenges in manufacturing the chips because they need a low variability. They need to have a very high quality. They don't use the same clean rooms as the ones from TSMC that builds the NVIDIA chips. It's not at the nano scale, even though the nanoscale doesn't exist really in semiconductor chips, but whatever. They use different processes and they try to improve it. So there's a company called Colab that was created by John Martinez from UCSB, a former guy from Google. And he tries to improve the process himself with working companies like Applied Materials in the US. So that's one thing. The other thing is how do you improve all the controls? Like the lasers for you and the control electronics for those guys. And then probably how do you connect everything? One of the key challenges that most of the companies are facing right now is how do they reduce the overhead of error correction? because this overhead is significant. I mentioned a couple orders of magnitude. And interestingly, there are many, many different options around that are being tested, including the famous work from Michal Lukin here in Harvard on shuttling the atoms in space and improving the overhead of error correction, which is one of the ways to do that. Another way to do that is to improve the connectivity between the qubits in semiconductor chips, like what IBM is trying to do. There are other options like companies like Norquantic in Sherbrooke in Quebec, or Alice and Bob in France and Amazon are trying to do, which is to create qubits that are kind of self-corrected. They have some part of a hardware level correction, which reduces the overhead of error correction that relies on a lot of classical systems around. So there are many, many different options. But what I would say to explain maybe why the time scale is long is that it's still experimental. It's highly experimental. We have 90 companies in the world trying to do that right now. They are experimenting new stuff. Most of the companies are R&D labs, actually. They try to sell stuff at the early stage, but really those guys, they are R&D companies. And they do science. They do technology development altogether. They are most of the time piggyback to an academic lab like Quera and Harvard for Michal Lukin's team. And it's the same all over the place, everywhere in the world, even in China. So we are still very early on in the stage of development. One surprising aspect of the quantum computing world, I would say, and it's not connected to the energetics, is that we have more skills and more IP, let's say, in software and algorithms than hardware. I mean, the first algorithms were developed before the hardware was there. So the Shor algorithm was developed in 94. Most of the key algorithms were developed between 92 and 97. Alexei Kitaev for quantum chemistry and others. And the hardware came later. So, but hopefully people are working in parallel, trying to address all these issues in parallel.
Guys, I forgot to mention this in the beginning. So I was going to give a shout out to Anna Noor in the background. I think she also has a question. She did an amazing job bringing this panel together, I think in a very thoughtful way, spanning these multiple technology disciplines. So maybe a quick round of applause for Anna, and then you can ask your question.
Well, that's very kind. Thank you, Gage. Really, really great to see you all discussing this across the different timelines. First, I had a question for Olivier, just to clarify whether the QEI has also started looking at the manufacturing process and the embodied carbon of this, or whether you feel it's still too early because we're not at a scale of really mass manufacturing, and the embodied carbon will come into play later. So just whether or not you're working on that. And then for AJ, from your experiences in the EE and photonics community, what advice would you give to the quantum community to have, be it energy or sustainability, be a primary design metric? What would you recommend?
So to answer you, neither the scientists from the QEI or most of the industry vendors are looking yet at, let's say, the carbon footprint and the product life cycle analysis of these products, because it's very early on. We are still at the R&D stage, like Pedro was saying. I think it's going to pop up later. But one key thing I can mention is, I mean, most of the materials we use in that space, they are very common. I mean, we use copper, aluminum, silicon, even rubidium is not that rare, the one that is being used by Quera. I mean, we don't use so much rare earth like in photonics or in smartphones. So there's less of such a problem. But when we're going to have a very large scale fault-tolerant quantum computers, which may have a very large footprint, that's going to be a question. But those systems, they are in the roadmaps of most industry vendors in the next 10 years at best. So it's very long.
So my advice to them would be take advantage of the fact that you haven't scaled up yet. You have an opportunity to start ground up where you can really think about the sustainability. Maybe think about sustainability first and then think about how you can build these systems, because everybody knows here the more efficient systems become, the more they will be used. So let's make sure that it's possible to build these quantum systems in a very sustainable way. And then start building them at scale. And then I would imagine quantum systems just running over all the CMOS-based systems or photonics-based systems that we have today. I would imagine that will take some time, but take your time, no hurry. CMOS is not going anywhere in the near future.
A last question. Over here, this guy wants it. I feel like he's like jumping out of his seat.
Thank you. My name is Dan Hibbs. I work at the Massachusetts Clean Energy Center. So really glad to be here today. Thank you so much for the lively discussion on quantum computing. My question is, earlier in the day, we heard a discussion on the role of government in regulating AI due to concerns of adverse impacts on society. Are there similar concerns that quantum computing could have adverse impacts on society without sufficient regulation? And what should be the role of government in the development of quantum computing?
Question.
Okay, I'll jump at it. I've been talking to lots of friends that are interested in the topic. Generally speaking, most of the companies are not worried about it yet. Most of the companies are dismissing this because, again, if the problem is so far ahead, even 10 years, like, making law is slow. Hopefully it doesn't need to take 10 years, right, to figure that out. The main places where quantum computing kind of poses any type of threat is exactly because when we're talking about this value proposition of quantum, the main kind of proponent option or alternative for that is exactly in the cybersecurity space. But that actually the government has already done a lot of pre-work on that. There is kind of new standards and protocols for security. These lattice-based methods came out of NIST this year or late last year, by now I don't remember. Those are not as tested as kind of elliptic curve encryption or RSA, but they exist. They are just also more clumsy and also more demanding of classical compute. So it's hard to necessarily put that on any SMS chip for your phone. But I think that the main challenge for regulating that or for answering that is exactly because we don't know what is exactly going to be the main application of quantum computing. Is it going to be materials? There's a little bit of indication that that is perhaps a good direction, better than others. Is it going to be optimization? There is a fair indication that that's probably not a good direction. But every now and then there's something that comes out saying, oh, maybe, maybe. So not knowing what this is useful for makes it very hard to regulate. Right, basically impossible to regulate. That's one of the reasons why that I actually think is an honestly good reason to wait before you start worrying about figuring what are the concerns. But we should keep it in our minds because what happens with AI is serious, right?
I'll jump on that. Yeah. You know that I happen to be European, and you have these nasty jokes from the US about Europeans trying to regulate everything. So I won't advocate for regulating anything here. But I mean, before any regulation, you need to be sure that we know what you're talking about. We need to know about how we measure energy, carbon footprint. So the first thing to do is to maybe create some standards there, and we happen to do that at the QAI level. There's a working group at the IEEE that's working on defining the way you measure the energetic footprint of a quantum system. And by the way, doing this measurement, doing this analysis requires to have a full stack approach, including the classical systems and the classical computers that drive the quantum computer. So we need first to have at least a common understanding of and a good methodology, and then we're going to see what we do.
Maybe just one thing to add, purely from a government perspective, I would say, so the AI race is going strong, right? The quantum race is started, it's not at the same place. So it would be great if the government could help with workforce development. We don't have enough people who understand quantum computing. So getting more engineers or more undergraduate students to learn that technology, maybe do a PhD in that and become future leaders in that area would be a wonderful way for the government to support the effort. And then hopefully we are in a good position when the race really heats up.
All right, getting the indication that it's time to go. But thank you so much for having us. I think this was really fun. Yeah, thank you.
Thanks a lot. Bye-bye.
Take a picture so you got to smile.
We'll now proceed with the short break. Please be seated by 3:10. Thank you. Yeah,
The next generation. Okay, good.
And is there a time? Is there a timer? Where do I look at it? Where do I use my phone? To see how much time? It might have to. So what time? Oh, like 5 minutes. 5 minutes. And what about the microphone? Nice. Use that or stand at the podium. The opposite
Started.
If everyone could please slowly make their way to their seats, we'll be starting in a couple of minutes. Thank you. We will now be transitioning to a series of lightning talks on emerging innovations in green AI. This session will feature a rapid-fire series of presentations from leading researchers and pioneers at the forefront of AI innovation. Please join me in welcoming our first speaker, KJ Joshi, the Chief Business Officer and Head of the Data Center Business at Hitachi. Please join me in welcoming Mr. Joshi.
Thank you for listening to me the second time. So I think hopefully it's going to be a charm the second time. All right. So I've already introduced myself. I think everybody knows me, but for anybody else who's new in the room, I am Chief Business Officer at Hitachi. I am responsible for their data center business. It's about a $2.5 billion business across all Hitachi Group. And prior to that, I worked at Equinix, which is another very large data center operator. And prior to that, I spent 8 years at Dell in the data center business. I've been in data centers for a very, very long time, 23 years. And I am based in Santa Clara, California. So if you ever want to reach out on any data center topic, feel free to reach out. So very quickly, I wanted to talk a little bit about what are the emerging innovations in the AI data center design. And first, let's understand the drivers behind what is causing a different design construct specifically for data centers in AI and how are they different. So let me start with the first element. Everybody's been using this phrase, AI data centers are factories. And what they are, when something is a factory, you need to think about overcoming industrialization challenges, which are similar to building a very large factory. The first thing we need to understand is that computing power is going to be the future labor force. Why do I say that? Because when your car is automatically driven and it takes you from point A to point B. If you go to San Francisco, you will see that Waymo drives you from point A to point B. It's very normal in San Francisco to have a driverless car. If you look at trucks, in the future, they're going to be delivering point A to point B. Today, already, other than landing and takeoff, your plane is primarily driven on its own. It literally flies on its own. There's so much sophistication and automation. So wherever you have more computing power, you'll have more leverage in terms of how you're going to grow your business. This is why US is fighting to really control the number of chips that go to a lot of different parts of the world, the NVIDIA chips, because they want to make sure that the future labor force in the country, which is going to be chips, is actually with the country. And if you see that how they are making sure that some countries don't get it, and it's almost a cartel-like behavior. I'm not a big proponent of it, but that's exactly what's going on. Second, we talked about not enough energy to scale. This has been talked about all day. I probably won't belabor the point on that. And third point is scaling gets harder as the factories get larger. So at some point, it's not economical to really keep building larger and larger. So what is going on? First, let me touch on a point around location. And first, AI factories, because of the power constraints, now are moving to tier 2 and tier 3 metros. You'll see Wyoming, Omaha, Minnesota. This was never under consideration. They're going where the power is. So keep that in mind. That's a pretty big shift in where the business is going. The average size used to be a 30 megawatt data center. Everything in data centers is measured in megawatts. It's now 200 megawatts. And many companies are now talking about a gigawatt data center. A gigawatt is 1,000 megawatts. So it's really getting very, very large, 800-acre campuses, and they are literally like gigafactories. The third big shift that's going on is self-generation. That means the AI companies are looking at generating power on their own. So that's a big shift. Now, how is the electrical system evolving? It used to be 12 kilowatts on a rack. It's now almost 85 kilowatts a rack, shifting to 120 kilowatts a rack next year. Just to put things in perspective, your laptop charger is a 64-watt charger. So when you talk about 120 kilowatts, you're talking about 2,000 laptops working at the exact same time. And that's the power that it draws, a single rack that draws. The other important shift, I think I mentioned in the morning, was moving. Not only are the boxes getting larger from 48-volt AC, they're moving to 480 volts, but they're also becoming DC. So from a design perspective, it's shifting from AC to DC to avoid a lot of losses. And the third big change was when you look at UPS batteries, they used to be next to the servers. Now they're getting outside the gray walls of the data center in the form of very large BESS systems, battery energy storage systems, because the power requirements are so large that you cannot physically fit in a container this size inside the walls of the data center. So now you have to place it outside. So that's the third big shift. On the mechanical side, which is called the cooling, there are three new technologies that are evolving. The first one is rear door heat exchanger, and it uses a coolant, and it basically takes the heat away from the racks, using a coolant, and then it dissipates into that, that fan that you are seeing. The second technology shift from 50 to 100 kilowatts is direct to chip cooling, where you're cooling the chips at by passing the liquid at a chip level. Completely different design. In fact, most OEMs are going to start providing this service. And the last one is around liquid immersion cooling, which is where you put the entire rack inside a liquid. So the server itself is going to be immersed in a coolant, and the whole technology is shifting where so think about how complicated it's going to get when your server is sitting inside a liquid cooled rack. Sorry, some of the fonts are gone a little bit, but one of the things I touched on, in the morning was a small format edge data centers. So we are now looking at building something like this, which is a 1 megawatt data center that you can put in your parking lot, but it will have three distinct modules: one cooling, one power, and one IT. So this also, again, the form factors are shifting around in the data center design. Last but not the least, there are three other big trends. I touched on renewable energy adoption, smart building management, which is systems like BMS, building management, and EMS, etc., and waterless cooling are three areas where there's a significant amount of new technology that are getting introduced. Thank you. I only had 5 minutes, so thanks.
Thank you, Mr. Yoshi. Now, please join me in welcoming our next speaker, Jennifer Cherlick, a practice leader of climate and energy AI at the Martin Trust Center for MIT Entrepreneurship. Please join me in welcoming Ms. Cherlick.
So hi, everyone. Really excited to be here with you all. And today I'm going to be talking about the net climate impact of AI, balancing current costs with future potential climate benefits. I'm practice leader of climate and energy AI at MIT's Entrepreneurship Center and also a mid-career MIT Sloan Fellow Master's candidate. So as we all know, AI is contributing to climate change. There's lots of news in the headlines these days, but AI could potentially also reduce climate change. So which is true? Well, both. Both are true because AI is contributing to and could maybe reduce climate change. So the question remains, is it worth it? Is AI worth it? Just for some background, many of you may already know this, but to get everyone up to speed and on the same page, the last 9 years have been the hottest on record, and it's continuing to increase. And emissions are the #1 cause of climate change. Energy is by far the largest contributor to climate change. Some estimates put it at 62%. And why is this? It's because energy-related emissions come from fossil fuels. 79% of our energy system is non-renewables like oil, coal, and gas, and only 21% is renewable energy forms like solar and wind. And we have runaway emissions. When I was at COP29, it was clear to me that although individual countries have done a great job of reducing their emissions, as a globe, unfortunately, we face a hockey stick of the worst kind. We have runaway emissions. So what technological innovation is needed? According to MIT researchers, we need to improve the technology to transition away from fossil fuels. We also need to increase the efficiency of the energy system, and we need to do things like capture carbon dioxide, reduce methane leaks, and mitigate pollution. Well, AI can actually help with all of these things. It can help us to decarbonize energy. It can help us to do material science discovery to find new innovations. But AI is also hurting our ability to do all of these things. It's using a ton of energy. And energy demand is increasing so fast that the grid cannot keep up. And AI, as we all know, is using a ton of energy. Did you know that a ChatGPT query consumes as much energy as 5 times that of a simple Google search? That is a lot. And in many cases, we can't control whether we're using it or not because it's embedded within search these days. While data centers currently account for varying estimates put it at 1 to 4%, but let's say 2%. Let's say they account for 2% of energy demand. Some estimates put them to grow to 4.6 to 9.1% by 2030, but some estimate them growing as high as 21% by 2030, and that is a huge amount. Well, what if AI could help with this? What if it could help to reduce climate change and to reduce its own emissions? Recent advances in AI, such as neural networks and large language models like OpenAI's ChatGPT, could potentially offer help in this area. Because AI is great for complicated situations. And what could be more complicated than the grid, said to be the largest and most complicated machine in the world? AI can help with energy systems. It can help to do things like better prediction of solar and wind generation. It can help with energy data management and predictive maintenance and fault detection. Just as an example, let's say 10 consumers drive home to their neighborhood with their EVs at the same time, and they all plug in their electric vehicles. This can create what's called a peak load for that area of the grid, where there's a spike in energy demand that the physical grid may not be able to handle. And so this necessitates adding more physical grid infrastructure to accommodate this increasing demand, which is both costly and time consuming and may not allow us to meet our climate goals as fast as we need to. But what if AI was installed at the site? So when the consumers plugged their cars in, AI intelligently managed when they got charged throughout the night, so everyone woke up with their cars charged. This could reduce the need for expanding physical grid infrastructure and those costs and timelines, and could help us move more quickly towards reducing emissions. This is a concept many of you may be familiar with called peak shaving or load shifting, where you shift the loads around. So that's a quite promising application of AI. But according to research from Google and BCG, AI only has the potential to mitigate 5 to 10% of global greenhouse gas emissions. And a recent report from IEA pegged it at 5%. So let's say 5 to 10% reduction potential. So some of you may be adding this up in your head. If data centers grow to 21% of energy and AI mitigates only 5 to 10% of emissions, AI will not reduce climate change. So as part of my work, I've been developing a series of equations to help us measure the climate impact of AI. And of course, this is a bit of a cost-benefit analysis that I think some people are talking about. Recent IEA report covered a bit about, but I think there's lots more room to talk about this because the news headlines are AI is ruining the environment, sucking up all our resources, but then we also have events and reports about AI for climate, and I think we need to focus on a balanced approach of what is it actually going to net out to be. So the net climate impact of AI can be looked at the AI climate harms minus the AI climate benefits at time t. Or if we want to look at it from an emissions perspective, we can look at the net emissions from AI as the emissions from AI minus the emissions avoided from AI. And in both of these equations, it's will it be positive or not? If the harms exceed the benefits, it'll have a net negative impact on climate. If the benefits exceed the harms, it will have a net positive impact, and same with for the emissions. But we also need to consider a couple other things. We need to consider the installed base of chips, because just because new, more efficient chips come out, like the amazing innovation of Google's recent Ironwood chips, which are like thousands of times more efficient, that doesn't mean all the inefficient chips are automatically going to be replaced. Similar to how the introduction of electric vehicles doesn't mean that all the gas cars immediately come off the road. So we need to consider that as well. We also need to consider the time value of carbon, because a ton emitted today is not the same as a ton emitted in the future. And right now, AI is having an undeniable environmental cost, but we haven't reached the full potential of that 5 to 10% emissions reduction potential. So we need to consider that as well. We also need to think about Jevons paradox, which says that efficiency gains can be outpaced by associated usage increases. And finally, we need to consider the positive aspects of load flexibility, being able to use things like AI and data centers to help shift loads around and reduce our emissions. So let's look for AI projects and pathways where the climate benefits exceed the climate harms. And we can also look at a climate AI framework to look for projects that are at the intersection of AI's capabilities, positive business value, and also positive climate impact. So let's work together to make the world a better place, because there is no planet B. And if you're interested in getting early access to my report on the net climate impact of AI, feel free to use this QR code to put in your info. And if you have any questions or want to chat further, if you're working in this space, I would love to hear from you. Thank you so much.
Thank you, Ms. Trelick. I now have the pleasure of introducing our next speaker. Please join me in welcoming Monica Wang, the Deputy Director at the Institute of Industrial Innovation at Shanghai Jiangtong University.
Thank you. Thank you, everyone, and I'm very happy to be here. And I come from Shanghai, and I'm very honored to speak here at the Goodman Conference Center at Harvard University, and to talk about Azure transforming education, innovation, and incubation. Maybe it is a little different from our other speakers, and hope you have a good break. Okay. About me, I'm a serial entrepreneur on AI and education, and also a marathon runner. And the most important, I think, I'm a mother of three. So let's start by looking at how things are changing so fast. It takes centuries in industrial in the industrial age for job changes, and also in the internet age, we see this change took decades. But in AI Azure, we are seeing it just a few years. We see that many leading technology companies are cutting their headcounts, and also it happens everywhere in the world. And also another changes is that the industrial age is centralized work. That age that brought us to work together in factories, in offices, but with AI tools, we see that there are many jobs we do at home-based, and also we can create, collaborate, and contribute from anywhere of the world. And also another chance we see that is this leads to many leaner companies, which are more agile and more efficient. Take Midjourney as an example. It's a very small team with very good skills and empowered by AI. And also we are seeing that the rise of many freelancers and what I call super individuals who can begin their startup alone and with very good AI capabilities and productivities. And also another big change is the business value. In the past, we see that companies are competing, especially on their material value, like products, like infrastructure and scale. But now it shifts to the most on emotional value, especially their connections with their customer relationships and bring their emotion values and something like that. And also we see that what kind of innovative talents we need in the AI Azure. Recently, the Forbes Technology highlighted the top AI talents in 2025. And we see that these talents, they are not only with technical capabilities, but also I see the strong willpower. I mean, passion, motivation, and curiosity about what they are doing, and as well as the mental power, creativity, agility, and endurance. So what kind of education we need in this Azure? I mean, centralized work, it turned education into a filtering rule. I mean, in my age, that education is designed as a filtering rule, a tool for the centralized and standardized work. Like everybody want to go to Google, go to Meta, and as well as BAT in China. But in the Azure, we see that the jobs, the work are decentralized. So the education must evolve. We see that AI is reshaping education. Take my daughter as an example. She's an 11-year-old girl, and she's a typically very I person and talks very little. But last summer, I sent her to a summer camp with AI Hackathon, and she did her first game with AI tools without any coding background. And I see her passion and her curiosity about this thing, and she become very, very passionate about this and become to develop more games. And I think that AI is not just a tool for innovation. It is lowering the barriers for innovation, especially in personal growth. And regardless of background and regardless of location, and also accelerates its timeline. Something we can do like in universities now maybe can do by a 10-year-old girl. So finally, I want to emphasize that no matter how advanced the technology is developed, it's ultimately about people. Life influence life. And as educators, as innovators and startup founders, what is our biggest responsibility is to inspire and empower our next generation. And AI can help us do that. But it's up to us to ensure that technology serves humanity, not the other way around. Thank you for listening. Thank you.
Thank you, Ms. Wang. I now have the pleasure of introducing our final speaker. Please welcome Khan Hakendi, a postdoctoral researcher at Boston University. Please join me in welcoming him.
All right, so yeah, I'm John Hakendi, a postdoctoral researcher at Boston University. I'm mainly working on carbon-aware computing issues. And I think in this talk, I'll be shifting the gears a little bit and talking more about more technical stuff. So there's been kind of a lot of discussions about embodied footprint and operational footprint throughout the day. And now I'll be mostly talking about a tool that we've been working on to estimate embodied footprint and the operational footprint of data centers. So in order to estimate the overall carbon footprint of a data center, we need to first look back at the life cycle of a data center and different stages of the life cycle. So the embodied footprint basically consists of the material extraction and the manufacturing stages. So when we talk about manufacturing, it basically includes the building and constructing the actual data center building, also manufacturing IT equipment, power infrastructure, and also the cooling infrastructure. So all these components basically makes up the embodied footprint. And when we talk about the operational footprint of a data center, it's basically the data center's operation, running workloads on hardware, and then serving user requests. So that's the operational footprint. And at the end of this life cycle of a data center, we have the end of life, where the hardware and also the building are put to reuse, recycled, and then which also have a positive impact on the overall carbon footprint of the data center. But it's really important to understand each of these stages to have a good estimate about the overall footprint of data centers. But I think Jeremy from EPRI was talking about 95% of the data is private earlier today. So that's also one of the problems that we have in doing some sort of sustainability analysis on data centers. So there are these data gaps, and we identify four main actors, ranging from hardware vendors, the big tech companies, data center infrastructure builders, and also the data center operators and the managers. For instance, it's not possible to get detailed LCA analysis from NVIDIA about their GPUs. So it's really hard to come up with accurate numbers regarding the embodied footprint of manufacturing these GPU devices. So this data gaps is the main challenge against coming up with accurate estimations on carbon footprint analysis of data centers. So how do we address this problem? So we built this tool called Carbon Meter. So this is a carbon footprint calculator for data centers, and it requires minimal set of data. So as I told you in the previous slide, we have this problem of data gaps. So it's important to come up with tools that will allow you to estimate carbon footprint with only using minimal set of data. So this tool requires only two types of data. One is the power capacity that is fed to the data center, and the other parameter that is required is the overall size of the data center. So if the user can provide these two numbers, which are mostly available for most of the data centers, we can then estimate how many servers can be employed in this data center. And based on how many servers that you can deploy, then you can estimate how many network IT devices you're going to be needing. And then you can add these numbers up to come up with an IT manufacturing footprint, which is a part of the embodied footprint. So for the operational footprint, there are many adjustable knobs that users can play with, but these are not really required. These are these numbers are usually publicly available. For instance, the energy source carbon intensity is available for different locations, so user can change this number and evaluate the overall carbon footprint for different locations. So for the IT operational footprint, user can also play with the IT equipment lifetime. So the longer the lifetime, you're going to be having a more efficient operational footprint. And then in the end, what this tool does is by just using these two parameters, one is the power capacity and the data center area, it just gives you an overall breakdown of operational versus embodied footprint. So this is a case study that we did for 3 different server models using different operational and embodied footprint distribution. So if you look at on the left side, you're going to see a Dell R710, which is kind of an older data center. Older type of server, which comes with a 400 gigabytes of storage. But on the right-hand side, you're going to see a more recent server, which is Dell R740, which comes with 4 terabytes of data storage. So depending on what kind of a server you're employing, you are using in your data center, the overall breakdown of operational and the embodied footprint is going to be ranging, it's going to be changing a lot. So if you look at an older type of server, you're going to see around 95% operational footprint versus 4.6 manufacturing, the embodied footprint. But if you look at a more recent server like R740, this breakdown is going to be a lot different than what we saw before. So the larger the storage size, the higher the embodied footprint of a server. So this distribution is going to be more skewed towards the embodied footprint. So 65 to 35% is what we expect to see in more recent data centers due to this larger storage servers. So what else can we do with this tool? So one other case study that we worked on is to look at how can we reduce carbon emissions and the electricity cost by using workload migrations. So in this plot, it's showing 2 different data centers in Europe. Our case studies were, at least for this slides, for this presentation, I'm showing mostly from data from Europe. It's looking at different data centers in Norway, Germany, and Denmark. And if you look at on the right-hand side, you're going to see one data center from Oslo, Norway, and the other one from Germany, Düsseldorf. And these bars are showing what's the maximum reduction in electricity cost or the carbon emissions by using workload migration. So since the electricity cost and carbon emissions are changing throughout the day, you can basically make intelligent decisions on when to move your workloads from one location to another to take advantage of different carbon emissions and also different electricity costs. So this tool allows user to analyze what benefits can they get if they deploy workload migration in terms of electricity costs and carbon emission reductions. So where do we go from here? The need for this tool was because of the data gaps that I was discussing. So we need tools that can allow us to do some sort of sustainability analysis without requiring tons of detailed data. So this tool, Carbon Meter, is the first version of this attempt, and it's an open source tool that enables users to do quick analysis on data center carbon footprint. But the longer term vision for Carbon Meter is to turn it into a framework to evaluate different carbon aware management policies, such as I showed you a case study on workload migrations, but there might be other techniques that can be employed. And Carbon Meter, the vision for Carbon Meter is to be this framework that can use these plugins and then it will allow users to do different analysis on different policies and management techniques. And then another direction for Carbon Meter in the future is to make it an extensible tool to integrate with other carbon aware tools. So this is not the only carbon aware or carbon footprint tool. So there are other tools that comes with different features, but the goal of this tool or creating this tool is to provide this open source framework that can be also integrated with other tools, as well as some other LCA framework, lifecycle analysis frameworks and databases. So there are tools, but usually these tools are disconnected from each other. So I think Carbon Meter has an opportunity to be able to this framework that can integrate different databases, different data types, different tools, as well as different embodied carbon estimation tools. I think there's a huge line of work in academia that are trying to come up with embodied carbon estimation methods so that we don't really rely on the data published from companies, because NVIDIA, for instance, or AMD, they don't really release any data. So we need these sorts of embodied carbon estimation methods, and there are good line of work in academia that are coming up recently. So Carbon Meter can also be used to be integrated with these type of estimation methods, and then it can be this one hub for carbon footprint analysis for data centers. I think that wraps up. So thank you.
Thank you to our wonderful speakers. We'll now proceed with a short break before starting on our fourth and final panel at 4:10. Thank you.
It's open source right now, but it's not empty. That's why I still
所以俩又收获一个包吧。
Sure. Okay.
Yeah, let's do it.
Thank you so much.
Hi.
Get all this panelists coming in a few minutes. Yeah.
Hey, they're over there.
Yeah,
They
yeah.
know I'm here. We've talked.
Thank you so much.
And is Clara remote?
Yeah, Clara, she's in Europe, so.
Yes.
Yeah, unlike our friend here.
I know, he came. He's been having a nice time at Harvard.
Yeah.
So, went to law school yesterday. I arranged with the professor.
Yeah.
So he sat in a class on international human rights. And it was interesting.
Yeah.
And kind of the American perspective. Then Kennedy Center lecture, Paolo, and he and Paolo have hit it off.
Yeah.
Yeah. So I think that's all good.
Yeah.
But he did have you should definitely connect with him.
Yeah. For sure. For sure. Yeah. Right. Okay. Sounds good.
So this is in the Charles Hotel.
Yeah.
Charles Hotel. I'm gonna stand over here. Paula. There, I mean, she's gonna be great.
Okay.
You know what I mean? I'm trying to get her.
I got
And
you.
then it's not so.
I'm ready. Yeah, we're gonna start in like sharp at 14, so like 4 minutes. Yeah. Yeah. Let's keep this. Yeah, exactly. Hi. Sure.
Yes, I think that India will introduce you at first, and you go to the stage first.
If everyone could kindly make their way back to their seats so we could start our fourth panel. This panel will discuss how policy frameworks and investment strategies can accelerate the development of sustainable AI ecosystems. I have the pleasure of introducing our moderator, Karen Clopton, former Chief Administrative Law Judge for the California Public Utilities Commission. Please welcome Karen, and she'll be introducing our esteemed panelists.
Thank you very much. Hi, Clara.
Hello, good afternoon.
This session, we will be discussing how policy frameworks and investment strategies can accelerate the development of sustainable AI ecosystems. Now, there are some who would believe that putting sustainable and AI together at the moment, just like green AI, is an oxymoron. But that's what we're here to talk about. Our esteemed panelists will explore public-private partnerships, financial incentives, and regulatory frameworks. As you just heard, I was the Chief Administrative Law Judge for the California Public Utilities Commission, so I was the regulator for 10 years. In addition to that, I was a human rights commissioner in San Francisco, and so I'm concerned about social justice impact of AI, as well as the siting of data centers. So we'll be talking about those issues, because we really do want to figure out how to encourage sustainable practices in not only data center design, creation, and siting, but in AI applications. We'll also be addressing how the regulators, both in Europe and in the US, view AI and energy markets, as well as consumption, and what the regulatory environment is at this time. Our panelists include Clara Talibert-Ritz, who is online, and she serves as Deputy Director and Legal Advisor in the Legal Service of the European Commission. She leads the Knowledge Management and Artificial Intelligence team and has played a key role in shaping digital and environmental policy within the Commission. As coordinator for the European Green Deal within the legal services, she has been actively involved in its legal implementation. We're looking forward to hearing about the European Green Deal from Clara, as well as in the legislative process leading to its adoption. We have Ari Pesco, who is the director of the Electricity Law Initiative here at Harvard Law School, where he researches and writes about electricity regulation, focusing utility oversight and legal frameworks shaping the energy transition. His most recent paper is entitled "Extracting Profits from the Public: How Utility Ratepayers Are Paying for Big Tech's Power." Be interesting to know from Ari what he thinks about crypto mining companies making more money from power, from generating power or not generating it, than they do from crypto mining. Benjamin Sovacool is director of the Boston University Institute for Global Sustainability and a professor in the Department of Earth and Environment. Dr. Sovacool works on areas of climate policy and energy justice. We also have Vernon Turner, who is the Director of Sustainability Services at Cognizant. He has been involved in green IT. There we are again, an oxymoron, but since 2009. and is a frequent advisor to the F100 on sustainable IT. He has collaborated in sustainability frameworks and measurements, such as the foundation of the community-used PUE, Power Usage Effectiveness metric. And last but not least, Galen Nelson is the Chief Climate Officer at the Massachusetts Clean Energy Center, where he focuses on emerging markets, manages strategic partnerships with corporations, academia, and international entities. Without further ado, I'd like to start by asking Clara about the European Union. The European Union has made a binding commitment under the EU climate law to become the first climate neutral continent. The European Green Deal, alongside the recently adopted Fit for 55 legislative package, sets the EU on course to reduce greenhouse gas emissions by at least 55% by 2030. These numbers, if you've been listening all day, are astonishing given where we're going in the United States. What role can artificial intelligence systems play in supporting the objectives of the European Green Deal?
Thank you very much for the kind introduction and then for this question, which is a burning one here on the other side of the pond. And here I am to give you some perspectives from the European Union's point of view. So indeed, the European Green Deal pursues very ambitious environmental goals, which require the green transition of many sectors of the economy and the whole society. And we think that the AI can contribute to the achievement of the goals of the green transition. But at the same time, we are also aware that digital technologies considerably increase energy and resource consumption and create risks of adverse environmental effects. This ambiguous picture illustrates already that political and regulatory action is necessary to channel the potential of AI towards the goals of what we call here in Europe the European Green Deal. We are convinced that the AI has the potential to achieve a green transition in several fields of environmental policy, and I would give you some examples. We are convinced that AI has enormous potential to accelerate the analysis of large amounts of data to increase our knowledge base, which would allow us to better understand and tackle environmental challenges. For example, the combination of Earth observation data with artificial intelligence can offer more effective, efficient, and timely monitoring of environmental impacts and trends. AI-generated information can also help consumers as well as businesses to adapt towards more sustainable behavior. Furthermore, automated steering mechanisms and technologies enabling predictive maintenance can also increasingly optimize a safe operation of infrastructures. But we also consider the potential of AI through sectorial assessments, and we think that AI can also play an important role in various important sectors of the green transformation. Some examples in this regard, AI applied to monitor and optimize energy consumption can support, for example, integration of renewable energies in the electricity grids and has also the potential to support the key priorities of increasing energy efficiency in the building sector. Furthermore, applications in agriculture may also allow for more efficient use of water, pesticides, and fertilizers, and they can thus mitigate environmental impacts. The same is true in principle for the transport sector, where AI-based methods are already used for improved planning of transport systems and infrastructure. They can contribute to increase energy and engine efficiency, optimize charging of electric vehicles, and they can also help coordinating the different transport modes or the control and management of, for example, railway systems. And finally, we are convinced that there are use cases of AI which can also contribute to strengthen the circular economy by making eco-design more effective, by assisting the inspection, the sorting, separation, and disassembling process to circulate products, to circulate materials in the economy. I would stop here, but I'm happy to reply to any further questions.
Thank you, Clara. We will definitely be getting back to you with questions about other EU acts, especially regulating AI. I have a question for Galen, who is also a senior advisor on market development programs across multiple sectors and sits on the MASS CEC's executive team, helping to shape organizational strategy and direction. Galen, what does the data center landscape look like right now, right here in Massachusetts? How do you see it evolving, and what energy policies should states contemplate to navigate the energy and grid impacts posed by these data centers?
Thanks, Karen. For those of you who aren't familiar with the Mass Clean Energy Center, we're the state's clean energy and climate tech economic development agency. So we're somewhat uniquely positioned in this space in that we're both, I think, generally enthusiastic and hopeful for the potential for AI to accelerate innovation in many of the areas that my co-panelists just pointed out from the EU, that there's a lot of opportunity to accelerate our climate progress, while at the same time being fairly concerned about the immediate energy impacts of AI. So we need to have a kind of a nuanced view of this rapidly evolving landscape. With regard to the data center environment here in Massachusetts, we're not facing the type of massive increase in demand that, for example, Virginia is looking at, particularly Northern Virginia. But there are about 40 data centers here in the state, mostly small data centers in the 3 to 5 megawatt range, about 180 megawatts total. And there's a lot of demand in the interconnection queue, according to our utility partners. Now, to be clear, this is a market with a lot of speculation, so many of those projects may not move forward, but nonetheless, substantial demand in the interconnection queue. And just to kind of put that in perspectives, and to be clear, well over like 1,800 megawatts of demand. And to put that into perspective, assuming a 45% capacity factor, you'd need to build out about 350 some odd megawatts of offshore wind to support a 250 megawatt data center here in Massachusetts. We've built about 800 megawatts of offshore wind thus far. We've got about another 1,900 planned. But again, just to put this in perspective, we're really struggling to meet our clean energy deployment goals.
So adding additional load at this time will be a real challenge for us. It's hard to say how the landscape will evolve, but we're certainly keeping a close eye on it. I don't want to spend too much time on the policy solutions because I think we'll probably get into that a lot later, but just reacting quickly to some remarks in an earlier panel, it's a lot of the usual suspects, efficiency, renewables, load flexibility. We can get into more detail with those, but I guess if I could underscore one point, it's that some of those objectives are much more difficult to achieve than others. We're really struggling again to build out new generation here in the state. Building distribution system, electric grid infrastructure is also very difficult. So we clearly need those assets. We need that infrastructure, but building it is quite difficult. I'll stop there for now.
I'd like to ask a kind of a positive question of Benjamin, because we've heard a lot of negative things about AI and data centers. Are they always bad for the environment, Benjamin, or are there ways to make their carbon and energy footprint lower?
Wow, what a nice question. I wonder who posed it for the panel. I first want to call out my colleague John, who's here in the audience, who just presented on data center management and some of the things they can do to minimize its operational footprint. But kind of taking a step back, in the energy policy literature, there's often a discussion of kind of supply push, demand pull policy incentives. And I think we often focus so much on the technology. I want to start with demand. There's a lot that we can do to curtail useless demand for AI. For instance, not every student should be using AI every class, running all of these searches with ChatGPT, which have a real footprint. And not everything, you know, if you're playing a trivia game with your partner and you really want to contest one of their answers, maybe don't hop on Google to search or watch a video about all of those, because all of those really do have a material footprint, right? We often think of the cloud as invisible, but the cloud is really a bunch of tech and stuff. So first, I would just say, let's just all be a little more aware that how we use these types of energy services. And the Intergovernmental Panel on Climate Change, their most recent report on energy demand is fascinating. It even argues that we could further reduce our own energy demand by 75% by mid-century in high industrialized countries like ours and Norway and Germany and so forth. So I think that's a little bit of a kind of the devil is us. And there's a lot that we can do just to be more aware and more conscious of how much we use AI. On the supply side, I often tell my students and colleagues to think broad about multiple leverage points, each of which can make AI or data center use more sustainable. So all the way at the beginning of the supply chain, more aware mining and minerals. So we have a better sense for cobalt, copper, gold, silver, all these things that go into making servers, microchips, and computers. There are really responsible companies and there are really irresponsible companies. And so suppliers could choose more responsible ones. At the level of data centers, how we make them, how we put servers into them, types of technology that we use, and what we're willing to pay all matter. And again, as even John was presenting in the session earlier, there are some data centers that have beautiful carbon footprints and those that don't. So why don't we follow best practices and not worst practices? And then lastly, two other elements, energy supply, offshore wind, great. Diesel, coal, oil, not very good. And by the way, I got my PhD from Virginia Tech in Dominion territory. It's still mostly fossil fueled. So like, you know, the Virginian grid, PJM, is not very good from a sustainability standpoint. The Mass Grid, New England ISO, much better, right? With at least some wind. And then of course, California grid, probably even better because it has less fossil fuels. And that's something else that we found in our research. Of course, the composition of the grid directly relates to data center footprints. Clean grids create cleaner data centers, dirty grids, dirtier ones. And lastly, what we haven't talked about much is waste, the afterlives of servers, computers, equipment, and data centers. How long do we operate them for? And do we have good take-back schemes for these devices, which sometimes have lifetimes of just 2 or 3 years? Where does all of this go? And I've read projections that the embodied e-waste in certain forms of data center infrastructure could actually outweigh all e-waste by mid-century. So we have a hidden challenge of what the heck we do with all of the tech. I'll stop there as well. Thank you.
I'd like to turn to Vernon and ask him, what are the main sustainability concerns while deploying or using AI?
Thank you, Karen. Thank you, Karen. So when we're looking at AI, one of the main concerns is obviously the amount of energy. We've heard this repeated and repeated today. When we think about the AI component of data centers, I heard earlier it's 21%. It's the number given out by IDC that says it's about 120 terawatts of data, which is almost the same capacity as Sweden as a nation. So when we're thinking about the challenges for AI, the energy consumption is obviously number one. And I'll come back to that in a little moment about how you can address that. And ironically, the second biggest challenge is waste. What are you going to do with all this material and in terms of its life cycle, its circularity we heard earlier. So those are two of the main ones. But the third one is the actual unbiased nature of the data and how that data is secured over the life of a data center. Because it's fairly easy today to lock down data that's inside a particular facility. Now, one of the things as a contrarian, what I look and say is we think and understand data centers as being the sole solution that we're looking at, a 10,000 square foot, 50,000 square foot entity. But in actual fact, we should take a step back and look for the best fit for an AI application, which might be in the cloud, which is low intensity in terms of emissions and carbon footprint. Probably find co-location is probably somewhat of a best fit in terms of the interaction between private and public. When we think of the enterprise, and that's what I think we've talked about a lot today, that's closest to the data, and therefore it cuts down on a lot of connectivity issues and what have you. But last but not least is the edge computing environment, which is closest to the consumer, the customer that wants the data itself. And the reason why I lay it out like this is that as you go through each of those phases, you're going to be creating content about a model that's created some output, or you're going to be doing some activity, and you want to be able to, as it were, sometimes we call it the digital Easter egg of where the output is actually going and how that affects people, which then leads to the whole idea of privacy and intellectual property rights. So it's not just a simple matter of saying what happens to the data center in terms of energy. I think you really have to take a step back and say, where is the AI application going to reside? And then from there, as a CIO, you're going to have to understand, where do I have to put my efforts to make sure that data is secure, not just from a physical location, but really from a usage perspective. I'll stop there.
And I think I'm going to treat Ari as a Nostradamus. What does unsustainable AI look like, and how can we avoid that future?
Well, I'll definitely answer the first part of that question. Not sure if I can answer the second part, but a bit of a pessimistic message here, but it's my fault for reading the news these days. So Benjamin alluded to one aspect of this, which is that we have different power grids in the United States. And there's been a good news story over the past decade plus of these sort of power systems are getting somewhat cleaner over time because coal power plants are going out of business, they're retiring, more clean energy is coming online. But we're starting to see some reversal of those trends. And it's either directly because of AI or people are blaming AI because of that. We have some large utilities, for instance, in the Southeast that were planning to retire coal plants, but now because of data centers are not going to be retiring those coal plants. We now have an administration in Washington that is explicitly trying to maintain coal plants, keep them online that were otherwise going to retire. And their justification is because we need to be, in the AI race against China. And I think they have other agendas as well, but they're at least using AI as a cover story for keeping these coal plants online. So that's an unfortunate turn of events. And, there's a lot of things we're going to see how they play out over the next 4 years. There's another aspect to sustainability that I don't know. I think it depends on how broadly you look at sustainability. I'm very concerned about, we heard a good story about sort of some of the very positive use cases of AI at the start of this panel, and those are great. Hopefully we can talk more about those, and I can be pessimistic about those as well. I'm quite concerned about detrimental uses of AI that may be happening right now. So for example, using these systems to target disfavored, oppressed populations like undocumented immigrants in this country, or targeting the administration's perceived enemies, and using these very powerful systems to do things that we could only have dreamed about a few years ago that could be quite destructive. So how do we avoid that? Well, I think there's a broader conversation, I think, about where this country is going and how we avoid potential bad outcomes. On the energy side, I mean, to get back to that story, the industry, I think, has, like I said, has been heading in the right direction. And there have been a lot of attempts at the national level, at the state level, at the corporate level, with voluntary pledges from some of these tech companies, with the utilities moving forward in different ways. And there's been a really good story, and we just have to make sure that we're keeping up that progress and not slinking back over the next few years.
Well, after Ari, I'm contemplating moving to Europe. So let's talk to Clara about the EU's AI Act, which is the world's first binding regulation on artificial intelligence. It was entered into force last August. How does the Act contribute to the development of environmentally sustainable AI? Both systems, and in what ways can it drive improvements in the resource and energy efficiency of AI technologies? Clara?
Yes, thank you very much for this question. I mean, this question is again about regulation, and we know that the critics from the US is always that we like regulating. But I have to tell you that when I speak to law firms here in Brussels, American law firms, they just begging us. They say that please regulate, 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 because this is how we will. This is a treasure hunt for us, because we have to make sure that the companies comply with all these requirements. And indeed, the AI Act puts a lot of obligation on high-risk AI providers and deployers as well. But now going back to the origin of the European Artificial Intelligence Act, actually its aim is to support an EU internal market for a secure, trustworthy, and ethical AI system. So this regulation is based on a risk-based approach and lists prohibited AI use cases. And it contains very serious and strict rules, specific rules for AI systems with high risk to health, safety, and adverse impacts on fundamental rights. So this is, in a way, the recipe from Europe to the concerns raised by my co-panelists, that if fundamental rights are at stake, maybe the best way is to regulate and then enforce, of course, enforce the rules which are set out in legally binding norms. Now, more specifically, the EU AI Act contains a provision, it's Article 40 of the Act, which establishes a framework for developing harmonized standards. Harmonized standards to enhance the resource performance of AI systems, with a particular emphasis on energy efficiency. Under this provision, the European Commission, this is the organization where I work, is tasked with initiating the development of standards by requesting standardization bodies specifically address the energy consumption of both high-risk AI systems and general-purpose AI models across their entire life cycle. Now, Article 40 also underscores the importance of international collaboration, and this is a very important aspect. International collaboration in AI standardization. And it requires that European efforts take into account existing global standards and that we should actively contribute to strengthening internal cooperation, which, in our views, has the potential to significantly improve the environmental sustainability of AI technologies. One of the most forward-looking aspects of the AI Act is to support the innovation in a controlled environment that enable the testing and development of innovative AI systems under real-world conditions, but with less strict legal obligations. We call them AI regulatory sandboxes. And these sandboxes not only promote responsible experimentation, but also provide a space to focus on broader environmental goals, including biodiversity protection, climate change mitigation, and overall environmental sustainability. We think that they should play a crucial role in identifying best practices for developing energy efficient and environmentally conscious AI solutions. However, we also know that this AI Act is only the first step, so the first baby step to regulate this technology. And we also listen to the critics, of course, which say that the Act focuses too much on energy consumption. Maybe it's too narrow and overlooking other vital environmental concerns, such as water use, raw material extraction, and electronic waste, as we also heard from other co-panelists. So we are also looking into this matter to ensure that AI evolves as a genuinely sustainable technology, to try to develop a broader, more holistic approach by taking into account certain other aspects as well. For example, establishing standardized metrics to consistently measure AI's full environmental footprint, or to leverage public procurement to drive market demand for sustainable AI solutions. Also considering and raising awareness about the long-term social and environmental implications of AI-driven climate strategies, and to use AI to power environmental management tools that help address ecological challenges. So, in summary, we think that exploring these additional dimensions could provide a more complete understanding of how to build sustainable AI ecosystems. But we are also aware that ultimately the success of any regulation, including the AI Act, will hinge on the specificity and ambition of its standards, as well as the speed and commitment with which industry stakeholders will implement these rules.
On that note, it would be great if the panelists would address AI in sustainability and what is sustainable AI. Maybe we'll start with Vernon.
Yeah, I think it's really important to understand the difference between sustainable AI and sustainability in AI, because again, that's a journey that the maturity of AI will take. When we think about sustainable AI, we're thinking about how to make our models more efficient. What's at the silicon level, how to do things better. Really trying to make that piece as small as possible. But as that becomes more mature, then you start to see AI in sustainability, where you see the use cases start to pop up, and where AI then needs to be running, as our co-panelists just said, in a standardized manner with metrics that everybody can understand. And really one of the things that we see here is there are a severe lack of standardized metrics by which you can compare two users or two applications or two workloads. So you can understand better, is it really worth doing this piece of work? Is it more valuable to me as, say, for example, if I'm a CEO, I don't know really what the cost of running my AI application is. And what I will say is where that extends to a little bit of the, not quite the Armageddon dark theory, but that the hyperscalers don't really want you to know how much energy you're using because your subscription model is only based on the size of compute and storage that you consume. But what happens with the energy, you get billed for that as a lump sum. And as a company, that energy bill is then just peanut buttered or spread over everybody. So everybody gets an equal share of your bad behavior. So what I think here is you need to understand what the journey is as the industry matures from that sustainable AI, which we've heard a lot about in depth today. And really, as you look at it from a business perspective at the end, where AI in sustainability will help change behaviors. Okay.
Ari, are you as optimistic?
Well, maybe I'll raise a tension in all this and a concern. So I guess that's not optimistic. Some of these sort of use cases that I think have promise with regard to our power system, or making the interstate power system here in the U.S. operate more efficiently, connecting clean energy plants more quickly to the system. Right now, this process can take years, and maybe we can dramatically speed that up. At the local level, you can imagine AI helping to efficiently charge electric vehicles in a way that doesn't stress the system. So all these things can be imagined as potential massive benefits that are enabled by AI. You run into this tension, though, where our power system is largely controlled by monopolies, our electric utilities, that are the opposite of innovative in many ways.
Analog monopolies.
Sure, they're analog. And so you have this tension of these sort of tech companies that historically have wanted to go fast and break things and innovate, running up against now they need this energy that's being delivered by these monopolies. And so the extent to which the monopolies that still control the power system can integrate the uses of AI in their actual operations is really an open question, because historically they have not had any financial incentive to innovate, unlike the tech companies who their incentive is to innovate. And the other danger with all this is potentially with AI, depending on how this develops, do we have sort of one company that develops the best AI that then dominates? Do we have a few companies that dominate this AI space? Who knows how this is going to play out? But then you could have sort of AI monopolies looking, just to protect their turf rather than really innovate in interesting ways. And so I think this tension with monopolies in the power sector and potentially monopolies in the big tech monopolies as well could really inform how this all plays out.
Galen, what do you think the state regulators should do in this instance?
Well, first, I think it's important it was wonderful to hear the perspective from the EU, and I think it's fairly clear to everyone in this room that we're not going to see that kind of leadership at the federal level here in the States. But to be fair, under any administration here in the federal level, it's important for folks to understand that with the exception of the transmission system, energy and the spheres, the kind of jurisdictional waters that impact data centers are largely regulated at the state level. So whether we're talking about the built environment and building code, there are some national standards, but statutorily, those sectors are regulated at the state level, where we're talking about energy siting. The mix of energy on our grids is a little bit of a mix there, but whether we're talking about the building out of the distribution system and how utilities are regulated, those are all regulated at the state level. So our success, as it were, to manifest a sustainable AI future will really turn on whether states lead on this issue, at least from an energy perspective, or not. And I think it's important for folks to understand that we're not going to see kind of a federal government sweep in to rescue us. And again, not simply because of the current political environment, but simply because that's not where the jurisdictional authority lies for much of what will impact the carbon footprint of data centers.
Well, nobody's coming to rescue us, but I'd like to know from Benjamin about the environmental justice aspect of this.
So there are innovative tools in energy policy that apply almost directly to data centers. And so, I mean, I'm a huge proponent of energy efficiency, demand response, load management, which give better price signals and information. So if it's just one big, block unit, let's make real-time prices or time of use prices, visible for consumers, or more visible, or have utility scale incentives so that the data center providers change their behavior. The big industrial demand response programs have helped hit industrial users in many, many states, even in this deep South, where if you give them different price signals, they will immediately change some of their consumption patterns. And then the other thing we're working on at BU is, well, some of the biggest curses of data centers, they're huge loads of energy. They create lots of heat, can now become the tools. Let's make microgrids and distributed generation where maybe they provide heat. And I can give you one promising example, unfortunately from Europe, but I was visiting PIC, which is the Potsdam Institute for Climate Change in Potsdam outside Berlin, and it was in a nice new building where their supercomputer heated the whole building. So they didn't even need to actually create fossil fuel heating, because the heat generated by that computing device, I took a picture, and I was comfortable the whole time. I was actually hot. People were opening the windows because there was that much excess heat generated from all their modeling runs for climate change. So there's an example of, why don't we think more about integrating data centers in a way that's more distributed, closer to where we use heat and energy services on campuses, hospitals, neighborhoods, and so forth, which also will minimize losses that are associated with having data centers so far away, or in Virginia or offshore, and so forth. And so this has been a trend towards distributed generation for electricity, solar photovoltaics, small-scale wind, small-scale hydro. Let's do the same for data centers.
Yeah, I agree that there's great promise, I think, to leverage waste heat from data centers, and that will certainly involve, I think, a new, novel, and much more integrated approach to both energy planning and economic development.
This behavior change by both consumers and the tech companies, what does that look like for cloud service providers in terms of, should they have the right to use your AI-generated data to provide and improve their services, such as energy and compute cycles reduction? Vernon?
So I think it's going to be a fight between what the hyperscale cloud service providers want to do with your data, and do they have the right to that? And I think you'll find in the small print that they can use your data to improve their efficiency. Now, that goes back to what I was referring to earlier. Whose data is it, and how was it created? For example, was it created by AI itself in terms of generating that output, as opposed to your raw data that you have running as a business unit? So I see this food fight happening again, because I think there's going to be this idea that can hyperscalers, cloud service providers monetize any of that? to say, look, you know, you could run better if you did this, because we see on the backside of it what your implications are for the environment, and therefore you could do better. We benchmark you, and this is where you go down this tricky slope of trust here. We can benchmark you against somebody else in your industry. We won't tell who that is, but this idea of subtle marketing and subtle, I call it threat behavior, is something that I can see popping up over and over again here.
Ari, what do you think about the food fight? The food fight Vernon is talking about.
The food fight for who can monetize the improvement of the data. Is it your data? And therefore, if you want to be able to improve it, or is it the cloud service provider that's hosting the data that says, you know, I know how much energy you're actually using.
Right. No, I mean, look, I think my assumption is the service providers will own as much of this as they can. Absolutely. I mean, that's been their business model, as I understand it, for some time. So anything that you type on the internet belongs to them. I mean, look, we have a copyright lawsuit playing out right now with OpenAI, right, is being sued by the New York Times, I think, and others. But, you know, all of the information, if you've ever published a website, if you've ever written an academic paper, you know, it's been gobbled up by these systems. I think whatever they can gobble up, whether it's related to energy use or whether it's related to content, they're going to want to gobble it up. I don't know how you shift that incentive. I mean, I think at least in the energy space, there's been a sort of a long-term sort of consumer empowerment movement that has a lot of good ideas, but I don't know how much real progress it's made. And so maybe there's an analogy there. I just don't. I think they're gonna. This is what they do.
I'd like to open it up to the conference attendees. Are there any questions from the audience? Yes.
Well, the question is an elaboration. We're talking about how to intensify or put the users of
Is the mic on? Because we can't hear you.
The ChatGPT users, how to shape their behavior of usage of the LLMs. An idea, you know, you're charging for electricity as a user. So why don't you charge for usage and you put them, you use this much energy, you generate by your questions this much CO emissions. At the same time, I just heard the other rather read article. Mr. Altman, OpenAI was unhappy people saying thank you to LLM because it burns so much energy. Because technically how the LLM works, every single whatever demand or question you have, it processes. It's not like filtered pre-made answers to it. So technically it's running for no particular reason.
So can I just take a quick? So one of the difficulties that we're facing with is, and I dealt with this in the financial services industry, is accounting and chargeback is a really boring topic that CIOs and CEOs don't want to deal with. And when I say that is business units don't want to know how much it costs to run their application. They just want to run the application. And what happens is CEOs say, of course, I want to grow the business, go and run this application. So chargeback and accounting for consumption has always been a bugaboo with the industry. But I think the issue here is that with things like agentic AI and what we see here in terms of the explosion of applications using AI is going to make that chargeback even more difficult. And therefore, if someone in the room can come up with a application that's able to do that, I think you will be very well compensated for that effort, because nobody knows how much it costs to run that inquiry using AI. And I think to Roman's point, if you saw something that said, this is your carbon footprint, do you want to proceed? Or if you have exceeded your budget as a business unit, go back and get more approval. I think you'd start to see behaviors, and I think that's the difficulty. The last point is We heard earlier today about shaving. And again, as a capacity planner, I used to be able to see this, what we call a camelback. You know, it was a two-humped peak usage in businesses, typical mid-morning, mid-afternoon, and try to shave that off. It is really difficult to shave that off with a dynamic inquiry that AI is generating. You know, what are you going to do? Stop it in the middle of doing its modeling? Not going to happen. So I think the only way you can change that behavior is to say, look, this is how much you're costing us in the environment space, in the energy space, in the infrastructure space. Do you want to continue with that? So.
Are there any other questions?
If I can just add just quickly from a behavioral standpoint, 2 other tools that we don't like, but they work are restrictions and scripts. So right now, I have a whole bunch of human students who are trying to grab articles from Scientific Direct and they get caught after 20 downloads because all these, you know, ChatGPT ones are kind of restricted. So it works, like they're not able to download more than a set number. They've reached the maximum for a day. They have to literally wait another day. And then scripts would give warnings. So with some smart home energy systems, if they're using, for instance, a home in Florida wants to heat the pool, start the air conditioning, but also start the floor heating to make your feet comfortable when you get out of the pool, which people do, it'll give you a warning and say, well, that's going to cost $5, and it will kind of help give you more information. So both of those things might work in an AI context to say, you've already run 5 GPT searches today. That's it. You can wait till tomorrow.
I'd like to thank the panelists. We've come to the end of our panel, the end of the day. Thank you so much. Thank you, Clara, for joining us. We appreciate you.
With pleasure. Thank you.
European Commission. Please stay on for a moment. I think we're going to take a photograph and we want to include you. Okay. Thanks. No, no. And I like you. Good job. I appreciate that.
Roman used to work with me.
Yeah, I know.
And I said, do not ask the question. He goes, I'm going to ask the question. Thank you. Thank you. Thank you.
After they finish, we can start. Or yeah.
Yes.
Yes.
Thank you to our speakers. I would now like to transition to our last event of the day, our launching ceremony, where we'll be launching the Journal of AI and Sustainability and the establishment of the GRI AI Institute Advisory Board. Please join me in welcoming the team.
Thank you, everybody. I know I'm the last one for today. We have gone through 200 slides. for today over the past 10 hours. So thank you for your patience. And let me just finish today by telling you who is behind the scene. So first of all, I just want to extend our greatest gratitude to our supporters of this event, especially a shout out to Professor Ayşe Koskun from BU SAIS and our amazing sponsors here with different parts of Harvard University, including the Office of the Provost and Slaller Institute and OFS. Today, I'd really love to extend a warm and great gratitude to everybody who is behind this whole journey. We have spent the past almost 6 months from different teams here. We don't have their names because it's too much under one slide, but we have over 60 people from our summit organization team and from our white paper team. All of us, I'll tell this in details when I finish my speech. And just a quick what's going to happen is I'm going to speak for 5 minutes, and then I'll introduce all of my staff on stage to let them come to the stage. And then we're going to have a photo with our staff, and eventually we'll close today with the photo with all of us here. So that's just what's going to happen in the next 10 minutes. So I know some people has joined us later today. So we have already presented this in our first meeting in the morning, but for the people who came in the afternoon, and we just want to say that please feel free to scan our Google Books book. And just to zoom out a little bit, in the past 10 hours of today, we have spent a lot of time coming from the first panel, which is about the technology innovation, to the second panel, which is about public health effect, to the third panel, which is on the cutting edge quantum computing, and the fourth one that just finished with the cases from the Massachusetts and European Union. And we know that this conversation would go on, and many people here, you might have the answer, how can I learn about this systematically? And that's why we have presented our white paper already. We only have a few limited copies, but because of the sustainability promises, all of them have already been available on the Google Books. So please go there and please scan the code. And just to zoom out a little bit, today we have a lot of cases about United States, because here we are in Cambridge, in Massachusetts. But our white papers, not only did we talk about different factors of selections when it comes to cool climate, natural hazard resilience, stable power grids, we also look at different kinds of economic and government incentives, which I'll show you the slides later. But first, there are so many things that are happening outside the world. And there are so many new Virginias that is happening in every part of the world, especially in Southeast Asia, Middle East, and Europe. When it comes to Southeast Asia, this triangle, which is the Sijori region with Singapore, Johor, and Batam in Malaysia and Singapore, have been growing its data center infrastructure over the past few years. We've looked into some very interesting case studies, including Day One, how they are using renewable powered campuses linked to Singapore via submarine cables, and how they are using their model to optimize cost and connectivity. We also look at one of the cutting edge projects in UK, how the cloud data, how they are using 100% wind power and make sure they can have the sub 2 millisecond latency to the major European exchanges. We've also looked into, in the United States, how all kinds of big hyperscalers, Meta, Google, what kind of facilities, their data, and how they're using different kind of technologies like closed loop liquid cooling to have almost near zero water waste with a WE over 0.1. And we also look into, basically, this will give you a systematic way to look into how those companies are using the latest hardware, the latest cooling technologies, and all kinds of energy sources to achieve their ambitious goals. And you might wonder, we have so many policies covered today, and how can I find them? You can definitely find them on GPT, but we already have our amazing researchers to sort them out for you, looking into some of the key regions, looking into the government approaches, nuclear energy proportions, and new actor development, etc. And we also look into basically all different countries, what kind of advantages they have in this big AI race, what kind of challenges they have, and what kind of regulations and policies they have in place. And with all kinds of United States, many 50 states, all of them have different regulations to attract or not to attract. And we have also looked into a lot of the most symbolic states and looking into their benefit, their minimum investment criteria, job, station requirements, etc. And we also believe that this is not a book to ourselves. We also, as we mentioned in the morning, we are launching this open access journal, AI and Sustainability, to promote innovative research and facilitate knowledge exchange. Our scope, we look into some particular areas when it comes to many of the topics today that we have discovered. AI carbon and water footprint, AI governance, data center decarbonization, advanced computing, because we believe that there are so many different fields that make green AI achievable. And my personal story, why am I doing green AI? Everything started 2 years ago. I was working with a professor here at Harvard who is doing computer architecture. And I found out that he has done amazing journals in ASP+, like those so many computer architecture journals, but nobody else reads it. They're talking about how they can have more better computer architectures to reduce the life cycle, especially the embodied space that Carol earlier today mentioned. But when I go to a different conference, when it comes to like computing system, when it comes to data center operation, when it comes to the PES, power and energy system, and that is the engineering side. And now we're talking about like legal and policy. And then 2 years ago, this is newfound land. And that's why I started the whole Green AI Institute and our Green AI Summit deliberately to bring people like today from all kinds of backgrounds, because they cannot just talk in their own room in IEEE, ISO, ITU meetings, or in those PUC meetings. All of them have to come together. And that is why we are doing all of this. And we do not just want to do it once a year. We want to use more open digital platform to share those information online. So we're also calling for papers and calling for editors and reviewers for us to keep this nonprofit and keep this platform open. And every year in our annual summit, we're using this flagship event to feature some of our best postdocs, best researchers. And just a quick invite again for all of the people here today. We'd love to welcome to become the member. As a student, it's perfect for you to get to know more companies. And for companies, it's perfect for you to find a group of organized smart people. You can find smart people everywhere, but it's not easy to find a group of organized people that we convene together, and we host weekly meetings. As I mentioned, we do things, we do stuff, books and all that. So that's why and today we just have people reaching out to us from RPI, setting up a new chapter there. And we have so many emails in our inboxes. And eventually for our industry partners, as I mentioned, you might talk to this person and that person sporadically, but we are a nonprofit that our mission is to convene more people and to do research to make them publicly available. And if you have relatively more, busier schedule, then you can join us in the volunteers. You can help us with video editings and marketing and partnership and all of this. Because talking about marketing, most academic work are amazing, but the more we write, the more we realize that how important it is to voice it out and present it to the right people, like here. So as just conclude, our mission is to build greener and more equitable AI through so many initiatives. And here I just want to do a big shout out. And by the way, if there are volunteers outside, they can also feel free to join in with us. The story of the summit was 6 months ago. We are very lucky, to host our first summit here at Harvard. And with the support of Professor Aisha Kosko at the BU, we're able to expand it. But what's more is we have so many volunteers and staff who are working with us for almost the past 6 months seamlessly. We have people here, in the tech team who are today, they've done a great job making sure the whole YouTube thing is so smooth and the whole Zoom is so smooth. And we also have our amazing, programming team like Tina and Jay-Z who are helping us to, get all the speakers, to make sure you come here at the right time, And we also have our event support team who make sure all the food, all the logistics are, amazing. And we've also got our research team with Stella, Chur, and Caitlin, and many people who are not here today. So as I mentioned, we have so many members. It's hard to put all of their information under one page. That's why we use the, like the screenshots. But all of us here today, we've tried a lot of effort, and we think that this is not the end of our summit. We love to continue with more people, from our team and outside our team to make sure that we can make this, continue in the future. And for the conference, I just want to say that, again, Thanks again for today's speaker, but this is not the end of our conference. I'm just gonna do a quick introduction of tomorrow's meeting, because as you guys might know, this is a collaboration between Harvard and BU. And before I go to the next slide, the way to contact us, there's an email address there. We'll respond to you almost every day. And we also have our LinkedIn. Feel free to contact us with different ways. And just a quick spoiler for tomorrow. Tomorrow, we're gonna go to Boston University across the Charles River in the very beautiful building in the computation and data science buildings. And today, Professor Xie was mentioning the Harvard one is the most sustainable, but I also heard from BU that this is the most sustainable in Boston. So we might have a battle tomorrow, but you know, tomorrow's gonna be even better. So we're gonna start the day with very warm breakfast, and then with 3 panels, we are continuing, exploring, different interesting topics when it comes to people from IBM, from Oracle, from all kinds of leading edge tech companies. And then to the number 6, which is AI and the grid specifically, how there is complex interactions moderated by Professor Koskun. And then after the amazing lunch, the lunch and breakfast are available for all our participants, our speakers and attendees. And we're gonna have the last panel, which is moderated by Professor Suchigopa from BU on AI for global sustainable development, technology, policy, and impact. And we close it the day, the 2-day event. So just, please feel free to come back for Saturday. It will be even better. And in the end, I just want to say a big thank you to our staff. So I'd love to welcome all of the staff and volunteers of Green AI to come to the stage first. And then later we'll have a picture for all of us here. So yeah, so let's give a big warm applause to our staff and volunteers. Yeah, all of us. Yeah, all of us. Please come to you. Yeah. Okay, yeah. Let's invite all of us to come here. Please join us in a big group of us. Yeah, all of us here. Let's do maybe 3 rows. It's a big photo here. Three, two, one, three AI, okay? Three. Super green AI. Super green AI. Thank you.